So we should make Xavier. Oh, there he is. Bonjour, Xavier. You hear me, Xavier?
You hear me?
Oh, yeah, now I hear you. We should, today we are starting at 9:15, so we have a little bit of time. But we can test your presentation.
Yep. So, can you see it?
Now I see it, yeah.
Okay.
I've seen in your titles, I have seen pictures like this. Do you use the same picture every time, or there is a different picture?
No, that's the same. I could not find so many.
Because I've seen it and I forget usually, so
Yeah, I just changed a few things. If you look carefully, that's not the original picture here. It used
so you
to
actually
be triangles, and so it's actually modified.
Oh yeah, I see brain in there. That's interesting.
So that's
how is Miriam?
Good.
Yeah, I told Elise yesterday that you are going to talk, and she says, "Oh yes, I need to send."
Yeah, I know that Miriam asked some news a few months ago. I don't remember exactly when, but
yeah, because of the corona, we can't. With this year, we did not go at all.
Yeah, and it's not going to be very easy for Christmas in France.
I think it's same here. It's very bad. So hopefully this is the last bad month.
Yeah, hope so. So the screen sharing is working.
Okay, I think I just saw Mu Chung come in. So let's make him. Hey Mu, how are you? You're muted.
Hello, can you hear me?
Yeah, now you can.
Okay. Let me test the screen sharing.
You use a different brain every day?
Oh, it's the same brain. It's just different color. We generate like 10 or many different.
It seems like you spend all night generating one picture and then you use it next day.
I think you may want to give me permission, or
you should have permission because you are a co-host.
I see a button called the share screen.
Yeah.
Oh yeah, I can share it now. Okay, let me.
Yes.
Oh.
Can you see the screen?
Yeah. This is going to be a colorful section.
Okay. I think it works. Okay, thanks.
All right.
Let me unshare it. Stop sharing. Okay,
yeah.
Okay.
Unshare, don't log out. Yeah. Do it all over again.
Okay, I unshared it.
Okay. Hello, Ian. Where is Ian? Oh, there you are. Unmuted.
Hello. Hi.
Good morning.
We already
Hi,
finished
hi.
the testing. Okay.
Well, we are still waiting for USA and Sebastian.
They
That
said
will
they'd come on the hour.
Yeah, probably. We are starting today at 9:15.
Yeah, yeah.
I thought I will sleep a little extra, but as it happens, I could not sleep a little extra.
Oh.
I mean, I'll sleep better once the workshop is over.
I think so. Well, it seems to be going very well so far.
Thank you. I'm glad you think that way because
Yeah, no, definitely.
it's a variety of topics.
Yeah.
Statistics and imaging shows up in so many different ways in the community nowadays that you can have very, very different flavors of talks in the same workshop.
Yeah. Yeah. So we've tested Moo's one. Is that right?
Yeah, it was okay.
So
And Xavier tested before you logged. Xavier is fine.
That's good.
Did you know that we are live broadcasting this on YouTube?
I saw that, yeah, yesterday. Yeah, I haven't checked it out myself, but how many people are watching though?
I have no idea. I didn't log in because I think if you log in, it sort of interferes with this setup.
Yeah, I can imagine. Yeah.
But I did send it to my son, and he says he just saw the screen. He didn't see any pictures. He just saw the screen and he heard the speaker.
Yeah.
And of course, he found it very boring and he logged out within minutes.
I don't know. No taste. No.
Yeah, I mean, these middle schoolers
Yeah,
don't
really.
deep learning.
Yeah. Poor parenting. That's what I blame.
Yeah. Well, I did what I could. I should have enrolled them in deep learning right in the elementary school.
So it's a big undertaking for you.
It's not. It's much lighter than when we had it, a few years ago in Tallahassee. That was, the logistics of receiving people, taking care of them, and then making sure of minor issues here and there. This, believe it or not, is all emails. I mean, there is nothing more to it.
Yeah.
Which is very convenient.
Yeah.
Now that begs the question. I mean, in the future, let's say, the virus disappears, like our president said, then what? I mean, in future, are we going to go back to the old style of meetings or?
I think we will, yeah. But I think there will be a room for online ones as well, myself.
Yeah, I think it will be a hybrid. It's not easy to just go back to.
No. And probably we'll broadcast them more, so some speakers might be remote. Because it really is a lot to track. If you travel, I don't know, 10 hours to give a 20-minute talk and then go back.
I mean, of course, you get a lot more at a physical presence, interacting with people and all that. Yeah. There's a lot of rewards there. But in terms of just the pure technical part, I mean, this gets you, and these are fully recorded meetings.
Yeah.
So you can have the recording, and we are even asking for the PDF files. We'll try to post them too.
Yeah, no, I think there's definitely a role for this sort of meeting, I think, or in part. Yeah.
I'm wondering if funding agencies are going to take off the travel money in the future. You don't need that. Just buy a good computer.
I think it depends also what you want to do. I mean, things like meetings in in Oberwolfa or in Lumini. When you
Yes.
are 1 week together, that's much more efficient to actually share. There's much more than just sharing a talk.
Yeah.
Now
No, I
for
think that
the
kind is a different model.
but for just giving a small talk, and that's it, then I agree that it's much easier to just give it well remotely. It's saving travel time. It's saving a lot.
You know, like these huge conferences, then there are these small workshops, and then there are these Oberwolfach things. So I think some of them will be redefined completely.
Can you
Hey,
guys
good morning,
hear me?
Osa.
Hi, Osa.
Good morning. Can you hear me?
Yes, we
Yes.
can.
Brilliant. Just wanted to check. I'm looking forward to it.
And we are too. So please check see if you can share your slides.
So I'm just going to share my entire desktop because I might have to.
Okay, that works.
Does it look right?
Yeah. Yeah, perfect.
Yeah, you can see it.
Yeah, works well. Yeah.
Great. I wasn't able to join yesterday because I was alone with the girls, but how did it go?
It's very good.
How many listeners did you have?
About 250 or something, was it at one point? Or maybe more at the beginning. Was it more, actually?
Yeah,
the
peak was 285.
285, yeah.
And towards the end of the day yesterday, I think it was around 164. So that's the range we did.
Brilliant.
But I think what is interesting about, we were just discussing the nature of this workshop, that people sort of pick up their topic of interest. People don't have to sit through the whole thing. So if you're in that city attending a workshop, you're sort of forced to go to talks, even if that's not really your main thing. But if you're at home, you can easily zoom out.
I can't decide whether that's good or bad. I think it's got a bit of both.
Yeah, I think
it's also good to be obliged to see things that are not directly just your interest. It's opening the mind to much more things. And
that is true.
The students, they have often the tendency to only look at what is exactly in their subject. And that, I think that's a wrong thing to do. I mean, you need to be exposed to other ways of thinking to, just to design to have new ideas. Otherwise, you're just mainstream and that's it.
Yeah, no, I think at the student level, at all level, we should be broader because things have changed so fast around us. We all have to. Yeah, so I think
going away somewhere also means I don't have to be at home with the kids. I can actually sit for 6 hours and either listen to a talk or do something, but concentrate.
Yeah, young parents have extra constraints at home for home meetings.
I think you guys know that very well.
Just getting out of that phase. Just coming out of it. All right, we are online on YouTube, so I'll send the link to everybody.
So Nuj, are you in your office?
Yes. I decided to come because my internet at home is 90-20, so 90-10. So I wanted to be 100%. But I took a picture. It's the first time ever. I've been at this university for 20 years. I have a picture of my car as the only car in the huge parking lot. It's the first time ever. It's a Saturday morning in a COVID semester. So first time, no problem parking.
So don't get
And also,
stuck in the elevator.
another reason to be in the office is internet. It's campus internet is so underused that it's all free. It's all available for you. Now, Ian, where are
I have a question for Zoom. Is there a way to admit everyone automatically?
to do what?
To admit the people automatically.
No.
Can we? No.
No. So the way it is, this is a Zoom account through our university, and we were told that if you have more than a certain number, then you have to screen people.
Oh, okay.
Now we may ignore that instruction, and maybe we can. Chao, can we do this automatically?
No, so usually if there's above 1,000, and then the university will just suggest us to do it by the webinar, or we can go to the YouTube. So
no, but let's say we are less than 1,000, and like today's meeting, can we make the entrance into the main room automatic rather than going to a waiting room?
Yes, we can.
Okay.
But if we do it in that way, if someone, some people, they make noise, and then we want to let them go, and then we will just leave the meeting, and they cannot put it in the waiting room.
Yeah, it's a safety issue. I mean, so it's advisable not to do it. But it is a sort of a pain to keep an eye on.
Yeah, it'd be so much worse if somebody came on and did something very spammy though and ruined it.
Yeah, that's why, and then you can't blame anybody because they'll say we told you so beforehand.
But although if they aren't able to actually speak or show their, well, I suppose people can show their video because we can see and hear people at the moment. So yeah.
There are plenty of ways to bomb this thing, so we can do what we can.
And avoid that if at all possible. Yeah.
Hey, Sebastian.
Hi, hi everyone.
Hi.
Are you in a church or something? Where are you?
No, OSU has these standard backgrounds that I downloaded, and this is one of them. I think it's like stained glass by the stadium.
Oh yeah, this is the other kind of church, the stadium. we have that too. We have I mean, I'm not kidding. We have the stained glass window with our coach, and that goes 4 stories high. And I'm told that's the largest stained glass portrait of a human being in this side of the country. And it has the feel of a church. You see this 4-story high stained glass.
That's
all right. So Sebastian, can you check your presentation and see?
Yeah. Is that okay?
Yep, just showed up.
Yeah.
Yeah. Cool.
Okay.
You're almost getting there.
I mean, I figured projecting this background is better than projecting the back of my basement. So those were the 2 choices. It's either this or.
I'm surprised. No, not. I would have been surprised. At first, I thought the university forced you to use this background.
No.
That would be something.
Usually, I did project just the back of my basement, but I figured for this meeting, I'll be a little bit fancy and have something else.
You're being broadcasted not only on YouTube, but on this thing called Bilibili, which is a YouTube of China. You may have a great visibility.
So does
So
that
do the
mean it's
best.
streamed there, or is it recorded?
It's live broadcast. It's recorded on Zoom. The talks are. not our chat.
Good to know.
Yes, it's important. Yeah, I should not have criticized my football coach. I would be in great trouble in the university.
It's a really bad move. Yeah.
Yeah.
I believe that portrait is of the former coach, though.
Oh yeah, that is Bobby Bowden. Yeah. That's the
But you can say anything you want now.
Yeah, and the new coaches haven't made it to any poster yet. We are bad. Our new coaches have been that bad. Nobody puts their picture anywhere. But Carlos, have you seen that thing? I mean, that 4-story. This is a huge stained glass picture.
Like
It
when
has a church. I mean, it beats Notre Dame in Paris.
Yeah. When I took a tour of FSU, that's pretty much the main thing they showed you, the stadium.
And you decided to come to FSU because of that?
Yeah, it was, it was the deciding factor, I guess.
Good to know.
I looked up that book by Ulf Grunander that someone recommended yesterday, and I guess it hasn't been in print in a long time, so it's on sale for like $300 to $400 online. The cheapest one I found was $250.
This one?
Yeah. Some people sell it for like $400, more than $400.
I'm surprised it's out of. The thing that I really wanted for our sort of research was his book called Abstract Inference, where he derived statistics for stochastic processes, which is very relevant for functional data analysis. And that book is not even available even as a used book anywhere. I've really searched for it. Now, he gave me an autographed copy when I was working with him, and I loaned it to somebody and it just disappeared. I never saw it again. And I really feel like that's a book that will be very relevant for our research right now. I mean, he wrote a lot about the operator theory, spectral representations, very classical theory for functional data. But if somebody has access to that book, I would be very eager to. I mean, I had it when I was not really prepared for it as a PhD student. Now I feel like. Hey, Derek.
Hey.
How are you?
Good. How are you?
Very good. Is it very early morning in New Mexico?
It's 7:10 in the morning. So yeah, I'm the only one up right now.
You and your horses.
Yeah, and the cows and everything else.
You have cows also now?
Yeah, we have over 200 acres we live on here. We're out in the middle of nowhere now.
You are out there, man.
Yeah, it's nice during a pandemic.
Yeah.
There's no one around you.
Are people trying to move into your ranch?
There's actually quite a bit of people moving out of Albuquerque up to this side, about 30 miles east, because it's rural and there's not many cases. So there's been a lot of housing is very a hot commodity right now out here.
Cool.
People are putting their house on the market and selling in like 12 to 24 hours.
Wow. You planned it well.
No, I should sell and move somewhere else, right?
Just sell it by the acre. You will you will just exponentially.
Yeah.
How are things at Sandia?
Good. Going good. Actually, we're doing some good things and research is good. There was broad interest in this workshop too. We sent it out lab wide, and there's actually a few people on yesterday, and there'll be some more on today. A couple people actually from another research team saw Sebastian's talk and are highly interested in what Sebastian's doing. So
cool, good to hear that.
I want to take the plenaries from yesterday, Rama's talk, and just like wave it around the lab. How we need to think about deep learning.
Yeah, it's good to have for beginners some entry points into deep learning world. I think we are coming up on starting time soon. Hey, Chow, can you make Scott a co-host? Acton?
Okay.
Thanks.
How are you, Scott?
Wonderful. Great day yesterday. Thank you.
I'm glad you think that. All set for this noon and 12:30 session?
For sure.
Are you all set for the 12:30? Okay, yeah, you said for sure. Okay.
Yep,
Good.
I'm ready.
Glad to have you in your multiple capacities. Image processing helps your research, and then at NSF.
Thanks. Should be fun today.
Yeah.
So you ready, Anuj?
Let's give it a minute or two because I see still people coming in. It's sort of the analog of people entering the morning session with their coffee mugs at the last minute. Person. Just give it a minute.
I think it's now bandwidth bucket, right?
Bandwidth bucket. Oh, yeah. Good to see you, Ranjan.
Yeah, I've been here. Yes, I was here all day yesterday also, but because of bandwidth, I keep my camera off.
Okay. Also, alphabetically, you have been moved down somewhere in this.
Yeah.
You should be.
I mean,
alphabetically, AA would be nice. All right, Ian. So let me just say welcome to everybody. Thanks for joining in. It was a great day. Lots of good feedback I got from people who both spoke and participated yesterday. I promise it will be equally exciting today, if not anymore. We have a fantastic lineup of speakers. So this morning's session chair is Professor Ian Dryden from Nottingham, Mr. Shape Analysis. So I'll hand over to Professor Dryden.
Thanks, Anuj. So yeah, welcome to the session on geometrical and topological statistics. Very exciting session with 4 great speakers. Before we start, I want to thank Anuj and all his colleagues at FSU for putting on this workshop. I think you've done a fantastic job. So it's been very easy as a co-organizer because I've essentially had to do almost nothing. So that's the best sort of organizing. So thanks very much, Anuj, and all your colleagues. First speaker we have is Javier Penic, and he's a senior research scientist at INRIA, Sophia Antipolis in France, and also at the University of Côte d'Azur. Javier is an expert on geometrical statistics for computational anatomy, and his work has really shaped the field for the past 25 years or so. So I'm very pleased that Javier is going to give the keynote lecture in this session. So.
Well, thank you very much. Thank you very much, Jan. That's a real pleasure to be there. Can you see my screen?
Coming up. Just say if you have any questions, please post them in the chat, and if there's time at the end, I'll read some out. But yeah, apologies if we don't get through them all. Okay, Javier. Yeah. Okay, so thank you very much, Jan and Anuj, for the organization. That workshop is fantastic. So my talk is geometric statistics for computational anatomy, and maybe I'm gonna start by the application domain, which is anatomy. So up to the 1980s, anatomy was basically, well, the main tool was dissection, and the goal was to represent one individual or the anatomy of one individual in detail so that we can extrapolate to other individuals. But in the 1980s, then there was the revolution of medical imaging, and we could observe basically in vivo and in situ, so we could observe many, many different anatomies. And then came the need for actually creating generative statistical models of the population. And that's where computational anatomy actually comes from. It's the idea that, well, we want to do statistics on shapes. Well, for the application will be for different organs. We want to know not only what is the mean shape, what are the normal variations, the pathological variations in the shape, also the evolution over time, either in growth or aging. And that's knowledge that we want to build. So computational anatomy is not about the results, but also about the methods to build with statistics. But the results of the statistics, then they can be used as a prior in some kind of Bayesian estimation framework for personalized medicine. So the idea is to make statistics on groups and then use that information to improve the diagnosis, the follow-up of specific patients. So here is an example of what we'd like to do. So these are surfaces of the right ventricle extracted in images of 18 subjects. And these subjects are kids, actually, ranging from age of 6 to, or even earlier, I think, to 16. And the idea is we would like to be able to model what is the variability there, but also what is the evolution over time. What's the mean model, and how is that shape changing with age? So one way to do that is to actually try to compute an atlas. So this would be the mean shape. So we are trying to have this shape, which is optimally centered, so that if we register it to each of the observations, then basically all the deformations sum up to 0, sum up in some sense that I will clarify later. So that the atlas here, the mean shape is basically the atlas is the mean shape, and the deformation encode the variability. This way of doing things is actually lifting the need for statistics on surfaces, on shapes, to Lie groups or groups of deformations. And so that gives the question of how to do correctly statistics on these type of spaces, Lie groups, groups of diffeomorphisms.
So in this, just to continue with this example, this is the mean anatomy that we have computed. And if we look at the different modes of variation that we can have, there's, well, with 10 modes, we encode quite a lot of variability. And if we look at what are the modes which are significantly correlated to, well, time, to the age. So here the surrogate variable is the body surface area, but that's basically a measure of age. Then we can select 6 modes, and then along these 6 modes, if we try to regress what is the evolution of the shape over time with respect to age or to body surface area, we see this type of evolution. And actually, this evolution can be interpreted here. That's one. It's not just figures or loadings. It's visual, and we can see that with the growth of the child, then the volume increase, and some of the valves actually are deforming, which have some impact. And each of these steps here of the interpretation was actually known in the literature, but independently. So here, just with this type of statistics, this is allowing to have some kind of insight, and because we can visualize what's happening, we can try to explain it better and to relate it to the literature. So more generally, what we like to do is what we have is different type of features. So this could be surfaces. So this is typically the right ventricle that we just seen, but we could work on the surface of the brain. We could work also on the tracts. So sets of lines extracted from diffusion transfer or diffusion MRI that actually encodes the pathway within the brain. So all these objects, these are objects that are actually non-Euclidean. They don't live in a Euclidean space. That doesn't really make sense to add 2 surfaces. Or what is the subtraction of a curve from another? It doesn't really make sense directly. So we need to revise the way we want to do, or we have to do our statistical modeling. And so the goal is really to do very simple statistics, but on objects which lives in nonlinear manifold. And by simple statistics, what I mean is computing the mean value, covariance, simple extension of PCA, or PLS, and things like that. So the talk will be essentially divided in 2 parts. The first part will be how to do statistics on Riemannian manifolds, and then I will try to convince you that it might be something even more general than Riemannian manifolds, which is affine collection spaces, which might be better shaped for transformation groups. Okay, so when we talk about nonlinear spaces, we need to define a little bit what it is. So the simplest space that we can deal with are flat spaces. That's Euclidean spaces. And then immediately after, we can think of the sphere or the hyperbolic space. These are very simple spaces. They are very useful. Spherical statistics are a well-established domain, and Jan is active in this part. But in general, it's a bit too constrained to contain our data. So we need something more. And we often look at homogeneous spaces, Lie group symmetric spaces. But the most general framework that is used right now is the one of Riemannian and affine connection space. And that's where I'm going to deal with. And I will stay in this talk in the category of smooth manifolds, although we are interested, and I think Urza will talk about that, about stratified spaces and spaces which are much more shaky than the smooth ones that I will talk about right now. Okay, so if we have a differential manifold, there are 2 basic ways of looking at that. So think of the surface of the Earth. You can look at it as some kind of a sphere embedded in the 3D space. So that's the embedding, the extrinsic point of view. Or we can look at charts, different charts here, and with a way to relate them with transition functions, then we can compute and do differentials in these different charts. So that's the 2 different ways, and they are actually, in finite dimension, they are equivalent. So it means that if we have a given atlas, we can find a way to embed that in a space if this space is sufficiently large. So the next question is how to measure things. We want to measure lengths, straight lines, volumes, things like that. So if I take this example of a very simple manifold, so it's basically a bump, I can have one global chart by projecting vertically. And now if I take one curve on this surface and measure the lengths in the embedding space or in the chart, obviously they are different. So if we want to have something which is consistent, then we need to come back to the basic tool to make measurements. And the basic tool is the dot product. So with the dot product, I can compute, if I have a vector in an embedding space, I can compute the norm of this vector. And by integrating the norm of the tangent vector to a curve, I can get the length of that curve. So now if I'm going to a manifold, and if I look at here, two orthonormal bases at different points, and I'm just projecting them in the chart, and what we see immediately is that they might not be orthonormal. So if we want to actually make measurements, then we need to remember that this is actually an orthonormal basis if we want to be consistent with the embedding space. So the key idea of Riemann was to revise the idea of the dot product and to say that the dot product, we need to specify it at each point. And here, specifying that this basis is orthonormal amounts to specify what is the matrix, the symmetric positive definite matrix that we need to put here in the dot product. And the dot product will change smoothly from one point to another. So it's now depending on the point. So here, if we have just one surface in an embedding space and we want to have the metric which is corresponding to the embedding metric in the chart, then we just need to project the embedding metric and look at what it is. Now, if we have several charts, then they need to be consistent. The metric need to be consistent. So a Riemannian manifold is something that where we can compute locally with the dot product. There are generalization with norms which do not come from a dot product. That's Finsler manifolds. There are other type of generalization, but the most simple one is Riemannian manifold. We have the dot product. We can compute the norm of a vector, and now again we can compute the length of a curve by integrating the norm of the tangent vector to the curve. And now if I'm integrating in the extrinsic, with the embedding space, or in the intrinsically within the chart, then I'm getting the same distance. I am again consistent. So with the length of a curve, what we can do is now given 2 points here and here, I can look at all the curves that go from the first point to the second one, and look at what are the curves that are minimizing the length. And this is what we call geodesics. So the shortest path between any 2 points. I will not enter into the details, but the Euler-Lagrange equation, the calculus of variation, shows us that these curves, they are solution of a second-order differential equation that actually specify the acceleration of the curve. So if the acceleration is specified, then there are three parameters. The first one is the point where we start the curve, and the second one is the tangent vector. And that's going to be the key to parameterize things in a Riemannian manifold. So these are the basic charts that we will use, which are the exp and log map. So the exponential is basically if I am at point x with this tangent vector, then by following the geodesic that start at this point with this tangent vector, what is the point that we arrive after a unit time? So that's going to be where a map sending the tangent space to the manifold. And the log, the inverse of the exponential, is basically unfolding or unrolling, if you wish, the manifold on the tangent space along geodesics. So if you take a geodesic and unroll, then the geodesic will become a straight line. But only the geodesic starting from the contact point here. The geodesic starting from other points will have a more complex behavior in the tangent space. But the key thing in the exponential and log map is that radially everything is consistent as if it was Euclidean. Now with these tools, the exponential and log, we can rephrase many of the algorithm that we use to compute. So for instance, if we take the subtraction, well, subtract 2 points, that's basically computing the vector that shoot from one point to the other. So this is exactly taking the log that allows you to shoot from x to y. So this is going to be the vector xy is going to be log x of y, and that's the vector that allows to shoot. Adding 2 vectors within a single tangent space, that makes sense. Now, adding a vector to a point, that can only be done if the vector has the foot at the given point. So if I have a vector in this tangent space, I cannot add it to y, to the point y here, but I can add it to x, and that's basically amount to compute the exponential, to compute the geodesic. So now with these 2 tools, then we can just rephrase, for instance, the distance. The norm of the difference between 2 points, that's going to be the norm at point x of the vector that shoots from x to y, that allows to shoot from x to y. Or we can write it also, and that's also the case, that the distance is, the Riemannian distance is the norm at y of the log y at x. So that's how we can rephrase many of the classical computations. Okay, now if we want to go to statistics, the first object that we usually use is the mean value. And the mean value is usually defined as an expectation, or this can be seen as an integral. Sometimes, so Fréchet first worked from a vector space to infinite dimensional vector space. And he first extended the definition of the integral to have the mean in these spaces. But then he realized that this was not working anymore for more complex spaces. So what he did was proposing to take a property as a definition. And he observed that the mean is minimizing the sum of square distance to the data points, or to the mean square deviation. And so he proposed to use that as the definition. So in a Euclidean space, that corresponds uniquely to the mean value, but in a manifold, then we may have several minima, and it is not so obvious to say when it is unique. So one of the key properties of this equation is that if we take the gradient of this equation, this is allowing us to characterize the critical points, and the critical points, they satisfy a barycentric equation, which is when you are at the mean point or any critical point, if you develop the distribution on the tangent space, then the expectation is 0 in that tangent space. And so that's going to be what we call exponential barycenters, and I will use that later. But this is a larger definition because we have not only the minima, but also the maxima and the local saddle points, the saddle points. Okay, so once we have the mean, then, and this is this first vector field, which is developing the distribution in the tangent space and integrating in the tangent space, taking the expectation in the tangent space. This is often called the tangent mean. This is giving a vector field, and the flow of that vector field is going to the Fréchet mean. So this is a way to compute actually the Fréchet mean. But once we have that, just to have the uniqueness, there are conditions. So in non-positively curved metric spaces, we know that the mean is always unique if it exists, so that everything is going well. But in positive curvature, then we need to have a sufficient concentration. So if the distribution is too dispersed on the manifold, then we might experience several local minima. But if we are sufficiently concentrated, then we can go one step further, and we can look at what is the law of generalization of the law of large numbers and the central limit theorem. And it turns out that that's resolved by Bhattacharya and Patron-Généraux. This is still holding, the CLT still holds. If we look at the expectation at the population mean, Fréchet mean, of the empirical mean taken with n samples, then this should go, and we weight by square root of n, then this should converge toward a Gaussian here. But the Gaussian has a modification with, classically it would be sigma here, but here there is a modification with this matrix H, which is the Hessian of or the inverse of the Hessian of the square distance. And so if we really want to understand what's the modification, then we need to understand what is that and how does it behave. And we have done such a work recently by proposing new Taylor expansions based on the curvature. And we have been able to prove that actually, if you take the expected Fréchet mean with n samples, it is a biased estimator of the population Fréchet mean, and the bias is in 1/n, and it's related to the gradient of the Riemannian curvature contracted with the covariance matrix. Now, if we look at the concentration of the expected Fréchet mean with n samples, that's going to be, as usual, the covariance matrix of the initial samples divided by n, but there is also a correction factor in 1/n, where we have the curvature appearing in the contracted with the covariance matrix. And this is an effect which is kind of new, but we can look at what it gives for in negative curvature. If we're concentrating the curvature, then we can go to an infinite convergence, an infinitely fast convergence. So it's actually something which might be explaining the stickiness in stratified spaces. And on the other side, on positively curved manifolds, the convergence is lower, and at the limit we might have behaviors where it does not converge in 1/n or in square root of n. And that's what has been described recently by stickiness. And this, we might already see these effects just with smooth manifolds. So this is something that is interesting, because it means that we always say that if there is a sufficient number of samples, then we can use the law of large numbers and everything looks like Euclidean. Yes, but maybe not at the speed that we expect. So what is a sufficiently large number? This is depending on the curvature, the gradient of the curvature in a manifold. So be careful in manifold learning, or when you're learning in manifold, the curvature might impact a lot your results, especially with small data. Okay, so beyond the mean value, we can go to PCA, so the principal component analysis. So one of the simplest way of doing PCA is tangent PCA. We compute the mean value, then we develop everything in the tangent space at the mean value. In that tangent space, we are in a vector space. The mean is 0. We can compute the covariance matrix and decompose it in eigenvectors, and that is giving us a subspace in which we can project the data. So if we look at what is the subspace that this generates on the manifold, this is what has been called the geodesic subspace. And then if it's working very well if it's highly concentrated. But then if the distribution is a bit more spread on the manifold with respect to the curvature, then other methods like geodesic PCA or principal geodesic analysis has been proposed. To PGA, for instance, is minimizing the sum of square of the residues to the subspace that is generated, and that's different than tangent PCA, which is maximizing the explained variance. And we can also generalize these geodesic subspaces by the Affine span of a number of points. And one of the interesting things about all these subspaces is that if you add components, they are embedded subspaces, properly embedded subspaces that describe larger and larger spaces. And one of the subjects on which I'm working is trying to describe PCA as a search or as an optimization in the manifold of flags. Flags are exactly sequences of properly nested subspaces. And actually, we were able to show that PCA is optimizing a specific criterion on the flag manifold. And that's a way to generalize PCA also to manifolds. Okay, I'm just going to take one simple example of tangent PCA to illustrate things. So this is a database of radiographs where we have scoliotic 300 scoliotic patients. We have frontal and lateral radiographs. On these radiographs, the clinicians pointed very precisely some points so that they could be we could reconstruct their coordinates in 3D and know what is the position and orientation of each of the vertebra in the 3D space. So originally they directly tried to do some PCA on the points position, but then, as you imagine, if you are with a scoliosis, then you can have quite a large motion, and so the PCA is not really doing a good job. So here what we proposed is instead to consider that this is an articulated object, and what we are interested in is actually the articulation between vertebrae. So what we want to encode is the difference of what is the translation and rotation between two neighboring vertebrae. And that is an encoding of an object which is actually living in a rigid body transformation to the power 16 here, for one for each articulation. And if we put the left invariant metric on that, and we do statistics on this set of 300 spines, this is the mean spine shape that we find, and we see that there is a small right scoliosis here. Maybe there are more right scoliosis than left scoliosis, like right-handed people versus left-handed. But what's more interesting are the modes of variation. So the first mode, so here we see it from the front, is basically linked to growth. And that's normal because we did not, on purpose, normalize with the scale. So we can see the growth of the child, and we can see that with the growth there is an increase of the scoliosis, and that's normal. It's about 1 degree per year if nothing is done. The second and third mode, they are actually the free modes of vibration of a rope. So that's a natural basis to describe changes of shape of the spine. And the fourth mode here, we can't see much in this frontal view, but if we go to the lateral view, this is the lordosis. This is the angle here at the bottom of the spine, and this is something that is going to increase, especially in elderly people. And with this description, we were able to predict actually the clinical classification. So this is just an example where, by taking our samples, or by putting them in a space which is adapted to what we want to describe, an articulated object here, then we can end up with statistics which are more meaningful than just standard PCA on points. Okay, now the second part of this talk is how can we extend the setting to transformation groups. In particular, if I take the example that I shown at the beginning, we have an atlas, and we're registering with diffeomorphisms to each of the observation. We want to shift or to lift the statistical analysis to the transformation group. So what is a transformation group? That's in finite dimension what we call the Lie group. It's basically a smooth manifold with a composition and an inversion operation. And these two operations should be smooth with respect to the structure that we choose. So we have a group on one side, we have a Riemannian metric on the other side, and we put both together. Now, if we want to have some invariance properties, then we should decide if we're invariant on the left action, so composition by a fixed element on the left, or right action. And in general, there are many as many left invariant metric that we want. We choose a metric at the identity, and then we propagate it at every point, or we propagate it by right translation. But having both left and right translation is much more difficult, and it's actually only working for abelian groups or compact groups. So in general, if we go to even rigid body transformation, there is no bi-invariant transformation. So it means that if I'm taking a set of transformation, the mean of the inverse will not be the inverse of the mean. So we're not fully consistent with the group operations. So one of the questions is, can we design a natural structure where the statistics would be fully consistent with the group operation? The second aspect, which is of interest for us, is the analysis of longitudinal deformation, and this will involve prior transport. So let's assume that we have patient with Alzheimer's disease, for instance, and we have observation over time of patient A here, And because Alzheimer is basically something where the brain is deforming over time, we could think of modeling that with a geodesic in a space of diffeomorphisms. So let's assume that we can have we can regress a geodesic here. We can regress a geodesic here for another subject. These geodesics, they are parameterized by their initial tangent vector. But the initial tangent vector here is related to this anatomy and here to this anatomy. And we need to actually transport this deformation from the patient to the template. And to do that, we need another tool, which is called, in differential geometry, parallel transport. So that's one of the questions. How can we design parallel transport methods that are stable? And in the end, what we want is to be able to, of course, parallel transport all the deformation that we measure on subjects and be able to do statistics at the group, at the population level, to have a deformation, a trajectory over time that we can either apply to the template here, and that's the evolution that we can see, or to the different subjects. Okay, so I need just, in this slide, just there is one idea. If we want to have a mathematical basis, good mathematical basis, in Lie groups, there is one specific curve that is in, or one set of curve, which is interesting, which are one parameter subgroups. So the idea is, if I take a tangent vector at the identity and I left translate it, I have a vector field and I can take the flow of that vector field. And if I integrate up to time one, I'm ending up somewhere in the group, and that's what we call the group exponential. So this is not exactly the same as the Riemannian exponential, but this is exactly the same idea. Locally, it's a one-to-one mapping between the tangent space and the manifold, at least in finite dimension. And so if I have a tangent vector at the identity, I can compute, and I choose a metric, I can compute the left invariant geodesic, the right invariant geodesic, and the one parameter subgroup. Two of the three curves are geodesics. Can we put a structure so that the one parameter subgroup is also a geodesic? And the answer is yes, but we should revise a little bit what is the notion of geodesics. So previously, geodesics were length minimizing curves, but I also said that actually the equation of the geodesic is specifying the acceleration. And here the idea is we're going to say that a geodesic is a curve with no acceleration. So in that case, we need just one thing we need to be able to compute the acceleration. So if we want to compute the difference between this tangent vector, this speed, and the speed just at time t plus delta t, these vectors, they are actually belonging to different tangent spaces. So what we need is a way to actually project one tangent space to the neighboring tangent spaces. And this is exactly what is called the connection. If you just take a linear way to encode this mapping, that's what is called a linear connection. And so now the geodesics.
Left, Javier.
Sorry?
About 10 minutes left.
Yeah, okay. So with this definition of geodesics, we still have an equation which is actually exactly the same as before. We have a second order differential equation. So it means that we still have exponential and log formulas as before, but they are only local. So we can continue to work with expand log map. And if we take on Lie groups, if we take, there is actually one special connection, which is called the Cartan-Schouten connection, which is left and right invariant. It's symmetric in the sense that it has no torsion, and its geodesic starting from identity are the one parameter subgroups. So in matrix Lie groups, it means that the matrix exponential will be encoding geodesic starting from identity. And the geodesics at every other point, they will be written by the left or the right multiplication by another matrix. In spaces of diffeomorphism, we are going to parameterize the diffeomorphism. The one parameter subgroup will be obtained as the flow of stationary velocity fields. And that's a framework which is very efficient because we can continue to do some statistics. Obviously, we cannot use the mean value with the Fréchet mean as before because we don't have a length. But if we take the critical points of the variance, this was a barycentric equation of that type, and that continued to be feasible in our affine connection spaces. So we can still define mean value with exponential barycenters. There is local uniqueness in certain convexity conditions, and we can continue to compute covariance matrices and things like that. One thing we cannot do is just diagonalize this covariance matrix to have a PCA, for instance, because the basis in an affine space is not defined. If I'm changing the basis, I'm changing the covariance matrix. But if we are taking the law of large number, CLT, Malanobis distance, everything continues to hold. Okay, for diffeomorphism, what it gives is basically encoding, taking a stationary velocity field, and if we take the flow, then we obtain a diffeomorphism. One of the key issues is that we have with that very efficient numerical algorithm, like the scaling and squaring, which is allowing to compute the exponential in log n step with respect to classical geodesics, where you need n steps. And we have also the BCH formula, which is allowing us to do some approximation for gradient descent. So this is what is at the heart of some of the registration algorithm that we have designed over the last 10 years or a bit more. The idea is if I've got two images, I want to find what is the velocity field along which I should flow the first image to resemble the second image. And that optimization framework is using a lot of the symmetries of the stationary velocity field framework. And that's the log demons algorithm that in particular Marco Lorenzi has developed. So now if we have sets of images, and if I'm coming back to Alzheimer's disease with different longitudinal sets of images, we have one registration algorithm. For each registration, we have a geodesic parameterized by the initial tangent vector. So if we have several images, then we can set up a geodesic regression scheme, which is quite easy to fit as much as we can, as best as we can, the whole sequence of images. And now what we're missing is just parallel transport to be able to actually transport the trajectories from one subject to another. And for that, we first looked at numerical schemes proposed in astrophysics by doing some kind of geodesic parallelograms and compiling them in ladders to actually do the parallel transport. And then we realized that we can actually do something simpler, where we have, if we're parallel transporting along a geodesic, and we call that pole ladder because it, with the different steps of the ladder, is resembling a ladder in some bolts. And recently, what we were able to actually explicitly compute the numerical accuracy of that scheme. And we were expecting it to be of order 2, and it turns out that it's very efficient because it's of order 4. And it's actually even exact in only one step if we are in a symmetric space. And the structure that we put on the Lie group, this is exactly a symmetric space structure. So we can have the parallel transport in only one step along a geodesic. And Nicolas Guigui just generalized that to other numerical scheme. And even if the geodesic in a general space is not known and you have to integrate it, then we can still have a quadratically convergent scheme to approximate the parallel transport, and it's more stable than the classical schemes. So this is the results that it gives on a set of Alzheimer people. We took 2 images, 1 image apart on 70 people. So we have 70 tangent vector to the longitudinal geodesics that are parallel transported to the atlas. And then we compute the mean of this trajectory and extrapolate that, multiply by 15. So when you do some image registration, you know that if you multiply the deformation by 2, usually everything breaks down. Here we multiply by 15, and it still looks like a young brain going to a very old Alzheimer brain. And from that, we can continue to make some statistical analysis to see what is the difference between this would be the stationary velocity field for normal aging, and this is what needs to be added for Alzheimer's disease, and we see that there is a very strong component here around the hippocampi, and we can try to design to see what are the differences, and we could put into evidence even these differences in the normal subgroup of the ADNI database between the one that are A-beta positive, so they are at risk for Alzheimer, versus A-beta negative. And this is, so this was not, with just volume measurements, this was not possible before. Okay, so to conclude, well, I hope that I have shown that EXP and LogMap in Riemannian affine manifolds are the good tool to generalize many of the simple statistics. We have also efficient discrete parallel transport. We can continue also to generalize that to manifold value image processing. But in practice, if we want to implement things, then we need to put all that into a software box, and that's what we're trying to do on an initiative of Nina Mjolan. We have started 2 years ago the GeomStat library in Python, where we now have more than 15 manifolds with mean, PCA, clustering, parallel transport algorithm implemented, and there are about 15 to 20 people participating. So if you're interested, just go and look at that. And just to conclude on more open questions. So now what I've shown here is what's happening for very regular spaces, smooth Riemannian spaces, and a bit affine spaces, but still smooth. So one of the key questions is how to go to stratified spaces, what's happening in quotient spaces, and can we generalize or geometrize statistics? So what is the influence of curvature? One thing we have also issued recently with Peter Mikor and Stefan Sommer and Philip Harms is a study of what is the space of samples. If you take samples in a manifold, well, they actually live in a manifold which can be seen as a stratified boundary of the manifold of smooth probability densities. And that way we can revise, for instance, the Fréchet mean as a projection on a specific stratum on the boundary of the space of probability density. So it's a new look at statistics as geometric projection. So just to finish, I'd like to thank many of the collaborators from which I stole many of the images and illustration of that talk, and just signal that there was a book that is out this year on Riemannian geometric statistics with application to medical image analysis. And so if you're interested, many of the things that I've touched in that talk are better explained in that book, and I encourage you to have a look if you're interested. I think I finished there.
Excellent. Thanks very much. That's really good. So we have time for maybe one question, if there is one. I think in the chat people are being polite and not put anything in yet, but don't hesitate to put in a question. And even if we can't read them out, we can make sure Javier gets them. So,
can I, Ian, since I have the luxury of being loud here, can I just ask a quick question? Xavier, I mean, excellent talk. This is, as usual, you continue, you're marching along, which is fantastic. The question that you also do a lot of practical work. You develop this theory and you do a lot of practice. So the question from a practical point of view is, you have these curvature calculations, which are a beast, which are difficult for manifolds that we are getting into nowadays. So when is it, for a given data set, do we have tests? Can we test this hypothesis that curvature makes a difference? You made a remark, if you have a small sample and if the data is spread out, curvature will make a difference. But for a practitioner, when is it that tangent PCA is good enough and that's it? Or when is it that you need to go into your Cartan connections to really do things correctly?
Well, I think it's a difficult question. There is one thing that is continuing to work in in manifolds, it's a bootstrap. So if you have a sample, and that's the way I actually verified the Taylor expansion that I've shown, at least for the coherence matrix, the way it concentrates, and to show that it's actually concentrating at a lower speed than what we would expect in a Euclidean space on the sphere. I have tests where you just take a sample on the sphere, and then you bootstrap to do many samples to see what would be the coherence matrix that you would expect. And you can compute it actually here by bootstrap. So this is a very expensive way of doing things. But actually, already 20 years ago, when we were discussing the uniqueness of the atlas, has it converged, or is it sufficiently well centered? One of the answer was, if you start the estimation of your atlas from different points, and if they all end up sufficiently close to each other, then it means that you have converged. And this is basically the same type of test that we can do to do things. Now, the beast of the curvature, I tend to consider up to very recently that it was actually a beast that was preventing to do many things. But actually, many of the manifolds that we're looking at, they are quotient spaces. And if you take Riemannian summation, we have formulas to compute the curvature. So this is something that is, if we start with a simple space and quotient, then there is a canonical way of computing the curvature. The formulas are there. They are just unbeatable, well, unreadable, but we can program them. And that's one of the things that we're going to try in the future in the library. Maybe this is the way to add second order estimation just by having this quotient structure. And this is actually exactly the way to compute the curvature on Kendall-shaped spaces. The work of Remodeling is by going through these formulas. And instead of writing them down explicitly, which is, I agree with you, a beast, we can compute it exactly with the same formula, but automatically. So it's kind of like the revolution of automatic gradient, automatic differentiation. It might be automatic curvature computations if we start from a simple space.
Good.
Okay, thank you.
Yeah, I'm just going to ask a very quick question, if I may. So your barycentric subspace analysis, looking at different dimensional subspaces to summarize data, is principal nested spheres a special case of that, or not? Or
so not directly. I mean, if you take yeah, well, yes and no. If you take great subspheres, that would be a case. So what I believe, but it's still a conjecture. What I believe is that if you take very special case where you have points which, well, limits of points coalescing in certain direction, we could generate not great subspheres, but lower dimensional or small subspheres. And in that case, that would be a general case. So I think there is a relationship, but here it's algebraic geometry, and I'm not really good at that. So there's room for other people to show it.
No, that's very good. Well, thanks very much indeed for an excellent talk. Thank you.
Well, thank you for the invitation.
Sorry. So Åsa is next. Do you want to share your screen?
Yes, let's see.
All right, so Åsa Fréchet is a professor at the Technical University of Denmark in the Department of Applied Maths and Computer Science. Åsa is an expert on trees, graphs, topology, and works a lot in medical imaging and machine learning too. So looking forward to your talk, Åsa.
Thank you very much. I'd like to start by thanking the organizers for inviting me. This is a really nice program that you put together. So I've been really looking forward to this for a long time. And also thanks for the very professional setup with everything online and so many listeners. It's really nice. This talk is in collaboration with Anna Calisano and Simone Vantini from Politecnico Milano. This is Anna's PhD work, and we have two papers. One is a preprint, another is in preparation, but will soon be a preprint too. So you'll be able to find these from my webpage, the first one already, the second one soon. And these form the basis of Anna's thesis, which she handed in about a month ago. So most of what I'll be saying today, if I happen to see something smart, it's probably due to Anna. If I say something stupid, it's probably due to me. I'll start out by trying to convince you that graphs are everywhere. So in the examples here on top, you see an example from computer vision where a network encodes as nodes different objects and as edges their relation or their spatial arrangement. You see a couple of examples from bioinformatics and chemoinformatics where they represent protein structure or chemical structure. We have a mobility example up here that's been at the heart of Anna's work. We have some medical imaging examples, an airway tree or a brain connectivity network, and also a social network over here. Graphs can have different numbers of nodes, as you see in these different subway maps here. You can have different edges between those nodes, and you can have different types of attributes on the nodes and edges, such as either categorical labels, such as the name of a subway station, or vectors, for instance, encoding the length of a connection or the coordinates of a node. So we're looking for some sort of a setup or a framework that can handle graphs of such different structures. In Anna's work, we've considered a space of graphs that's been around for a while. So the earliest account that I know is from Brinesh Jain with a paper in JMLR 2019. He called them structure spaces, and they could also encode more general structures than graphs, but here we're interested in the special case of graphs. And here graphs are represented by their adjacency matrices. So for instance, a graph like this one, if you number its nodes, 1, 2, 3, 4, then you can write up its adjacency matrix like this. And that adjacency matrix lives in Rn plus n, or n times n. Now, the numbering that I gave this graph was completely random. So by changing this numbering of nodes, you get multiple representations of that same adjacency matrix. If I number it differently here, you can see my adjacency matrix changes accordingly. So if I want to have a unified or a coherent description of these graphs, I need to consider all different representations of the same graph as being one single object. And the way to do that mathematically is by considering this node permutation group, which is precisely what I'm using when I renumber these nodes. I apply a permutation of the node labels, meaning a permutation of the node rows and columns in the matrix. And then I mod this thing out. So what I get as an object in here is an equivalence class consisting of all the different representations of a single graph. And I consider that set the graph itself. So elements of this quotient space are graphs. Graph space is this quotient space. And inside the space of adjacency matrices, I will find the orbits of these permutation matrix consisting of all the different representations I can get of one graph by permuting the nodes in this representation here. Now, within this framework, it's easy to accommodate graphs with different numbers of nodes. If you have a graph with 3 nodes and another one with 4, you simply add a dummy node with no attributes, no edges. It's also easy to extend to vector valued nodes and edge attributes. So if you want to encode edge weights, well, you do that by having numbers in your adjacency matrix. And if you want vector valued attributes on nodes and edges, well, you just, instead of using scalar values inside your adjacency matrix, you put a vector at every location. You can even have different dimensional attributes on nodes and edges if you like. It just makes this a little more complicated. Now, quite a bit of work has been done on doing statistics within this space. Jain himself did quite a bit of machine learning back in almost 10 years ago. And more recently, there's some work coming out of one of Anusha's PhD students, and also out of Kolashik's and Rosenberg's and Lin in Boston as far. And there may be other work that I'm not familiar with, but certainly these two work in the same space of graphs. Now, we've been looking a bit at the geometry of this graph space and what some of the consequences of that geometry is. So this graph space, like I said before, is a quotient space where I have this group, and I'll call it T to be consistent with the notation in Giants papers, although this is really just the permutation group. Now, I have this total space. This is a space of adjacency matrices, and I factor out this group of permutations in order to get graph space, which is the quotient here. This projection from adjacency matrix to the equivalence class of all these matrices, I call that projection pi. Now, this graph space here, it inherits a metric from the Euclidean metric up here, because remember, if I have scalar attributes on my edges and nodes, this graph space really is just this space. And if I had vector valued attributes, well, there's just an additional D. So this up here is Euclidean. And this graph space is a geodesic metric space. Any 2 points can be joined by a shortest path. And this total space up here, you can think of it as sort of a tangent space because, well, if I pick my favorite graph down here and I pick a representative of that graph, I can find the permutation of nodes that brings, any representation of this other graph as close as possible to this one up in this total space. Now that permutation is going to give me the distance that is precisely the same as the intrinsic distance inside the quotient space. So this is a property that is very similar to what you see in tangent spaces with X-band log maps. So if I pick a base point, for instance, a mean or some favorite graph that I have, and I pick a representative of it up here, and then I align all my other graphs to it, then this is going to be very similar to what you do when you are projecting your data onto the tangent space in a manifold statistics setting. So this finding an optimal permutation, you can think of it as an analog of having a log map in a manifold setting. Now, one of the things we found was that geodesics in this graph space are not necessarily unique. And here's a toy example that will illustrate this. So if you look at these two graphs, y epsilon and z epsilon, I've encoded in color when edges have the same value and when nodes have the same value. And red consists a little plus something small, and blue encodes minus something small. Now, if I want to find the geodesic from this point to this one, then I have two options. So either I use the matching that is indicated by the planar embedding, matching this edge to this one to this one. In that case, I have to interpolate my node attributes. So I get this thing here as the midpoint of that geodesic. Alternatively, I can swap the two edges and map this node, the red node up here, to the red node down here, and map the blue node to the blue node. In that case, I end up interpolating my edge attributes, giving me the midpoint that I see here. Now, these are two different paths. We can show they are the shortest possible paths you have between those. So in other words, geodesics are not necessarily unique within the space, and the curvature of graph space is thereby unbounded from above, because if it had been bounded, then we would be able to find unique geodesics at every point if we were sufficiently close to it. So this is why I have the small epsilon here. Now, setting that epsilon to 0 gives me a point and a particular point in graph space, and adding these epsilons, tiny epsilons, is going to bring me infinitely close or arbitrarily close to that one point. And arbitrarily close to that one point, I'll have these two graphs that can always be joined by two geodesics. So there is at least one point in graph space where arbitrarily close to that point, I will not have unique geodesics. And that means my curvature cannot be bounded from above. Now, this is annoying primarily because I cannot be sure to have these unique geodesics even locally. And that is going to give me some consequences for the statistics I can do, and at least for the proofs that I can do. just a brief remark, this counterexample is not depending on having node attributes. So you might look at this and say, well, you know, if I only have edge attributes and my nodes have fixed value or no values at all, maybe this doesn't happen. But unfortunately, it does. I can just replace this node here by having an edge with similar properties. So yeah, what does this mean for statistics? Let's start by looking at the mean. So just like in Xavier's very nice talk, we can define Fréchet means also within this space as the minimizer of sum of square distances to your other data points. Now, because geodesics are not generally unique, Fréchet means are also not generally unique. In particular, these two midpoints of geodesics between z epsilon and y epsilon are means of the set of those two single points there. So the set of z epsilon and y epsilon has two Fréchet means, this one and this one. Well, okay, so they're not unique. The same thing holds on the sphere, so maybe that's not so problematic. So let's just consider the Fréchet mean to be the set of such minimizers and move on. That's also useful. Well, the next issue we had was looking into trying to compute at least one of these means. And the first thing we looked at was one of the most common algorithms used within manifolds and other stratified spaces of non-positive curvature for computing means. And this is what you might call an iterative weighted midpoint algorithm or a stochastic gradient descent algorithm on manifolds. It's a very simple algorithm. It consists of first sampling one point and then another, moving 1/2 along the geodesic between them, then sampling a third point, moving 1/3 along that geodesic, then sampling a fourth point, moving 1/4 along that geodesic, etc. Now, if you're working within non-positively curved spaces, you'll know this as Sturm's algorithm, and it's guaranteed to converge to your actual mean. And Xavier has looked at the same algorithm within Riemannian manifolds and proven similar convergence properties. But as far as I know, these proofs on convergence usually require you to be able to work within a neighborhood where your geodesics are unique. So usually you ask that your curvature is bounded. And because of this, we were at least not able to prove that this actually converges to a mean in our graph space. So we went with a different strategy, which is more similar to generalized Procustus analysis. And this is a strategy that we're also going to use for other statistics. So we decided to call it line-order compute because that's essentially what we do. So we start out with our graphs, and for every graph, we pick some representative of it inside this space of adjacency matrices, and we compute the mean of those. And then we align all our graphs to that computed mean. And in some cases, that means I have to pick a new representative that is closer to it. So I get a new set. And now I compute the mean of those representatives. And again, I align all my points to my new mean, get a new set, compute the mean of those, and keep going until convergence. Now, in this case, we can guarantee that you converge to a local minimum of the Fréchet function in finite time for a generic data set. Unfortunately, we can only guarantee converging to a local minimum, and I'm not sure whether it's possible to show that it's global. Either way, just to show you some qualitative examples, for a data set consisting of handwritten letters A, we obtain a mean that looks like this, so at least it looks reasonably normal. And for a set of mobility networks from the Lombardia region, where we're looking at 4 different modes of transportation, rail, bus, bike, and private car, we obtain the following Fréchet means for the different modes. So you can see at least those means, they resemble the data sets and they at least look like Fréchet means, so nothing standing out so far. Now, in order to move beyond Fréchet means, we'd like to compute some higher order statistics. And one way you could do this is utilizing the fact that this space of adjacency matrices acts a bit like a tangent space. So you could align all your points with your favorite points, such as the Fréchet mean, and perform statistics on those aligned points. And this is similar to what Guo and Srivastava and Sarkar do in their tangent space. Well, they don't call it tangent space PCA. That's what I call it. But but I think it's a nice analogy for understanding what is going on. Now, if your data set is very spread out, then you risk, however, that some of the points that are farther away from the mean, that their residuals to the principal components become incorrect because you align them to the mean and not to the principal component. So just like tangent space methods in manifold statistics, you risk having some distortion if your data is not very localized. So you risk having distorted residuals when you move away from the base point. And this is usually the motivation for trying to do intrinsic statistics. And this is what Anna's work has revolved around. So we denote our data as a set of graphs living in this graph space. And we're optimizing over generalized geodesics within this graph space. They are projections of geodesics in the space of adjacencies and matrices. And our task is to find one of these generalized geodesics that minimizes the sum of squared residuals, that is the distance between the actual data point and its projection onto this generalized geodesic. So that is essentially what we're drawing here. Now, using this analogy with the Procrustes analysis, we make a very similar algorithm that we call now align and compute, that essentially consists of iteratively aligning the data to the computed statistics, recomputing the statistics, aligning, recomputing, just like you do in generalized Procrustes analysis. And again, just like before, or just like with the mean, we can show that within finite time, this algorithm converges to a local minimum of the function we are trying to optimize. And now the crucial thing in order to get that is that when we align our data points to the statistics, so to the principal component in this case, we are minimizing precisely the same residual as we do when we are fitting the statistic. And that is why this works. So looking at a few examples again, so with the handwritten letters A, well, the first principal component seems to be capturing some tilting. Oh. And you can see it in particular both on this, what do you call it, the horizontal stroke, but also in the general shape of the letter. The second principal component captures something similar, but a bit more similar to rotation, really. So you have this more of a rotation going on. And well, the third principal component seems to be capturing some strange shape effects. Looking at a similar example with the mobility networks, well, if you take a look at the data, you'll see, well, in the middle of the night, there's certainly less traffic, and in particular for bike and also for rail and bus, you can see that there's considerable less activity than at other times of day, whereas the private car stays relatively fixed. Now, that's interesting because we can see the same thing within the principal component, and the first one captures quite a lot of the variability here. So you can see for the bike, it really gets, that's where it's most clear that it's capturing a very large difference in activity. And you can also see it more vaguely in the bus and rail, whereas the private car stays pretty much fixed the whole time.
10 minutes left.
Thank you. Now I also have a third example, and I'm calling it preliminary because Anna sent it to me yesterday. So I might not be completely exact on exactly what's going on here, but we're looking at networks of, this is like social networks of baboons. So baboons like to groom each other by, I don't know if they're picking insects or what they are doing, but they are interacting. And this interaction somehow reflects the social hierarchy within a group of baboons. And this is a nice example because it shows how, even though, you know, one baboon is always the same baboon, it might have different roles in the social network. So it really makes sense to model this network of baboons without putting labels on the baboons, because the baboon that is an alpha male today may be tomorrow's beta male or vice versa. So these are naturally unlabeled networks. Now, and Anna sent me a very nice movie that I'm hoping I can play for you. I hope you can see this. So in the first principal component, we see that the network is becoming denser. And in particular, we see that that it's primarily becoming denser within this small cluster, and then you have these two very isolated nodes that become slowly more connected with the rest. Whereas in the second principal component, well, it's similar, but it's somehow less disconnected. And I'll admit I haven't had that much to look at this, but so I'm not exactly sure how these two are different, but they are both clearly capturing increased density in the networks. And just visually, it seems like it's happening in slightly different ways. So this is why I stuck preliminary on there. Next time you hear me talking about this, I can probably say something more clever about how those two are different. But it's a nice example because it very naturally shows how, this unlabeled nature of the network is very natural. I'll move to our final paper, which has to do with graph-valued regression models. So these are regression models where we are trying to predict a network. Now, again, our data consists of, well, it consists of inputs, which are considered to be Euclidean, but then the outputs live in this graph space. And again, we are optimizing over models, which are projections of nice, so to say, well-known models in the space of adjacency matrices. And in this case, we are looking at linear regression models. So in principle, you could have nonlinear basis function, but we are looking at linear combinations of those. So classical linear regression models. And the task again is to describe the relationship that minimizes the sum of squared residuals. And note that we are really looking at the differences between data points and predictions. So we no longer have perpendicular projections onto this statistic. We are looking at the difference between the prediction and the actual graph. And the algorithm again is similar as before. We alternate between aligning our data to a model and re-optimizing the model or refitting the model. And just as before, we can show that this algorithm converges to a local minimum of the sum of squared residuals in finite time. And again, the trick is again that when we realign to the model, we are minimizing the precise same residual as when we are fitting the model. And that is again why it works. So in our first example, we will look at correlation networks where we are looking at correlations between 9 different cryptocurrencies. And in particular, so our data set starts when Bitcoin emerges in 2010. And in particular, you can see that, well, in 2010, we only have Bitcoin. So our graphs there are very simple. And then throughout time, we keep having, or we get more and more of these different networks. And the task is to predict what this correlation network looks like over time. And again, we are treating this as unlabeled networks because just like with the baboons, these cryptocurrencies can play different roles in the correlation network at different times. And we have 2 different visualizations here. So up here, we view an adjacency matrix visualization of the result where we've aligned the predicted to the true value. And below, you see a network representation of the same. And I think they are both nice because, well, it becomes very clear from the adjacency matrix that we're really predicting something that's very close to the truth, but at the same time, the graph structure is easier to see from the network embedding. The second and before I move to the second example, I just want to make the remark that we can really see that we need to have these multiple iterations of the algorithm because the residuals or the sum of square residuals is going down, not just in the first iteration, but also over the next few iterations. We don't need that many iterations in this example, but we do need more than one. Another example comes from mobility, which is close to Anna's heart. Here we are looking at public transport in Copenhagen. And this is in collaboration with Movia, which is the bus company in Copenhagen. What you see over on the left-hand side is different bus stops. And on the right-hand side, you can see the areas of Copenhagen that we have aggregated these bus stops into. So everything blue over here, for instance, belongs to this area, and we aggregate that into a single node. Now, we looked at these graphs through a period that contains some time before the COVID-19 lockdown in Denmark in March. And then we also have graphs from within the COVID lockdown, and also from the time where we started to reopen again at the end of April. What you just see here is the within area fluxes, or I believe a prediction of the within area fluxes, when you are just looking at this in a completely standard way, you know, with aligning the nodes that correspond to the same regions. So this is completely standard analysis. And what you can see from this is just that, you know, before the lockdown, there's a lot of traffic and more in some areas than others. I would like to just point out these two regions here that I will return to later. They are residential areas. I live up here. Then in the lockdown, you can see everything is dead. And after the lockdown, when it's slowly starting to open again, you can see slightly similar, well, you can see similar patterns as to before the lockdown, but with a lot less activity. And if we do a regression analysis, keeping the nodes associated with, or, you know, keeping the node labels on, so these are labeled graphs, well, you can see again the same thing. There's more activity before, and you see the old pattern sort of re-emerging weekly after the lockdown. But if we remove the node labels and start treating these as unlabeled networks, then we effectively allow different nodes in this network to have different roles at different times. So, you know, the place where I live can have one role at one time and another role at another time in terms of global network topology. And you can really see that the network structure is different during the lockdown. So if you just view this as a transportation network with no information about where the different nodes are and which ones match, you can really see there's a difference. And this is the interesting part, in my opinion. If you look at which nodes are swapped with each other when you start moving through time, well, what we're showing here is the most popular node matchings with intra-by. So this is the inner city as a function of time. And before the lockdown, it has a very special function in the network. It's a hub. It's where everyone goes in order to go somewhere else. And it's never matched to anything else. It's very unique. But during the lockdown, and this was why I was pointing out these areas to you, it starts to be matched with these residential areas. I mean, this is where I live. And I live a very boring life, and so does everyone else living here. So you can see that this inner city, it really started to act very differently in terms of its role in the network during the COVID-19 lockdown. And the moment Denmark opened up just a tiny bit, it got its old role back again. And we just thought this was a nice thing to see as to how these are different modeling choices that you do. Do you want to just keep your node labels and only consider how the same connection changes over time, or do you want to look at how they play a role in the global network structure? And you can do both. Now, just a brief discussion. We've been doing statistics within this graph space where the total space is Euclidean, meaning that generalizing Euclidean methods becomes easier than you would otherwise expect. And this approach with, we call it the line and compute, it's essentially a generalization of Procrustes analysis. It allows us to do intrinsic statistics while retaining the computational advantages of Euclidean statistics. But there are limitations, as always, and I think the worst one is that our distances and our matchings are NP complete because graph matching is NP complete. And that means what we'll do is necessarily going to be approximations in order to be able to do something. Now, in the paper by Guo et al., there's a nice comparison of different matching heuristics for this. if anyone is interested in that.
I think we'll have to begin to wrap up now, actually. Yeah,
yes.
Sorry. Yeah.
Very quickly. The graph space is highly non-Euclidean. It's likely to affect statistics. We don't yet know how. And one problem that we have is that because we are interpolating in our statistics, many of our statistics end up having a complete matrix structure, even though our data matrices do not. And that's another open problem. That's all I have. Thank you very much.
Thanks very much indeed. Thank you. Excellent. Thanks very much for the excellent talk. We have got a question which I think you've already answered, which is about the geodesic computation being NP complete, which you actually had on the last slide. So I don't know whether you want to say something about the approximation.
If I want to say something about it?
Yeah, yeah.
Well, I mean, so there are lots of heuristics for graph matching, and there's usually a correlation between quality and speed. Well, a negative correlation. So, I mean, depending on your problem, pick the one you think is best and maybe utilize whatever structure there is in your problem, and it can get better. Our examples are not that big, and that's also because we've been using off-the-shelf matching algorithms.
So how many nodes could you go to, do you think? That's another question we have.
So we haven't, I think we've gone, I mean, we've used graphs with like 20 for sure. And I know Anna is having some students implement C++ code that should be able to go much higher. But we haven't looked at anything much bigger than that.
So yeah, tens rather than thousands.
Yeah, and I mean, you could go higher if you are willing to lower your quality on the matching.
Okay, I think we'll better proceed. So thanks very much for your excellent talk.
Thank you.
Can I just, I think it's wonderful talk, Usa. I mean, I like everything you said. We do the similar things, but this graph matching problem is the real problem. I think that's a lot of other mathematics just falls into places when smart people look at it, and that will be fine. So I think there is a great opportunity to collect with decades of work on graph matching. You know, they never thought about geodesics. This is our thing, but there's tremendous amount of work, and something, just a little plug here in what we are doing is, I mean, we can work with 10,000 nodes, but the idea is to somehow have a multispectral representation of a graph where you sort of zoom through the resolution. You can come down on resolution, you can go back up on the resolution, and you can try to solve these registration problems at a lower resolution, and then sort of iteratively build them up. And so the things we are doing where we actually have shapes of the edges, so we call them graph shapes, which is even bigger complicated issue, because now you have non-Euclidean edge attributes, because the shapes are now attributes. So I think there is a very great potential of building this up, bringing tools from very diverse disciplines that have looked at these things in the past. And ultimately, I mean, I have felt this for the last 5 years, 10 years, is matching, graph matching, that's the problem. And it's good that people are pointing this out, but there are solutions available by sort of going to lower resolutions, solving the problem there, moving that solution, propagating it back up in the more resolution space. So just like we do for image representation.
If I may just quickly add to that, I mean, in algorithmics, people put a lot of attention on handling worst case problems, right? But most of our problems are based on real data. Usually we don't have worst cases. So I think there's also possibilities for getting more speed just on looking at what does data typically look like.
Well, I think in the interest of time, we must move on, but there are a couple more questions. So I don't know whether you want to, from Ranjan and Derek, I don't know whether you want to answer them in the chat or perhaps send them an email or something. So can you see them? Can you see the chat? So we're ready, Moo?
Oh, yeah, I am actually. Let me share the screen.
I'll send them to you if you can't see them.
Are you talking to me?
Yes. Can you see them?
I can just answer in the chat. It's okay.
Okay, yeah.
I can't
All
see
right.
them.
Thank you very much. Yeah, thanks. That's great.
Thank you.
Oh. Right.
So
I'll introduce you. Yeah.
Okay.
So
Sure.
very pleased to welcome Mu Chung. He's an associate professor of biostatistics and medical informatics at the University of Wisconsin-Madison. Mu is an expert on computational anatomy, shape analysis, topological data analysis, and medical image analysis. So thanks very much.
Okay. Thank you, organizer, for this great workshop, actually. And I'll talk about the topology learning for brain networks. And this is a joint work with the PhD student Tan Song. I hope he's here. If you have any question, you can just type your question to the chat, and if Tan is here, he will answer the question. He was working very late. We have a paper deadline, so he was working. I don't know if he's here actually. Anyway, okay. Before I started, I have one advertisement. We actually organizing a workshop. It's a satellite meeting for OHBM. I was organizing this with the Korean local organizers, but due to Corona, it's going to a Zoom meeting. My sessions are completely booked. So if you want to join, give a talk, you need to bug either Beans or Martin or Anchi, I guess. This talk is basically motivated by two great paper. One is Anuji's paper on graph matching. Before he worked on the elastic graph matching, he was working on a tree data. So I know he was working on this for many years. Then this Stephen Maron's paper, Gaussian homology paper on a brain tree in analysis of applied statistics. It's a very good paper. And so when I saw these two great people working on this tree data, I felt that I should also work on this problem. So I spent 2 years to collect the data, process data, and we actually published paper. Sorry, something went to. Let me see. Sorry, something went actually wrong. So we actually did a circle tree. It's a tree actually you can obtain from the brain surface mesh and published paper. The way we actually did it was that we approached the problem as a geometric problem. So we basically did the heat corner smoothing on the trees and just do the voxel-based morphometry type of the very simple morphometric analysis. The problem is that we are able to detect gender differences, male and female, but we are not able to detect much finer signal. It's a genetic signal. So we are not able to discriminate the MG twin and DG twins. So we realized that we need a matching because if you treat this as a geometric problem, all you can do is a diffeomorphic shape model. Diffeomorphic regression basically assume continuity. While this is tree, you cannot match it with a geometric regression. So we need more discrete approaches. So that's why we are doing topology. So let's. So
do you want to share the full screen or sorry, the
oh,
slideshow?
sorry.
Slideshow. So it's probably a bit easier to read.
So we actually wrote a paper. Tan actually wrote a paper in archive, so you can read it. It's a 42-page paper with lengthy, but we did a lot of validation. And these are all my collaborators who, I have so many people who helped me on the project. And by the way, I'm actually looking for another postdoc. So if you're interested, you can apply the position with me. So the data is coming from restricted fMRI. So we have it's basically time series at each voxel position. So we have about 300,000 voxel position, and it's MG twin. So basically, you will have now. This is the example of the fMRI at every 30 seconds. So see the differences here. It's a resting state, so you're not going to see much differences, but still it's fluctuating over time. It's dynamic. So what we do is what we can do is that we can actually do the correlation of the whole time point, and to construct a single gigantic correlation graph. You don't want to do this with your computer; it will crash your computer. You need the specialized hardware. So actually, I don't know. I actually waste time doing with the GPU. I don't know why it wasted anyway. So this paper, we actually quantify the cycles, number of cycles, for example. And the problem with the complete graph is that, especially that comes from correlation matrix, is that you're going to have a lot of cycles. So it's a functional network is characterized by the cycles, while we have another data, it's a DTR. We'll obtain the structural network, which will be characterized by the trees, actually. So you can have a diffusion tensors. Then you can have this kind of tractography, 1 million tracks. And I'm bringing up this old paper because we did something that's relevant to this talk. So we use topology. It's epsilon neighbor point set topology. It's a simple stuff. Then we actually constructed the network without pixelation. It's pixelation free. Also, it's multi-scale. So you can build a network in any scale you wanted. And now the conclusion of this paper is that it's basically structural network is basically a single gigantic component that looks like a tree. I mean, there's some cycle, but the number of cycles is far less than the functional network, which is coming from the correlation network. So we have two networks. One functional, that's a lot of cycles. The other network, structure, that's like tree-like. So topology would be totally different between the two networks. So if you simply superimpose two networks and try to do the regression model, I don't think that will work. I mean, you can do it, and you can get the signal. However, I don't think that's the proper way to do this kind of the network modeling. Now, this basically we are dealing with a lot of data, like billion connections. So we need some sort of the data rejection, but to do that, we need to know the scale of the data. So this with a 3mm resolution, it's coming from fMRI. We will have about 0.67 billion connections. That's a lot of connections. So you can have this kind of the network at the voxel level. And that requires about 5 gigabytes RAM memory. Now, if you want to increase the resolution to 1mm, you will have 90 billion connections. And it's 700 gigabytes of memory. So what the biology people, neuroscience people did was that they come up with this biological data reduction. So instead of doing this, building a network at the voxel level, we're going to build a network by parcellating brain into about 100 regions. And make it very sparse and make it very simple. So this structural connectivity matrix is characterized by 116 symmetric matrix. And then for functional network, you can do the same thing. And so your first attempt might be trying to overlay this and try to do the regression at the edge level. That's what everybody does it, but that's not a good approach. Why? Parcellation boundary doesn't overlap actually across the subject modality. Simply trying to match and do the data analysis at the edge level, it will get the job done. However, I don't see that's the optimal way of doing it. So that's why so many people come up with so many parcellations. You have to understand this field to understand the problem actually. I mean, because there's a problem with the parcellation, because the way doing this kind of brain network modeling is not optimal. So they realize it. So each time, every day, they come up with a new parcellation. I don't think that's the way to go. So let's do something very different. Okay? Forget about this kind of parcellation-based network modeling. We're gonna build a mathematics that will basically map the one network to another. So I got the idea from the Diffeomorphometry shape model, like Mike Miller's group's kind of the shape model, where we have a template. Instead of doing that, why don't we build a template, network template, and the rest of all the network to the template, and do the data just like a Diffeomorphometry shape. So instead of Diffeomorphometry shape, we're gonna do a Diffeomorphometry network. That's the idea. So this requires basically graph matching. Anuj talk about the importance of graph matching. So that's the idea we're gonna do. So we're gonna project the map functional network to the structural network like this. So this is formulation time came over. This is not my formulation. It's a Tan's formulation, Tan's formula. And so basically we have a goodness bit term. And then we also have the topological loss. It's a topological penalty. So if you increase the lambda, we will increase the topological closeness. If we don't have if lambda equal to 0, basically it's just geometric term, Province norm. So that's how we do it. So lambda about 100 will exactly match the topology of this graph to the topology of this template. 100%, I can guarantee you. So let's do Gaussian homology. This is a research topic I've been working for almost 10 years now. So let me go over the basics on the graph filtration. This is a concept my former postdoc, Dr. Lee, introduced to the field. This is baseline methodology and baseline terminology now. Anyone doing the Gaussian homology and brain network modeling basically use this graph filtration. There's nothing new. It's very simple concept. Even high school students will understand it. So the way we do is that the filtration is an algebraic object that has nested structure. So in a graph filtration, what we do is that we basically delete the one edge at a time. And so now, so we delete the edge to, let me see whether I can have a, let me see, I can have a pen. So this is a deletion of this edge, deletion of this, deletion of this. So we are keep deleting the edges in the increasing order. That's what the graph filtration is. And how many cycles in this graph? Well, some people may say there are 3, but actually there are only 2 graphs, 2 cycles actually. 1, 2, and what about the big cycle? Well, that big cycle is a linear combination of these 2 cycles. So it's actually for vector space. That's the essence of the Gaussian homology. Gaussian homology is about the vector space of the topology. We are not just building some topological features or some graph features. We are building a vector space. So if you have a vector space, you can do a lot of things. You can do the pre-analysis basically. So that's why if you want to, you can build a sparse model on this because it's a vector space. Okay? So this vector is characterized 2 bits. So it's Betty 0 and Betty 1. Betty 0 is basically count the number of connected component, and Betty 1 basically count the number of cycles. And they are bases. We are basically counting number of bases. That's what this thing does. Now, in this paper, we actually shown the monotonicity. This is only increasing or decreasing monotonically. It will never fluctuate like this. And if you have a monotone function, most of the functional data analysis people will know that it's very easy to align the data and do the data analysis. So it makes things very simple, very stable. So then what the Tan did was that he figured out that some sort of decomposition on this graph iteration. So he figured out that what edges will destroy the cycle, what edges will create the component. So these blue edges are basically destroying the cycle of a graph iteration, and these red edges are basically creating a component node, basically creating node. So you can tabulate the lifetime, which is like the death subtract by birth. It's called the persistence and the Poisson homology, and it will give you exactly the. Now, it's actually starting from minus infinity because cycles are born. I mean, even at that point here, there's already cycle. So you can think about this as a lifetime of the cycle to be from minus infinity to all the way to the 0.3. And you don't want to handle with the infinity. So you usually match it to the some like value 0. Same thing with the lifetime of the node or connected component. So its starting point would be, the birth point would be here, and the death time would be infinity, but you don't want to worry about the infinity. So you basically match it to the last value, edge value. So you have an interval, and this interval is called the barcode. And the Poisson homology is all about analyzing this barcode. And so I would say, I have to say it's Tan's theorem number 1. And so he actually, there are only 2 cases. So you can actually decompose edge weight into either E0 or E1. That's only 2 cases. And how you constructed this to identify the edges that create component, it's actually maximum spanning tree. It is a maximum spanning tree. So so it's a maximum spanning tree plus something else, and that will give you the actual original graph. That's you can read the proof in the paper, in the archive paper. So with that tool, with this kind of the algebraic representation, we're gonna do the registration, graph registration or graph matching. So we have this, so we need to build some penalty or distance. So based on this decomposition of the zero-dimensional topology and one-dimensional topology, obviously we can actually separate the cost function into these 2. And so the zero-dimensional topology loss would be the minimum of the all possible bijection between the birth point to the another birth point. And this will be coming from here, and this will be coming from here. Same thing with this. Now you do this with the bijection on that point. And the next theorem the Tan did was that this is amazing. People may know this if you worked on I think this is known result in the mathematics. However, you may not know this if you never worked on this. That's the minimum of this bijection can be, usually you have to use the Hungarian algorithm, brute force approach for doing an optimization, but you don't need to do it. It's already given. The proof can be done in an induction. Tan did it in a paper. So you only need to match smallest birth value to the smallest birth value. Same thing with this, smallest death value to the smallest death value. So optimal graph matching problem, we reduce it into sorting problem. Sorting problem is n log n algorithm. You can apply this method to billion node if you wanted. As long as you sort the data in your computer, you can apply this method. This is a graph match.
Roughly, slightly less than 10 minutes to go.
Okay. I'm sure I can finish it.
Yeah.
So I want to emphasize the importance of these scalable approaches. This algorithm, even if you have astronomical data, we can apply. Size doesn't matter. As long as you can sort the data, you can do the graph matching. Idea is just so elegant, actually. I don't know why no one actually thought about this, actually. So I'm going to show you the example of how you're going to do the graph matching. I have this kind of graph here. And I'm going to match it. So the number of nodes is different. Topology is different. The first graph has 2 cycles. The next graph has only 1 cycle. Now, how we do is that we're going to do the trans decomposition. So it's MST, maximum spanning tree. So I identify maximum spanning tree. I also identify maximum spanning tree here. Then I'm going to sort the edges. So I have a sorted edge. I'm going to sort the edges. Now I'm going to simply map it, smallest edge to smallest edge. Then the remaining edge left, that should be matched to here, to minimize the cost function. Same thing with this. I'm going to match it, smallest to smallest, smallest to smallest, smallest to smallest. Then this edge is remaining. That should be matched to the last edge value to minimize the cost function. That's it. That's the idea of and we claim that will preserve topology perfectly. And with this technology, I'm not sure whether there's such concept as a topology mean. Well, it's again trans construct. So we can actually do it's like very similar to Fréchet mean. Fréchet mean is defined this way with different cost function. Now, again, you don't need to do optimization. You only need to sorting. So you sort the both and data values and match them and average. Basically, we are doing an averaging on all the statistics. That's what we do. Then based on this, we can do the averaging. And then the next thing Tan did is learning framework. It's a regression framework, but once you know how to we do regression, clustering and deep learning should be obvious. It should be obvious. So we're going to only show the regression setting. And so regression will be done. It's basically minimization. Now, thing about this is that you basically have to optimize this cost function. So you may think about gradient descent. So we do gradient descent by sorting. So we call it topology gradient descent. Nice thing is that we have the gradient, the derivative is exactly given this way. Everything is linear actually here. So you only need to figure out the sorting. So we're gonna do the optimization gradient descent by sorting. That's it. And runtime is exactly n log n. And whenever you deal with the matrix and the graph, n log n algorithm is possibly the best possible way you're gonna go through. So we also worry about the optimal parameter selection. It seems like if you look at the optimal parameter for every possible subject, it's very stable. Think of it, standard deviation 0.00012 is like almost no numerical error. So I don't know what's going on. Actually, I'm still trying to figure it out. My guess is that topological approach is so stable, you don't have much variability. So you can do at the group level by adding more. And this is group level learning. So group level. So this is functional network here, and this is structural network. So if you go in here, my functional network will be deformed into more close to the structural network. And eventually, all the topology matches. So it's 100% matching in terms of topology. It's a topology equivalent. So we did an extensive validation study. Now, in this kind of almost impossible to see simulation. So we generate basically 10 networks and 10 networks, this kind of thing, and try to do the two sample comparison setting, whether to see whether methodology will actually detect differentiate the networks of the different topology. So we come up with a new test statistic. So it's between rows, class rows, using topology rows, within class rows, and form the ratio statistic. Now, so this is our runtime. It's essentially flat. Our runtime is flat compared to the older graph matching algorithm. I don't even know what all this graph matching algorithm is. Tan is saying it's all the state out of methodology in computer vision. At least I know this one. It's just spectral matching. It's basically matching the eigenvalues. That's I know. And think about it. It's 100 seconds. While our method is best. Now you don't want to apply permutation test. One permutation will be more than 100 seconds. Then if you want 100,000 permutation, that's 100 days. Do you want to do the permutation test for 100 days? You don't want to do it. So we got the kind of bottleneck where our method works perfectly fine. The problem is we cannot compare with the existing methodology because the existing method is so slow. So we came up with, it's a method we actually developed last year. It's a random iteration method. It's a way to speed up the permutation test by doing a slow random walk. Permutation test is basically random walk in a space of the permutation group. Now the idea is that like this: if you just instead of swapping half of data to the other half, we're gonna only swap one data, subject 2 and subject 3, then only figure out what's changed there. You don't need to compute all the test statistics in a brute force fashion. You only need to figure out how much is changed. It's what we call the online learning and computer science. So we are basically using the idea of online learning with the permutation and drastically speed up the computation. That's how we did the validation. And so this is performance. It's always it's p-value, average p-value. Smaller p-value is an indication of the good performance. In this case, most of the graph matching algorithms are not performing well. It's expected. If you look at this data, simulation data, where you almost not able to see any pattern there, it's expected graph matching algorithm will not perform well. While our methods is really nailing down the topology. So we're able to do this kind of well, basically it's original Pearson correlation, while this is a TANS methodology. It's actually essentially amplifying the signal. That's the message. We want to take it. So what next? Well, the TAN is working on extending this framework to the dynamic data. So it's what we call the dynamic topological data analysis. Okay. And
right.
Yeah, I want to show the. Yeah. I'm done.
Okay then. Well, thanks very much. Thanks. Excellent. So we're a bit short of time, so we might have to move on. I'll just ask one question. Is that especially with the parcels, you know the labeling. You don't need to do any graph matching, do you? In those cases?
No, I think about it. These parcellation boundaries are not necessarily. I mean, that's what the biology people do. They use a fixed parcellation, but your parcellation should be different from my parcellation.
Yeah, so there could be some room for, yeah.
Yeah, so it's simply matching the network to another network at edge level. Is starting with already noisy data.
Yeah, but then they wouldn't be too far out in the wrong place. So, they'd be more or less, they'd be in the right area. Yes. So, maybe you want to relax it a bit, but not, not just overall permutations. That could limit the problem a lot. Yeah.
Oh, that's why we have this premise norm. It concerns the geometry, with the goodness bit term. So you cannot do this with just the graph topological cost function. You need to have the goodness bit term with the topology. You have to modulate.
Yeah. Well, thanks very much indeed. Yeah, thanks. So if there's any other questions for Mu, please do put them in the chat. Sebastian, are you ready?
Yes.
Okay, thank you.
Can you see my screen?
Yes. So so thanks, Mu. Now we've got Sebastian for the last talk of the session. Sebastian's associate professor in the Department of Statistics at Ohio State University, and he's an expert on statistical shape analysis, especially curves and surfaces, and also in image analysis more generally. So thanks, Sebastian.
Thank you, Ian, for the nice introduction. Thanks to the organizers for inviting me to speak, and also for putting together. Enjoyed all the talks so far. So this talk is based on recent work that was done with my PhD student, Xiaohan Guo, and my collaborator that I've been collaborating with for quite a while now, Karthik Bharat, who is at University of Nottingham. So in this talk, I'm going to talk about univariate functional data that exhibits phase variation and is spatially indexed. So that's sort of this first point that I highlighted, and we'll be interested in spatial prediction and clustering and this type of, so the methods that we developed have various applications in environmetrics, medical imaging, and so on. Connecting these methods or the general area to imaging, there are many other ways that spatial functional data comes about. For example, we can think of shapes of curves or shapes of surfaces in images where the image coordinates provide the spatial locations. One can also think in terms of marked point processes where we have a point process on a spatial domain, and then the marks are actually geometric objects. So things like shapes, functions, or trees, networks, any of those things. So here are just a few examples of the type of data that we're interested in. I'll come back to the example of daily ozone data in Northern California. I'll show that as one example of applying our approach. But one can also think about EEG data, cells in histopathology images, where we see sort of on the left is the actual image, and then the segmentation of the cells provides us with outlines of the cells in the image, and one can think of locations of the cells in this image as the spatial coordinates. Okay, so the main contribution here will be the definition of trace variograms for functional data. And this functional data will be unique in the sense that it exhibits two sources of variation, amplitude and phase variation, which I'll show you what I mean by those in a minute. So just to give you a little idea about what's in the literature right now for trace variograms defined for functional data, Narini et al. Applied multivariate spatial statistics after dimension reduction. So first the dimension is reduced, and then sort of fairly standard multivariate spatial statistics are applied. Giraldo et al. Defined an L2 metric based trace variogram for functional data, which was later applied for spatial prediction and clustering, which are the two tasks that we'll consider here. And then there are many extensions that later relaxed some of the assumptions that were made in the previous methods. One thing that's common across a lot of these methods is that the current trace variogram based approaches either assume that the given functions are perfectly aligned, or they indirectly treat phase variation as negligible noise. And so this is one of the drawbacks that we try to address with the proposed approach. Okay, so I want to start by giving sort of the standard definitions that are already in the literature of for variograms. So if we assume that we have a second order stationary and isotropic random field, which sort of at the top I'm denoting by Z sub S. S is a location in some spatial domain. Then this standard definition of the variogram is given here. It's a function of the distance h on the domain, which usually is just the Euclidean distance. And then this definition can be extended to second order stationary isotropic functional random fields, which I'm denoting by F sub S, where essentially the variogram is written down as the expectation of the L2 norm of the difference between two spatially indexed functions. So these variograms, they're very useful statistics when analyzing spatial data, because they capture the amount of spatial dependence in the random field. And in fact, they can play a key role in spatial prediction and clustering, as I'll show you in a little bit. Okay, so what are the contributions of our work? Essentially, we define different notions of the trace variogram for amplitude and phase components. So for the amplitude trace variogram, we use the spatial domain as is, but complications arise when trying to define the trace variogram for phase, because phase actually is a relative concept. It's not the same as amplitude. So instead, we modify the spatial domain where we actually augmented using the shape of the observed functions as a covariate. So this, the motivation for this is that, in fact, the relative nature of phase depends on the shape of the functions that are observed. Based on this the notion of the amplitude trace variogram, we propose an algorithm to compute a spatially weighted mean, and this mean, in fact, acts as a spatial prediction of amplitude, as will be seen later. And the last thing that we do is we use the amplitude and phase trace variograms to define hierarchical clustering that takes spatial information into account. Okay, so here's what I mean by amplitude and phase components of functional data. So there's no spatial information here. Suppose we observe original data that's given in the left panel here. We can notice two different types of variability. The first type is vertical variability. So essentially this is the vertical variability once the functions are aligned in some way. And the second source of variability, which is what we're calling phase, is purely in the x direction. So essentially this encodes the timing of features on these functions. So while the traditional methods for analyzing spatial functional data work directly with original data as given here, we will try to separate the definitions of the trace variogram into amplitude and phase components, and then use those separately for prediction and clustering. Okay, so let me start with a few preliminaries, because I'll use this notation throughout my talk. We start with a function space F. We assume that the domain of the function is 0, 1, but that's not necessary. The phase component is an element of this gamma, which essentially are mappings from the domain to itself, and these are direction preserving mappings. Function warping then can be thought of as the function coming from F, composed with one of these phase components, which is just this function gamma. To harness nice properties of this, what I'm calling the elastic functional data analysis framework, which was developed by Anuj and Eric Klassen, instead of working on the original function space, we'll actually transform everything into the space of squared slope functions. And so this transformation is given here. It's a simple transformation, but the nice thing that happens is that the L2 metric on the SRSF space is invariant to warping, which is a desirable property in the framework. So function warping on the original function space is just given by composition. When we move to the SRSF space, we compose Q with some warping function gamma or some phase gamma, and then we have this extra factor, which is sort of the derivative of gamma. Okay, under this framework, we can think of amplitude as the orbit or equivalence class of F under warping, or equivalently, we can think in the SRSF space as the equivalence class of Q, which are all possible warpings of Q. So these sets of definitions allow us to define multiple different distances that we'll use later on. So the amplitude distance essentially takes the inf over the set of phase components. And so what it does is it actually aligns Q2 with respect to Q1. And so one can think of the optimal phase as the relative phase of Q2 with respect to Q1. Another useful quantity will be the shape distance. And the shape distance is very similar to the amplitude distance, except we also remove the scale of the functions. So instead of computing the amplitude distance for the original functions Q1, Q2, we compute it for the normalized squared slope functions. And then finally, in our definitions of the phase variogram, we don't work directly on the space gamma, but we also take the square root slope transformation. This puts our phase component on the positive ortho of the unit Hilbert sphere, and we can compute sort of intrinsic distances on that space and extrinsic distances on that space. Okay, so now let me jump directly into the definitions of the trace variograms that we developed. We start with a functional random field, F sub S, where S again is our coordinates on our spatial domain. And we're actually going to think in terms of the transformed spatial random field. So we'll think in terms of QS, and again, S is just some coordinates on the spatial domain. The observed spatial functional data will be denoted by Q sub SI. And actually for simplicity, from now on, I'll drop sort of this SI notation. I'll just call it QI, where SI are just some locations, again, on the domain of interest. So the amplitude trace variogram is defined entirely in terms of the square root slope functions. And to account for phase variability in the functional data, we've attached these phase components in the definition of the trace variogram. For the phase trace variogram, as I said before, we augment the domain to include shape information for the functions. And so instead of working with the sort of pure spatial distance that's given here, we actually take a combination of the spatial distance and the shape distance that we defined, and the shape distance is weighted by a tuning parameter omega that can be estimated through cross-validation. And then given this definition of the new, what I'm still calling spatial distance, which it's not exactly the spatial distance, but given this new definition of the distance on the augmented domain, we can define, the phase trace variogram as essentially the expected value of the norm squared between the square root slope transformed phase components. Okay, so given these definitions, the next goal is to use them for spatial prediction or kriging, and then also for clustering. So let me start with the spatial prediction problem. Suppose that we're given data or pairs SIQI, so these are pairs of a location in our spatial domain SI, and then some function observed at that location. And what we want to do is we want to estimate first the amplitude component, which I'm denoting by Q0 gamma 0 here, at some new location in the spatial domain S0. And so the key idea here will be to define a spatially weighted amplitude estimator that will serve the dual purpose of a local template for alignment, and then also as an estimate of the amplitude component. And so as you see in our linear estimator of amplitude, right, this is essentially a weighted combination of warped original data. And so to actually compute this estimate, we need to also estimate the warping functions. And then there's a question of which template should be used for the warping functions. And essentially what we'll do is we'll use the template that's given by the spatially weighted mean. So the estimation of amplitude will be defined, as you'll see on the next slide, through an iterative algorithm that will iterate between two steps. One step will be to align to the current estimate of amplitude. And then the second step will be to re-estimate the amplitude using this linear estimator. This linear estimator minimizes the expected amplitude prediction error functional. And in fact, these optimal, the weights, eta I, can be estimated solely using the plug-in estimate of the amplitude trace variogram, which is given here. Again, the key point here is that to actually compute this V hat A, this amplitude trace variogram, what we need to do is we need to also estimate the warping, the phase components of Qi and Qj, which are given by gamma hat I, gamma hat j. Okay, so to sort of the full estimation procedure is given in this algorithm. As a first step, we initialize our template or our amplitude prediction with the function that's that has the closest spatial location to the location where we want to predict as 0. And then we repeat the following steps until essentially we reach some small tolerance epsilon. The first step is to align all of the observed functions with respect to the current estimate of the spatial amplitude component. And so this is just done using the amplitude distance that I defined previously. Then using these estimates of the phase component, we compute the amplitude trace variogram as defined on the previous slide. And then using this trace variogram, we can estimate the weights eta I, and then update our template to Q tilde 0. And so once we update the template, the alignments change. So we go back to the previous step. We align again, we re-estimate, and we just keep doing that until convergence. One thing that the algorithm also results in at the end are the optimal relative phases of each of the functions with respect to the spatial amplitude prediction that we get at the end from the algorithm. Without going into too much detail, these optimal relative phases can be used in similar fashion to estimate the phase prediction. Except in this case, there's no need for an iterative algorithm because we don't sort of have to estimate two things at the same time. So once we have the optimal phase, the optimal relative phases, we can just use those directly. And essentially the procedure for producing the spatial phase prediction is just a one-step procedure where we estimate the phase trace variogram, then use that to estimate the weights in the linear estimator for phase, and that's it.
You've got about 10 minutes.
Thank you. Okay, so how do we arrive at the final prediction? So from this, we can get a prediction of the amplitude component and a prediction of the phase component. The final spatial prediction will combine these two components. And not only that, but when we move to the SRSF space, I didn't mention that before, but we lose translation of the functions. So in fact, we have to predict function translation as well. Once we have these three predictions, we combine them and get the final prediction. Okay, so just to mention a little bit about the properties of the algorithm and how these different things are computed. So if we assume a simple model, so essentially the model considers only scaling of functions. So it's a very simple model. And if we have some additional conditions, we can show that the amplitude estimator computed using the algorithm I presented converges to the correct element of, so to an element, not the correct element, but to an element of the correct orbit as the number of observations in the neighborhood of the new location keeps growing. So as the number of observations goes to infinity. The other two things that that we've shown, and this is how we estimate the weights in the linear estimator, is that minimizing the amplitude or phase prediction errors is actually equivalent to minimizing a quadratic form. And this quadratic form only involves the weights that we want to estimate and the trace variogram, either the amplitude trace variogram or the phase trace variogram. And so this makes the estimation procedure fairly efficient because it's easy to estimate these weights. Okay, so let me show you a few results. So without going into too many details about the simulation setup that we conducted, this is showing predictions, spatial predictions for 3 different locations. In each case, the black function is the true function that we want to predict. The red function uses sort of the standard approach where we use the L2 metric based trace variogram without decomposing amplitude and phase. And then the blue function is the prediction given by our approach. And so especially in these first 2 panels, it's clear that sort of the approach that we propose often recovers features of the true function much better. So it actually recovers this peak and valley, whereas the standard approach has trouble doing that. And this is due to the phase variation that's in the original data. We applied this to the daily ozone data I already showed you. This is sort of in a small region in Northern California. What we did was we applied leave one out cross-validation for this daily ozone data, and we evaluated our method and then also the L2 metric based trace variogram approach that's already in the literature. And we evaluated that using 3 different error metrics. The first 3 metrics measure sort of pure amplitude errors in different ways. The 4th metric measures the phase error, and then the last one is just the mean squared error between the true functions and the predictions. And so it's maybe not surprising that we outperform the L2 metric based method on the sort of amplitude and phase errors, since we decompose and so we sort of gain that freedom. But what's a little bit surprising is that we slightly outperform the standard approach also under the L2 metric, which is what's used to optimize, which is that's the metric that's used to define the minimal prediction error for that approach. Okay, shifting focus to hierarchical clustering. sort of the standard way to do sort of spatially weighted hierarchical clustering in the literature is to combine the distance on the objects of interest with weights that come from the variograms. And so our distance matrix at the end that will feed into hierarchical clustering is just a weighted version of either the amplitude distance weighted by the amplitude variogram or the intrinsic phase distance weighted by the phase trace variogram. Now, the estimates of amplitude and phase trace variograms here are a little bit different, especially in the case of the amplitude trace variogram, mainly because this is a pairwise procedure. So in fact, in this case, there's no need to compute relative phases for all of the data with respect to a single component. Here, we just consider them pairwise using the amplitude distance. Okay, so we evaluated this new approach of hierarchical clustering using two different designs. The first design sort of has a regular grid of locations, and the partitions, the clustering partitions for amplitude and phase agree. So the amplitude and phase partitions are exactly the same for the two components. In the disagree design, the cluster partitions do not agree. And so this is sort of the more challenging case. So here's a single result based on, again, simulated data. In general, the proposed spatially weighted clustering using separate amplitude and phase components performs quite well. It can actually identify the two different clusters, the two different clustering patterns for amplitude and phase. As expected, the L2 metric based approach, since it doesn't decompose into amplitude and phase, it has to compromise between the two. So when sort of the spatial dependence is much stronger in the amplitude component, it will try to reflect the clustering from amplitude. When it's stronger in the phase component, it will do the other one. But usually it's some combination of the two. Again, we evaluated using sort of many repetitions for these two different settings. We used the RAND index as an evaluation metric, and in general, the method that we proposed did better than the standard method. So here is an application of this to real data. This is fairly standard data that's in the FDA package in R. This is daily temperature data averaged over these years here. This data was recorded at 35 stations in Canada. And so in this case, we'll try to apply our spatial clustering framework to this data set. Now, as a pre-processing step, since this spatial domain is very, very large, we first remove the latitude and longitude trends from the data, and then we cluster whatever's remaining, so these residuals. So here's the L2 based clustering. I mean, the main sort of strange thing that happens here is that Vancouver and Victoria are clustered together with Resolute, which is sort of way on the opposite northern end, which doesn't look exactly right. I think the main benefit of doing separate amplitude and phase clustering is that we can discover patterns based on these two components separately. And so we can discover patterns that are due to sort of the Y variation in the data, and we can also discover different patterns that are related to the X variation in the data. And so, oh, sorry, I'm almost done, in fact. So in the middle of Canada here, the two partitions that we get for amplitude and phase largely agree. We don't sort of have this strange clustering of Resolute with some of the other functions in either amplitude or phase. And for phase, interestingly, we get sort of a finer partition here where we split up some of these functions into separate clusters, which doesn't happen for amplitude. Okay, that's essentially all I have, and I'm happy to take any questions, and I hope I left some time for questions.
Thank you very much.
I see there are a lot of things in the chat, so.
Yeah, so we have a question in the chat. Do you know of any statistics to measure spatial autocorrelation in the case of functional data? Right.
So.
Spatial autocorrelation. Yeah.
Yeah, I'm not sure actually, but that's certainly that's a good question.
So one from me. So you haven't made an assumption about the underlying covariance function at all. Is that correct? And could you put in a family with some parameters and, you know?
Right. Actually, that is a part that I sort of skipped a little bit. I didn't give details. So essentially, if the variograms that we compute, it's essentially a point cloud, right? So on the x-axis you have the distances, h, which are the spatial distances. On the y-axis you have sort of the expression that I wrote down. And so before this can actually be applied for spatial prediction or clustering, we fit a model, an appropriate model to this point cloud. And this, for the results that I showed, we actually fit a turn.
Oh, right, okay. Yeah, so you are doing that, yeah.
We are doing that, that's right, yeah.
Yeah, I didn't know whether you're doing sort of some non-parametric thing.
No. We fit a turn. One can choose other models, but that's the one we used, yeah.
Yeah, good. Well, I think, are there any more questions? Oh, here's one. How might you handle the case where the functional data requires imputation? Okay, so there's a good question.
Imposing this framework with variograms are not estimated to the same lag value.
So I presume some missing parts to it.
Missing parts for functions in the actual functional observations.
I presume so. I'm
yeah, we haven't done that. I mean, we assume we observe complete functions. So we, I mean, sort of related to this, I have another student who, in fact, is working on that problem on sort of function estimation where the functions can be fragmented. And so, I mean, one could apply that approach first and then use the estimated functions in this framework, but that's not necessarily satisfactory because one would want to actually use the spatial information for the imputation as well. So one would have to combine the two.
Yeah, and a related question is about if the functions have different lengths. Yeah, so.
Yeah, we didn't consider that either. I mean, we assumed that the domain is the same. So one would have to first do some sort of pre-processing to get it to the form that we've assumed.
And is there an assumption the functions are smooth?
So
yeah, there is, isn't there? Oh, sorry, I shouldn't answer your question.
That's fine. It makes my life easier. You can answer if you'd like. Yeah, there are underlying assumptions. I mean, we do pre-smooth the functions a little bit before we use them in the for the spatial prediction and for the clustering. I mean, the function space that we start with is just the space of absolutely continuous functions, but in general, the prediction, sort of estimating the variograms is much more stable when the functions are smooth.
Yeah, you need to be able to differentiate them as well.
Yeah.
Good. Well, I think we are over time a bit. So thanks very much indeed. I'd like to thank all the speakers for this excellent session. It's been really interesting. So thanks very much indeed.
Thank you.
So do you want to say something, Anuj?
Yes, thank you very much, Ian, for chairing this session. You are just the right person to handle.
16 minutes late, though. That's a failure by 16 minutes.
That's absolutely fine. That means we got the bonus knowledge for 15 minutes. I want to thank Xavier, Usa, Mu, and Sebastian. All excellent talks, fantastic work. Keep at it. I want to, this would be the time for a break, a lunch break in our part of the world. I don't know what meals you will eat in other parts of the world. But I do want to mention that at 12:30, which is about 45 minutes from now, we have as an honored guest, Scott Acton from National Science Foundation. We have invited him to talk about funding opportunities, and there he is. It will be fantastic to chat with him. He is not only a National Science Foundation guy, but he has a brilliant career, back track record in image analysis, editor-in-chief of IEEE in image processing. So he's really a leader of the community in many different ways. So it will be great to have him. I will work with him on his presentation and the discussions. Half an hour session, 12:30 to 1 o'clock. Everybody is invited, especially young people, young assistant professors looking for dollars, and Scott is the dollar man. So this will be a good conduit to do it. Let's take a break. We will leave the session on, and we'll be back at around 12:30 for those who are interested in that. Otherwise, the regular session starts at 1:15 with getting back to brain imaging data analysis. Thank you, everybody.
Thanks.
Ian, I don't know whether you are in a lunchtime or dinner time mode, but what time is it? You're somewhere in between things.
It's dark. It's 4:45, so in the afternoon.
Yeah.
So a bit too early to eat. Too early for lunch. Oh, sorry, too early for dinner.
Are you at home or?
Yes. Yeah. This is a fake office behind me.
Is that fake? I mean, you're pulling that off very nicely. I mean, I have a real office and yours looks better than mine.
Yeah, well, no, this is my office at the university, which I'm projecting as if I'm there.
Yeah, so what I'm saying is that somehow the background, usually you can catch the few pixels overlapping boundaries.
But I think it helps, well, if you don't move much, obviously.
That's the trick.
I think maybe darker clothes helps as well. If you have a light jumper, then your head sort of half disappears and things.
That is true. So segmentation algorithm has to do a good.
Yeah. So I think it does it likes the contrast. Yeah. Good. Well, thanks for organizing. I'll be back later.
Okay. See you later.
Yeah. Okay then. All right. Thank you. Thanks.
Yeah. So, hi, Scott. So, did you want to start with the presentation? How do you want to proceed?
Yeah, that'd be great.
So, let's see. Do you have permission? I don't know. I mean, we're not ready to start yet, but if you want to test.
Yeah, let me test.
Yeah, that works.
Do you want me to unshare?
I mean, you can leave it on. That's fine. Unshare, whichever way you prefer it. Are you home or office? Or which
I'm
office?
home because there's a football game going on right outside my office, and I don't know what happens during pandemic football games. But in normal football games, we can't go to the office.
Okay.
It's not as important as it is at Florida State, Anuj, but you know.
Well, you know, our team is not doing well, but the hoopla is bigger than ever. Something happened this year. We are a bad team, and then we are playing some very good teams, which are our traditional rivals, and they canceled the games at the last minute for health reasons.
Oh, really?
And so this has become, you know, a source of contention because there was a team, Clemson, which actually arrived in town, and on the morning of the game day, they canceled the game. So, and they are rivals, so in some sense, you know, there's a lot of mudslinging going on, like you didn't want to play us, that sort of stuff. But I think it comes with the turf.
Yep.
But it is certainly very nice right now. The parking outside the building is just empty. And it's just, you know, like geodesically the shortest path between my office and the parking lot. Is a great time in that sense.
Yeah, there's good parking for sure at UVA as well.
So you're not in DC as much as you expected?
No, I'll be there next week for a little bit, but I'm generally in Charlottesville.
So everything is doable.
Everything is doable. We were all ready. We were ready for a snowstorm. We didn't know it was going to be a pandemic.
Okay.
Oh, we see you in presenter view. So Niz, do you know what I need to do to
Is it PowerPoint? Can you
Yeah.
hit the full screen on this?
Yeah,
I mean, don't you have that bottom, you know, at the bottom, you see that little.
Yeah, I was doing the little thing like this.
And it goes to that mode? That's strange.
Yeah.
I think it depends on whether you share the screen or share the
top left
PowerPoint.
corner.
Hold on,
There's a swap display, top left corner on your presenter view. It should work.
Top left corner.
Yeah, there is a swap displays option.
Yeah.
Oh, swap displays.
Yeah.
Whoever you were, thank you. Is that better now?
Much better. Let's wait a few more minutes. People are trickling in from their breaks. Are you okay with recording this session, Scott?
Oh yeah, definitely. And I'll give you a PDF of the slides after if you want it.
Okay, yeah, that would be nice. Yeah, fantastic. A lot of people are asking for recordings and PDFs. Not everybody's be able to attend the full. All right, I still see people coming in, but I think this is a good time to start. Welcome everybody back to this special session. I'm very happy and honored to introduce our guest this afternoon, Professor Scott Acton. He's a professor in electrical engineering at Virginia, Charlottesville, but is temporarily helping out National Science Foundation at the moment. So he is a star in his own right in this field, image processing, has done many different works, and was the editor-in-chief of the Transaction on Image Processing for several years, led the field very admirably. And so the main mode of operation today is Scott will present some main ideas, but we want to, time permitting, open up to some questions if people have about NSF and to Scott in general. So please use chat for that, and I will try to coordinate questions through the chat. Go ahead, Scott.
Thank you, Anuj. It's been a wonderful workshop so far. There's definitely some advantages to doing it remote, including my students can join us as well. Sometimes we can't all be together. A disadvantage is that I didn't get to meet Alan Yule yesterday, so I'm sad about that. All right, so I'm at NSF right now. I'm also at UVA, and that's where I'm talking to you from at this point, from my house in Charlottesville, Virginia. Let's go here. This is a 1-minute summary of my life. I was born in LA. We moved to New York. Our family didn't like it. We relocated in Northern Virginia, where I went to high school at Oakton High School. I went to Virginia Tech after that, studied engineering, got in a obnoxious red Camaro, went to Austin, Texas. Now, Anuj and Rama got to pay respect to their mentors yesterday, and my mentor was Al Bovic, seen here, winning the Emmy Award. Who wins an Emmy Award? I studied with Al Bovic at the University of Texas. Motorola supported my PhD work. Thank you, Motorola. And I began my career at Oklahoma State University, Stillwater, Oklahoma. A few years later, got in a red truck this time and went back to my home state of Virginia, where I've been teaching at the University of Virginia for 2 decades. Currently quarantined, so to speak, in Charlottesville with my wife and 2 sons that are attending school via Zoom. And now I'm having an office in Alexandria. Would love to answer your questions about the NSF as pertains to statistics and imaging in a few minutes. I'm going to take about 20 minutes of talking. The first 5 or 10 about my own research, because I couldn't bear to not talk about research while talking to this audience. So research and image analysis has impact. And let me give you an anecdote. 5 years ago, researchers thought there was no lymphatic structure in the brain. Some UVA scientists, not me, but Yoni Kipnis' lab, proved this thinking to be incorrect. And so their question that they've been working on is, could a previously unknown structure in the brain, we've been talking about the brain today, be responsible for a disease that affects many, many seniors? That is Alzheimer's. We were able to team with them on some work. Andrea Vicari is actually in the audience right now, a new professor at Middlebury College. We were able to team with the Kipnis lab, and through image analysis, and even through one of my loves, which is anisotropic diffusion, show that there's a link between Alzheimer's and the lymphatic system in mice. And this was named one of 5 notable advances by Nature Medicine. It was also acknowledged by Forbes, a business magazine, as groundbreaking research. So sometimes we actually make a difference. This conference involves statisticians, and I love it. So there's at least two possible approaches to involving statistics in your imaging research. Here's one. One is to be a great engineer and be a great statistician at the same time, like Al Hero. That's not my approach. My approach is one of rather robbing the statistician of his or her methods. And as you can see, I'm robbing Anuj right now. And let me tell you a brief anecdote about how I used Anuj's work in my work, in our lab's work. And it began with a question. It's a question from a biologist, my friend Barry Condren. And his question is, how do we quantify morphological difference between two neurons? I actually view this to be an open problem still, despite our great research, despite the research of Tamal Vadabal that I'm about to tell you about. And we take a different approach that we call path-based. And I'm hoping Shubhati Mukherjee is also watching from Paris, France. Envision this simple neuron on the right as a collection of three paths, maybe from the tip of a dendrite to the soma in the neuron. So we're going to view this neuron on the right as a union of three paths. These three paths obviously have position in three space. They have many other criteria or many other features, including concurrence. So we call concurrence at a given point, how many paths occupy that point or share that point. That's the concurrence at that point. What is the hierarchy at that point, which means how many bifurcations are above that point in the neuron. And so we've found out that higher hierarchy, if you're higher in the hierarchy, more towards the leaves, your morphology is less important. So we can take these two features, as well as the position in three space, and do what we call a neural path-to-path comparison. And what we're going to do is we're going to take two neurons, maybe one that's degenerated and one that's healthy, and compare them. And how do we quantify their difference? Well, we're going to auction off paths in one neuron to paths in another neuron. How do we do that? Well, with a Hungarian type auction process. And then once we get there, we're going to make a cost for each matching path. And that cost, you can see a sample cost function towards the bottom of my slide that penalizes differences in concurrence. It penalizes differences in locations and gives less importance to higher values of hierarchy in the denominator. Okay, and so we can parameterize all these paths and make them normalize from parameter 0 to parameter 1 and compare them. And then the neuron cost will be something like a combination of the path costs. And we can use this for clustering, we can use it for classification, and more importantly, what I'm going to show you, we can use it for visualization. And this is where Anuj comes in, because look at that location term. We used to do it in a style of doing a Procrustes analysis, making the best fit, and then doing some sort of Euclidean distance. We're not doing that any longer. We're using elastic deformation. This is from Anuj's paper going back almost a decade now in PAMI. And as you see, the one-legged man going from left to right in red in a non-elastic deformation seems illogical. The one-legged man going to the two-legged man in blue by elastic deformation, more specifically by transformation via square root velocity function, seems to be logical. And this is also true for my paths in my neurons. And so what we're going to do is we're going to take each path and transform it by SQRF to a manifold that Anuj and others introduced. And the beautiful thing about this manifold is, one, we can compute geodesic distance as a Euclidean distance, and that's nice. But two, statistically, I could take averages, I could take midpoints, I can even take 20% points along the journey and actually show how one path might deform into another path. And let me show you Tamal's work on this, and I think it's pretty cool. So upper left is a neuron with 400 paths. Lower left is a degenerated neuron with only 5 paths. Now we can see the midpoints by using, on a path-by-path basis, the square root velocity function, the statistical shape results of Anuja's lab. And this was just published in Neuroinformatics. And let me show you a little video. Here's how it works from a video. So say you're only able to image a mouse's neuron, for example, at 2 points. Well, you can simulate the points in between using our methodology. And I think that's pretty fun. What else are we working on real quick before I go to the NSF? We're working on image analysis below the diffraction limit. Okay, so electron microscopy has been doing this forever, right? Well, we want to image living things like bacteria below the diffraction limit. And let me just show you a couple examples. We're taking lattice light sheet microscope images, thanks to Andreas Gallman. We're doing deep neural nets because everyone else is doing it. And we're taking those deep neural net results that are flawed in many ways, including giving us broken bacteria or merged bacteria, and we're using geometry to do graph theoretic post-processing. We call this geometry and this graph theoretic processing L-cuts because we exploit the linear structure. And let me show you just a couple results. This just came out last week in Nature Communications. Here's some up close results. You see a raw image up in the upper left, simulated. You see ground truth in the upper right, which is almost impossible to do by human for these biofilms, these collection of bacteria. And I think it's a Shigella bacteria in this case. You see the CNN result, neural network result on the lower left. And then after our post-processing, along with the CNN, fixing some of these broken cells and also some of these merged cells. Gia has done a great job at comparing to the state of the art, and hopefully we're gonna get out a transactions paper from the image processing side soon on this work. As you can see, the result on the next to last column is her result in terms of a skeleton, and then we reconstruct from that point, knowing a little bit about the bacteria geometry. Now to what I'm getting paid for today. I'm gonna talk to you a little bit about the NSF. So we're trying to fund the best statistics and imaging research at the NSF. We do basic research. We're not necessarily application driven. We're a great home to many statisticians, as you know, and to many theorists in image processing. So my group is called Communications and Information Foundations, which is a bit of a misnomer given that I'm going to tell you that almost half of our stuff is machine learning. We have no deadlines for our core program. We have 3 program directors, Phil, Armand, and myself, and we have various duties within the cluster. And IPA just means that we're rotators, that will actually go back to our original jobs. Armand is at the University of Maryland, and I'm at the University of Virginia at some point. And Phil will be there as long as he wants to be there. Okay. So our program actually funds most of the states in the United States. Apparently, we haven't broken into the Wyoming, South Dakota, or Vermont markets. But maybe Professor Vakari will make that happen. About 1/5 of our awards go to female PIs, and of course, we're always trying to increase that. What are topics handled by my cluster? Signal and image processing. It's a big thing here. Machine learning, that's a big thing here. Information theory and communications. The word cloud that I formed below shows that learning and learned is a big deal. I took all these words from titles of our recently submitted proposals. We would like to say that in the past we've helped out researchers. We didn't do the research that has led to some big time advances in things like compressive sensing. That's helped out MRI. We've also done research and funded research in information theory that led to repair codes that you will use when you hit the Amazon cloud, for example. We even have our own movie in my program, and the movie's called The Bit Player. If you are a geek like myself, I encourage you to watch this movie. It's about the life of Claude Shannon, and it's a really nice movie. I think you can get it on Amazon Prime and maybe on Vimeo. You can at least see the trailer on Vimeo. So this was funded by our program, a movie. I'm very excited about Smart Health. I'm involved in this program. If you are doing collaboration in medical image processing or statistics of medical imaging, this might be the program for you. The new proposals are due in February, in a few months, and we're going to have a webinar December 21st at 3 p.m. New York time. So register online at the NSF website. I'm going to make these slides available, so don't worry about taking notes. These are meaty projects of $1.2 million, and they're jointly reviewed by the NSF and the NIH. And let me tell you a little bit about what we want here. We want not just basic understanding like Niels Bohr, or not just something commercial like Steve Jobs. We want Louis Pasteur. We want use-inspired research. And of course, if you're neither, that's a problem as well. So Smart Health, look for it on the website. It funds a lot of image processing, computer vision work, and we're excited about the new program that also has a focus on artificial intelligence, of course. In terms of COVID-19, we've recently funded, I'm in the computer science wing, if you will. We've recently funded over 300 small proposals related to the pandemic. There are going to be some big efforts that are coming out. I can't tell you more about that, but they're going to be coming out and being announced in the next couple of months. If you have a really cool imaging or image processing idea that relates to the pandemic now or future pandemics, let me know. Shoot me an email. I also am helping out with robotics. I'm not a roboticist, but as computer vision pertains to robotics, I'm lending a hand, and we now have what's called the foundational research program in robotics. So more theory-driven research that's also validated by application is in this new program that you can read about also on the NSF web. You've probably heard about the AI Institutes. They made quite a splash. To submit to this program, you need to turn the clock back 24 hours because they were due yesterday. These are the themes for this year. Of note to our statistics community is the AI Institute for Advances in Optimization and the AI Institute in Dynamic Systems. These are nice $20 million grants that are generally collaborations between several institutions. If you didn't submit this year, you can think about next year. Engineering, in addition to computer and information science and engineering, which is my directorate, is also a nice place to submit. If you have an imaging idea there, you might contact Jinshan Lin at the email that I'm providing. They form a program that funds a lot of fundamental and applied research in signal processing. So other areas that you might not think about, my most recent NSF funding before I joined the NSF is actually from biology and also from education more recently. So you might look at geosciences if you're a remote sensing person. You might look at neuroscience if you're one of these people talking about the brain today. And people from outside the US, we do have collaborative programs with many countries, France, a new one with Israel. So there is a possibility of joint funding. Cyber-physical systems is another place where image processing people get involved from time to time. And now, thanks to Judy Wong, I am going to talk a little bit about statistics for a couple of minutes. And when I was in grad school, they told me there were statistics, there were lies, big lies, statistics, and then benchmarks in that order. So the statistics program supports research in statistical theory and methods, and they actually do have deadlines that are in the beginning of December. You've got about a week left if you want to write what we call a small proposal. If you're an assistant professor, you might consider the career program July 2021. And in the future, workshops like this are often funded by the NSF. All you have to do is send us a short proposal with a little guidance, and we might be able to fund your workshop. The statistics officers, including Judy, are the people you see on the screen. And they're, of course, very knowledgeable in machine learning and data science as well. They have a graduate internship program, and this graduate internship program does not require US citizenship. look on the web if you're interested as a graduate student. If you've just graduated and you want a postdoc, we also have a postdoctoral research fellowship. This does require US citizenship or green card. And this is a joint program with other agencies that the NSF sponsors. So this will be due again in October 2021. I want to point out that there's a program called Computational and Data Science Enabled, or Data Enabled Science and Engineering and Stat Sciences. This is a cross-directorate program and involves big problems in computational and data-enabled discovery, which might fit this audience. Again, September 2021 for this program is going to be your next chance. If you're an anomaly detection person, we've seen some of that stuff in the last day and a half. You might be interested in our Algorithms for Threat Detection program, which is joint with Geospatial Intelligence Agency. And that has a deadline coming up in February. And you don't have to be a US citizen to participate in such a program as an investigator. Focus research groups. If you have a big collaboration working on a big problem, you might be interested in this new program that's starting in September of 2021. Statisticians are particularly called out as pieces of the puzzle here. So most of our programs are driven by 10 big ideas. I want to point you to the one in the upper left, which has relevance to this workshop, which is harnessing the data revolution. So harnessing the data revolution is a cute way of saying what we're doing here at this workshop, trying to do big data, trying to do multidimensional data, trying to apply statistics and get our hands and pop the hood on machine learning. I'm very excited because research in statistics and imaging are at the core of innovation and, in fact, technological revolution. They are keys to reverse engineering the brain, which I think is a 20-year horizon problem. They are the keys to statistical signal processing, which gave us the iPhone and other communications devices that we hate. Image analysis certainly is a key component in the driverless car. I like to remind people that signal processing, put the C, the convolution, in CNN. And finally, statistics is our only hope for rigor in data science. So with that, I'll open it up for questions.
Thanks very much, Scott. It's wonderful, exciting, and a little bit inspiring. I mean, I think it's sort of daunting for a young person to come out of school and college, and then there is a pressure on seeking funding. And it's good to know that there is somebody who is sort of inviting on the other end, not just making a judgment on you, but also seeking and encouraging. There are a couple of questions on the chat, and I'll bring them up in a minute. There was something, I remember when I was a new assistant professor, there was some either director or deputy director of NSF came to FSU, gave a large talk. And I remember she saying something about the people who get funded with high probability are the people who actually communicate with the program managers in some ways before they put in the proposals. Is it correct? I mean, is it still a tendency?
So great question, Nish. The answer is yes. And what's funny is that I'm arguably towards the end of my career, and I didn't know this. I didn't know this as an investigator, but as a program director, the people that actually reach out, and not only reach out, but sort of stick with the program, are indeed more likely to get it right in the end and to put in a good proposal. So I think that's totally good advice, and it's still valid in 2020. The meetings this year might be over Zoom instead of over coffee, but we're also, when this whole thing ends, we're certainly game for, kicking up our heels at the Starbucks and having a coffee and meeting the young investigators as well.
Fantastic. I think that's something important. I remember I have not really pursued that myself, but I do remember that I know some people are very active in contacting the program managers and sort of zeroing in on the topics before they write proposals. There is a question about international collaboration, and you did refer to it. So I wanted to see, like, for example, take the example with France. You and I have a soft spot for being in southern France. So how do we go about doing it? I mean, should we just put in I have a collaborator and they want to collaborate. What's the mechanism for, putting together the proposal over and beyond what we do, like small proposals here?
Yeah, that's a great question. And so one thing that might be misleading is that the French investigator will get money from France, and the American investigator will get money from the NSF. And basically what the cool thing is the collaboration is saying, hey, we're leveraging this capability that's in France and this capability that's in the United States. And if you fund us, this is going to make even a larger impact, because we're going to be able to do more things and go farther in the research. So yeah, so France is a good example with an established program. UK has an established program. I mentioned Israel, and they're all on the web on the NSF international website. But essentially the review process is independent, meaning that we're not going to have any influence over the French review process, and the French aren't going to have an influence on the NSF process. But it would be fun to get one of these together.
So how does it work? I mean, so I can, we do the process on our end and they do, but if these are independent decisions, I mean, what's the probability that they both get funded? I mean, is there some handshaking in between the evaluation somehow?
Yeah, I just think there's a greater chance, at least from our side, of funding an American investigator who's coming to us with a French investigator that's going to have funds going towards the same objectives.
Okay. So I don't know, Usa, if that answered your question, or if you had anything more to ask. But in the meantime, there's a question from Arvin about SBIRs. Can you say something about SBIR?
Sure. I'm not personally involved with SBIRs, but on the engineering side, for example, there's SBIRs that can be initiated by a company and with a university collaborator. These are, sort of small efforts of around $100,000. And in phase one, you might only have 6 to 9 months, but then in phase two, you might be able to get $1 million and actually, bring some sort of product or some sort of application to fruition. So certainly from the engineering side, there's a lot of SBIR money. There's also SBIR money from defense and from the NIH. It is a mandated line item from Congress. We have to spend a certain percentage on the SBIR program. So, and perhaps it's, maybe the phase ones are a little greater hit rate than a normal proposal.
Let me go back to this AI institutes that you mentioned. So what is the frequency? So are these annual programs, this listing you had? I'm assuming the topics change from year to year.
They're changing from year to year. It's annual in the sense it's been 2 years, and we think there'll be a third. It's made a big splash in terms of, at least in the United States, the institutions that were awarded in the first round really celebrated these awards. They're $20 million. And I think it's, we're in the midst of a revolution. We've been hearing about it yesterday, starting with Alan's talk. And these institutions, they want to say, hey, we're front and center. We're the ones that are moving the needle on artificial intelligence. And so this is a big way to do it. It could be argued that little small efforts are also important, but these are huge efforts that I think will definitely continue into next year. And statistics, as I said, play an important role in at least 2 of those efforts.
So the topics are usually the same. I mean, you had this listing about the broad categories of AI institutes. next year, will it be a different, renaming of the topic areas? Or
It will be. For example, agriculture put in money to do AI in agriculture. Companies like Google, Intel, Amazon, and Accenture put in money to do research that was relevant to what they want to see in the future. So, that's just to support the money that's already there from NSF. So the topics can be driven by other agencies and other large companies, for example, and they do change from year to year.
Okay, thanks. So this is a question from Ann Lee. Can you please say something about HDR Institute? Are the AI Institute calls replacing these?
No, that's a great question. And I officially don't know the answer, but so HDR stands for Harnessing the Data Revolution. And I haven't seen a new call for Harnessing the Data Revolution. I don't know if the management would say that it's a replacement, but it looks like that could be the case.
Okay, but isn't HDR more engineering oriented, or is it more general? Or did I misread that announcement?
I think you're right, Anush. Given based on like sort of the primary. So size, or the computer science side, drives the AI institutes primarily. Of course, engineering plays a part, and so does DMS, the Division of Mathematical Sciences. But you're right. The AI institutes are more computer science driven, if you will.
Any news on tripods? Are they done, or are they coming back next round?
I think tripods could come back. But I don't know that officially either.
Okay.
We'll have to wait till about February to know.
Okay. Any other question anybody has? One of our lead speakers yesterday, Sudeep Sarkar, has put in a very beautiful AI Center for Biology. It's fascinating. I mean, he put together 45 people from AI and biology. So fingers crossed, and be kind to us. But it's, it's very exciting to, like your work, with your colleague on Neuron and going to Nature Communication. And it's fascinating that, for people like us who can't directly just write Nature or science papers, but through these, you learn about problems, you get data sets, and you have a shot at something very fundamental in science, which usually, sitting in our offices, we are not exposed to.
Yeah, it's really fun. And next time, instead of just using your stuff, we'll have to collaborate. Okay.
Absolutely. Once you come back out, there is a quick question about from Arvind, follow up on SBIRs about connecting small businesses. Does NSF help connect universities with small?
That's a great question. So within engineering, if you check on the website, there's a division that's devoted to industrial partnerships. And they do exactly that. So I could provide you some contacts. If Arvind wanted to send me an email at sacton@nsf.gov, I'll make that connection.
There is a quick question from Carlos about, do you have recommendation on how to determine which funding best fits our research?
Yeah, no, so that's an important question. And I have two answers. The first answer is make sure you look at the web to see what's been funded, because the program names are really sometimes mysterious and misleading. So look at what's been funded and see if it matches your what you're doing. Another answer to that question is send me or other program directors a one-pager. We can't look at your entire proposal and evaluate it, but we can look at a one-pager and say, this should go to IIS, which is Intelligent Systems. This should go to RI, Robust Intelligence. So those are two answers to that question.
Fantastic, Scott. Great to have you at NSF, and look forward to working with you more. We will wind up that session. Our next session is scheduled to start in about 15 minutes. So let's take a little bit of a break, and hopefully we'll find our speakers for the next session very soon. Thank you, Scott. Excellent.
Thank you, Nish.
Thank you, Scott. So I have a question. Is Scott gone?
No, I'm not.
Okay, nice to meet you, and nice to meet Anuju too. We never met. One question I have, that I have been involved in this institute proposal with led by engineering colleagues, and I observed that they just have such a good process to really do this. I think if you look at all the proposals coming into NSF, very few are led by statisticians for this institute. And you can see that more and more funding are really going to this because hard problem have to be solved by a team. So I wonder, this seems to be an excellent community that I'm kind of putting Anuj on the spot since he organized this workshop. I feel it would be interesting for statisticians with Scott's help, who's an insider, to at least give a try. Because what I observed, I did a couple with CS people, and we got the Data Science Institute. We also got the deep learning, and now part of this dynamic led by MIT. And I'm just like part of it. But I observe that there's a way even young people can really lead. In the beginning, I felt like this is never going to converge, right? Because people never met 40 people, and somehow magically end up with a coherent proposal. And this is a process I've been watching and participating, but not as a leader, with quite amazement. And I felt this is what's missing in the statistical community. We just don't, I mean, even me, I feel I'm pretty much engineering compared with most people in statistics, right? For me, it was still amazing how this just gonna work. And this is kind of soft knowledge in the engineering community that I think statistics, maybe even mathematics too, we just don't have. And how can we get help from you and people engineering? Because I do think we can have a lot to offer, as you indicated, use Anuj's work, but we still not be able to really play a bigger role. I think we should really play. But I identify this is a bottleneck. I just feel I'm pretty amazed just even watching the process, right? I'm part of it because I'm an engineer, so I get a lot of opportunity to be part of it. First was the Purdue, right, and STC Center. I was with them for 10 years. Again, I got very good support. Didn't have to do a lot with the organization. So there's some sociology that the engineering culture has. I think stats and even medical people, biology people have, that we are lacking. And my question to you both is, can we use
I think you bring together a fantastic point. And I mean, that's the heart of the reason why I organized this workshop too, is I mean, it's a cultural thing. It's sort of a lack of ambition and going for the bigger things. I think there has been in the statistics community, some well-defined problems and focus on that. I mean, this section on statistics in imaging, this section has existed for many years, but it has been more or less neuroimaging data analysis. It's been it's a successful research topic, but it's not as ambitious as statistics could be, to step out of your comfort zone and look at all the different problems we could solve and to be the leaders. I think that's the point you are bringing in, is rather than just be a consultant on a project, step up. Because if you are providing the biggest chunk in that proposal, if statistics is at the core of the proposal, then we can be the leaders too. And that is sort of missing, I think, in our community.
Yeah, and I think that's the only answer, is just, as New said, to step up. And then also, as the rest of us become older and some of us take administrative positions, maybe to encourage our younger faculty to step up and to give them the resources. Because Ben, I think you hit on two problems, or two, I don't know if they're problems, but they're roadblocks. One is the history of the statistician, in the sense that the statistician is more likely to write a single author paper. The statistician is more likely to be humble. The engineer is more likely to write in these big teams and to build these big projects and to take over the entire world. The other problem is that within a mathematics faculty, perhaps the resources aren't the same as what we give engineering. To do one of these big center grants, you have to have resources, you have to have staff, you have to have the ability to have space. So all these things I think have been roadblocks, and yeah, I guess I'm in agreement with Anuj that we just need people in the community, both young and mid-career, to step up and to take leadership.
Thank you, Scott, and thank you, Ben. For
I think I definitely completely agree with both of you. But I think what I'm asking is, we can do some training. To do some training to give not just the ambition people have, the skills that the pipeline, and have some engineering faculty to talk to the, have a little, at least in the beginning, before the statistics community start having this knowledge within our community, have human mentors from engineering, and to really show, like, do a co-lead or something, or that's how we do it, and I'll do it with you this time, and next time you know how this is done. I think that's the self-knowledge, but I think space is a very good point, and also executive support. Engineering Institute is much better, right? They have very able staff who take over. I do, everything, like travel myself. It's a lot of those times, there's no help. So it's really the statistics community need to ask more from the university.
I think this is something we can propose to Kathy answer to, in terms of looking into providing training.
Yep.
Maybe this is something ASA can step in and do.
Yeah. It's for the next generation. I'm really looking forward to seeing that happening.
Thank you both. Thanks once again, Scott, and thanks, Ben, for bringing up this important issue. All right, we are going to wrap up this session and move it into next session. And I'm going to, where am I? I'm looking for Ranjan. Are you there, Ranjan? The next session. Oh, there you are. Jianling, would you like to check your presentation and see if are you able to share screen and make sure it?
So you mean to try to share screen right now?
Yeah, just to check. I will go through the speakers quickly if they are all here. I saw Marina, but yes, that worked. Yeah.
I haven't do the full screen yet. I'll do it later. Because if I do full screen, I have to escape anyway. It works, right?
Yeah, this.
Should I put it up already?
Yeah, you can leave it up. So Ranjan, are you ready to take over?
Yeah. I think there's a couple of, I think there are a couple of minutes left though.
Yeah, no, exactly. I was going to say, just take 2-3 more minutes and
sure. Yeah.
And start when you're ready.
Do you want me to try to share? Oh, sorry, I'm not visible.
Marina, yes, please try quickly. Just make sure.
Okay.
Oh, do I have to get out the sharing mode?
Yeah, that's right.
How do I get out? Let's see. Stop sharing.
Yeah,
okay.
At the top.
Yep.
We do this. I will go full screen.
Yeah, you're good.
Okay, perfect. So I can stop sharing. Okay. Thank you.
Waiting for Hong too, but he will show up when he'll show up. Hong 2 is 50-50 any given day.
Maybe he'll only show up when he's speaking.
We have to penalize him for that.
Did he show up at the organizing committee meetings ever? I don't remember. He did contribute though.
Yeah.
He contributes his own way.
Good to see you, Ranjan.
Oh, there was
Same here.
Yeah, hi. Good to see you over Zoom. Well, I can see your letters of your name.
We're all learning how to communicate with each other with 200 other people in the room.
Yeah.
Paying attention.
So I realized some time ago that what it hurts is new collaborations. No longer can you actually hit people and run into people in the hallway and talk about stuff, right? Because these are all setup meetings. So that really hurts, actually.
Yeah.
I mean, it hurts the younger people more, I think.
Yeah, we have to use this as just a starting point and do more. All right, Ranjan, let's get started.
Okay, sure. All right, let me get this. So thanks to Anuj and Florida State University for organizing this workshop. It has been great, and everyone has said great things about it also. So the topic of the session today is brain imaging data analysis, and we have three speakers: Jianling Wang, Hongtu Zhu, and Marina Vanucci. I will first introduce Jianling. So Professor Wang is a distinguished professor at the Department of Statistics at UC Davis, and she got a PhD in statistics from Berkeley under Professors Kiefer and Lecam. And she actually started her teaching career in Iowa, not Iowa State, but the other Iowa, University of Iowa. She was previously assistant professor at the University of Iowa, and then she was briefly at Wharton School before she moved on to UC Davis, where she is now. Her research interests span both theory and applications and are currently focused on functional data analysis and brain functional connectivity. She's an AAAS Fellow, ASA Fellow, IMS Fellow, elected member of the International Statistical Institute, IMS Medellin Lecturer, Noether Senior Research Awardee, Distinguished Achievement Award from the ICSA, International Chinese Statistical Association, and she's currently also co-editor of the Journal of American Statistical Association, Theory and Methods. So with that, I think I will hand it over to Professor Wang.
Thanks, Rajan. Can you hear me?
Yeah, sure, please go ahead.
Just a cautionary remark. I just noticed the internet seems to be a bit unstable this morning. I hope it'll work. Yeah, okay, so thanks a lot. Actually, you are one of the few people who knows I have two advisors. All right, and thanks Anuj for organizing this workshop. So actually, you are not seeing the picture, right? You are seeing my full slide, okay. Because I'm seeing, let me move it. So this talk is about how to align fMRI time series to study functional connectivity. And because it was inspired by my main research interest on functional data analysis, so I'm gonna start with a brief introduction of functional data analysis. All right, and then I will first show a predecessor of this one, which is a simpler version. But actually there we have more success story to tell. So to transform high dimensional data to functional data. And then only in part 2 here, this is the main topic. Okay, so let's begin. What is functional data? I think most people knows that by now, but just in case, I'm gonna run through that quickly and mention why we want to convert high dimensional data to functional data. So functional data is a sample of random function, and the key is each subject you observe a function, okay? So the atom of the data is a function, and these function can be curves, images, or object data. All right, so the first talk focus on curves, which is the predecessor, because Anuj said we should make these talks more expository. And the second part is for object data, which ties to image. So standard functional data is the fMRI data, and you see a function for each subject. And this is just an illustration of 20 subjects on a single voxel. Okay, so I mentioned that functional data are functions, so which means they are infinite dimensional. But in reality, we can only measure the data at discrete time points. The fMRI data you see here is measured at 300 time points. Okay, so realistically, this is 3-dimensional data, which is high dimensional because usually the sample size for imaging study is not that big. And the question now is there a curse of high dimensionality? Because we actually observe high dimensional data. And this is the strength of functional data compared to high dimensional data. So the method to handle high dimensional data are quite different from those for functional data. For instance, large P is a challenge for high dimensional data, but for people who do functional data analysis, we love high dimensional data like this. The more, the better, okay? And another benefit is that measurement error is a challenge for multivariate data, but it's very easy to handle for functional data. So the question now is then, how did functional data get away with the curse of large P and measurement errors? Well, the answer is that it's not a free lunch. Oops, sorry. Okay, it's because we assume continuity and smoothness of the data. Okay, so if the data is continuous function, then you can borrow information in a neighborhood, and that mathematically will jump through the hoops of the high dimensional curse. Okay. And the next question is, why can we assume continuity? Well, you need some kind of domain there, right? And the reason we can do so is because we have a natural ordering of the data. So often the functional data are collected over time, so you have an order in time, but it doesn't have to be ordered in time, as I will illustrate later on. Okay, so now back to the high dimensional data. With that in mind, a question that we have is there a way we can order the p-dimensional data? So the ordered data will represent a discretized version. Okay, so this is important because we obviously we only observe discrete data. Okay, so the goal is that can we regard them as the discretized version of functional data? Okay, so the goal is now to convert high dimensional multivariate data to functional data. And I call this a pre-processing step. Okay. The reason is right now we are not doing any damage to the data. We're just permute the data, the order, because it's multivariate data. There is no particular order. You can rearrange them whichever way you want. Okay? And after you arrange that, you will do the next step of data analysis. That's where you may cause some damage. Okay. All right. So the goal is, as I said, just to reorder them. And before I illustrate that, I have to remind the audience that this will make sense if your data are all measured on the same scale. Okay. In other words, for example, gene expression data is a good example. You have a lot of genes. Okay. It would not make sense for, say, if you are doing height, weight, blood pressure, etc., because they are on totally different scale. Okay, so that's the end of a very quick introduction to functional data, which motivated why we want to do that. So now we get on the business. How do we transform high dimensional data to functional data? Okay, so this is based on, this is based on an old paper 2011 JASA. Okay. And the idea is that we will regard, as I already mentioned, the p-dimensional data as an ordered, perturbed, and also noisy, because we want to accommodate noise as well in the measurement. Okay, so we assume, or at least we allow the data are contaminated. And we want to construct a proximity or a similarity measure between pairs of features. So let's say you have the J's and the K's feature, and you want to perturb them so that those that are closely related to or similar will be placed close to each other. Okay, so in other words, you put the friends or those who are alike together. All right, so what we were going to do is, for example, after we arrange them, maybe X, oops, xk will sit here and xj there. Let me illustrate quickly. So let's say I have a 10-dimensional data to start with. And then after we did our method, they assign each of them to a particular location, okay? So here's a real illustration based on a simulated data. You can see that there's no structure at all, very noisy. Okay, we start to organize the first one, the second one, etc. In the end, you can see here that you get, okay, last one, yeah, one more. Okay, you get actually a smooth curve, okay? So what I did was that I cheated. I actually started with this order, okay? This is the data we generate from a smooth function, and then we just perturb the order. That's what you see, okay? And in the end, we want to restore the data like that if we did perfectly. Okay, so how do we do that then? Well, the bottom line is we didn't invent anything new. We just use existing methods. For instance, MDS, multidimensional scaling, okay? So to do that, basically all you need is a distance matrix between any two features, okay? You need to find the right distance for your data, which is meaningful for your data. And once you have a distance to measure proximity, similarity, or actually distance would be dissimilarity or similarity, whichever. And then you are in business. You can perform that, and including using some machine learning tools as well, okay? But in this talk, we use MDS. Actually, we found the MDS more effective than a lot of the fancy machine learning tools for our purpose. Okay, so, how does it work? Well, after I have, let's say, with the previous illustration, let's say we have successfully transformed the data, okay, now to a similarly smooth curve. Well, it's still a discrete data, right? And if it's functional data, it should be function. So what do? Well, very easy. We just linear interpolated them, okay? Because we put them very close together. Oh, by the way, I should mention here, in MDS, usually you want to arrange the subject or objects so that the rearranged data reflect the actual distance of the two features. But here we don't care about the actual distance. We just want to put the similar ones together. So for that reason, we use an equally spaced grid between 0 and 1 to assign the location of the feature. Hope that's clear. This makes it easier, actually, because had we really be ambitious enough to take into account this, it would be a much harder task. Okay, so as I say, after stringing, then with the hope that if you believe there is a latent order of the data that is actually smooth, then you can start to apply functional data analysis tool to your data to do classification, clustering, or regression, whatever. Okay, so the MDS that we use is actually a unidimension because basically we want to align the data to an interval so we can apply functional data for curves. So it's UDS, called unidimensional scaling. And we gave a name to this method, stringing, okay? The reason is what we did before, if you look at it like that, it looks like, think of that as a pearl necklace, okay? Nicely connected together. And somebody made a mistake, drop it on the floor. So now they are all scrambled, okay? So we want to restring the data. So we gave that name stringing. Okay. String, okay, so the MDS procedure will involve, as I mentioned earlier, that you select a distance measure. And two examples are the Euclidean distance or the Pearson correlation. Okay, so for example, if you are dealing with gene expression data, then Pearson correlation or the Pearson distance would make more sense. But if you are dealing with another type of data, maybe just the Euclidean. So I have an example to illustrate both. Okay, let me see how much time. Okay, all right. So I think I'll skip this. It's basically just the MDS algorithm, okay? And you can get that from MATLAB. Let me run through quickly a couple of illustrations. I have 3 here, but I may have to just brush through some of them very quickly because of the time limitation. So the first one is, okay, forget about all the previous steps. Just say we select 50 most significant genes, okay? And the goal here is to see there are 2 types of leukemia patients, one with 27 and one with 11 patients. And we want to see how the genes distinguish these 2 groups, or the 2 groups have different expressed genes. So if you look at, don't look at the right panel yet, okay, look at the left panel here. These were the original gene order, okay? And you can see here, you can see a difference already between the 2 groups, okay? The top panels are the first group with 27 subjects and the lower ones, 11 subjects, okay? After we applied our MDS procedure here, you now see clearly these genes separated the 2 groups, okay? So this is an illustration just to show that it's for visualization, which was one of the main goal or objective of MDS. So we didn't do anything beyond that, just to show, because after we are done with that, it's pretty clear, then the biologists can run additional experiments to check. All right, the second example is tree ring data, okay, collected in 45 years from 1932 to 1976, and coincidentally for 45 blue oak trees in California, the Santa Clara County. So in this particular example, both the dimension and the sample size are equal, 45. So this is the original tree ring data, ordered according to year, because data were collected over time. So by definition, this is already like a functional data, okay? The question we want to debate is whether we can throw the smoothness assumption to it or not. Okay, now let's see what happened after we order it. Now you see a clear trend. It goes up, okay? So the intriguing question is what's going on there? And you probably can guess already. Trees grow faster when it rains more, especially in California. Okay? So the intrinsic order behind it is probably caused by the precipitation, annual precipitation. Okay, so I already explained that. That was the speculation, and that seems to make common sense. But of course, as a statistician or a scientist, we have to provide evidence, right? That was just a speculation. So we went to get the actual precipitation level of those years. These are the red curves here, the red dots. And then we compare that according to the order we stream, okay? So if you look at the first year, this has the highest rank, because you can see, let's go back, that earlier on, they are a lot of rain in that year. Okay, so these are the order of stringing. And you can see they seems to have certain synchronization together. They go up and down, you know, pretty much at the same time. So we did a statistical test for that, and sure indeed, it was significant. So the lesson learned from this one is that we actually started with seemingly functional data, but that's not the best way perhaps to impose the smoothness assumption. After we rearrange it, and then we got smoother data, okay? And which means stringing can uncover the latent factor. So next time when you have functional data, you might want to ask yourself, do I really want to treat it as functional over time, or is there a better order behind it? Okay, so the last example is again gene expression data. Okay, this time, let's say, just focus on the 80 genes we pre-selected, okay, out of 7,000. By the way, we didn't even try the 7,000. We knew we will not be able to do it. Okay, so a little bit pre-processing, or like most researchers do, is to pre-select the significant genes, then proceed with that. Okay, so after we select the 80 genes, previously, I never showed you that what did we do with it with the FDA approach. This one will be an illustration. So now that we have arranged the 80 genes as a functional data, Okay, so we will propose a model. This is this is breast cancer. Okay. Oh, sorry, lymphoma. Okay, so we are interested in survival. So we use the proportional hazard model. And here, actually, because we have a process which is based on the 80 genes that we constructed. So it's an artificial process we created, okay? And which model can we use? Where there weren't any at that point, so we proposed this is a new model. It's a Cox type of model, proportional hazards. And we basically, in order to handle functional data, you basically use integration, the inner product, and therefore you have a coefficient function. Okay? And this differs from the conventional Cox model, because what we have here is like we have a time variant covariate, so-called, okay? But the standard Cox model for time variant covariate looks like this. And it's what we call the concurrent model, because at time t, the feature at that time point only affects the current risk. H is the hazard function at time t. Okay, so it didn't use the entire history, and this one used the entire history. Okay? And another way to look at that is this data actually has been analyzed by many researchers, and they just treat the gene expression as 80-dimensional data. So they would employ this Cox model instead. So you can see here now the similarity between model 2 and model 1. Model 1 is just a continuous version. This is the inner product of vector. This is the continuous expansion, which is the inner product in the function space. Okay, after we construct that one, we have to create new methodology, etc., to do that. Okay, an interesting question is here. It's actually not clear which method is easier to do, because if you go back here, you have to tackle the high-dimensional data. Here you have to tackle, this is a nasty functional inverse problem. Okay, the reason is that it involves the inversion of the entire covariance process, which is not bounded. So it's actually not clear that we would be better off with the FDA approach. Okay? And then of course, we have to wait until we see what it works for the data or not. Okay, so after we did that, okay, we applied this, the method to estimate the coefficient function beta here. Now you can see, okay, this is very nice for us to see at that point. The reason is that you can see it, the MDS procedure or the string procedure actually clearly separated the genes into those which are at risk. Okay, those with positive slope contributes to higher risk. Those with negative does the opposite. Okay, so MDS actually, or string, successfully rearranged the genes so that all the negative ones were on one side and the positive ones on the other side. Okay, then we compare our method with some existing method. This was the method by, I think, Tetralogy, Hasty, and Eric Baer. They proposed here, the supervised principal component regression method. Okay. And the other two are just the standard ridge regression or lasso. Okay. We use a deviance measure for Cox model, and smaller deviance is better. So you can see here, stringing, okay, usually people just report median performance. Okay, so stringing has the smallest deviance. But we also look at a few more because it could be just fluke. We did better with the median. So we look at the first quartile and the third quartile as well. It's consistently better. So that is the verdict for this particular data set. Stringing did better than other high dimensional approach. Okay. All right, and then the theoretical support behind that method actually is in the 2016 paper, much later, and jointly with Xiaowang, the speaker yesterday, who gave a fabulous talk on GAN. All right, so to make it a quick summary, we allowed also additional discrete covariate because usually in survival analysis, there is a treatment, people are interested in that. So we end up with a semi-parametric model, and then we use the penalized partial likelihood approach to estimate that. And we can get semi-parametric efficiency for the parametric component and minimax for the non-parametric. So both are optimal. Okay, so sorry, it took quite a while. Let me see. How much time do I have left? 15
You have about 20 minutes left.
How much?
20 minutes.
Oh, 20 minutes, okay.
Yeah,
All right.
yeah.
So, but I will try not to use 20 minutes. Okay?
That's fine, sure. No
now
problem.
it's the real topic, okay? String object data. So the first part you just heard is to string scalar data, scalar components of p-dimensional data, okay? And in this talk, we will replace the scalar with an object, okay? It can be any object. Our toy object here is the fMRI time series, okay? And comes from the brain imaging. And we want to align those fMRI time series. That's the ultimate goal. And this paper appeared last year with a student in brain connectivity, I think. Okay, so I think I don't need to introduce this for this audience. Here is the fMRI time series here, for example, from this particular region or voxel, okay? In this case, it's the voxel. And what happened is that you have one time series like this at each location. So it's a spatial object. Let's put it that way, right? It's in the 3D space, and each location has a time series. So going back to the old picture where we have scalar, there in that previous example, all these features were scalar. Now replace all of them by a time series, okay? Basically, you have this one, like a time series fMRI on each one of them. Okay, and I haven't told you how many regions we have, okay? So we knew, as I said before, we couldn't do voxel-wise analysis. That would be way too ambitious. So we did a region analysis. So we partitioned the brain into 90 regions using the AAL template, okay? So imagine now in each region, we extract a representative fMRI time series. There's a story how you do that, etc. We use seed voxel, etc., and average around that. Okay, so to make the long story short, we now have a representation in each area, a time series, and all together we have 90 of them. Okay, not too fast. Okay, so to illustrate this, we use Alzheimer's disease data from UC Davis. This is not from the ADNI, okay? This is a local data. And that consists of 172 normal subjects and 62 Alzheimer's disease subjects. And I already mentioned this. Okay, so our goal is now to string those objects, which are time series. Okay, so this is a typical demented subject. Okay, this is a typical normal subject, just one subject. So remember, each subject you will have a brain map over there. Okay, this is just the display of the fMRI time series. So the way to look at it, there is an order in the AAL. You know, they arrange them in certain order. So we just follow that order. And on each, if you look at each of the vertical direction, that's your time series in the heat map. Okay. All right, because 3D picture would be too hard to visualize. And that is a normal subject. So if you stare at these two pictures, there seems to be some difference in the structure, right? But we don't quite know exactly what it is, okay? All right, after we apply the string method, which I will explain later on, you can see now, it gives a little bit more structure now. Basically what happened here, these are the new order after we string them. You can see now there's more continuity in there because they tend to stay more with the same color or similar color. Like previously, it just flip-flop, but still it's very hard to see it, okay? We seems to be doing something, but hard to see. Okay, so then we look at the brain connectivity map. Okay, this is based on connectivity. It's no longer the fMRI time series. It's a 90 by 90 dimensional matrix here. And these are the original one based on AAL order. And down there, you get the one after alignment. Now you can see there's much more prominent connectivity structure after we string them, okay? And so the later part of the talk will focus on this. All right, so how do we do that? Okay, again, the goal is the same as before. We want to put similar objects together, okay? And so that we can claim there's a smooth transition and possibly apply a functional data analysis method subsequently, okay? All right, so here we need to determine what the similar object means. In other words, pick a distance measure, okay? And since we want to study brain connectivity, the goal is to use the functional connectivity because we have functional data, the fMRI here. All right, so we want to use the standard measure in the community. They use Pearson correlation is possibly the most popular measure for connectivity study. And basically what it does is the following, okay? Consider two fMRI time series here, the red one and the blue one. And then at each time point, you have one from the red, one from the blue. That's like a pair XI, YI, okay? And then you have 236 pairs over time. You just do a Pearson correlation of those pairs, okay? That's called, that measures the temporal dependency, which is brain connectivity. When we first approached this problem, we were totally ignorant of neuroscience, okay? And when the collaborators show us that's how neuroscientists does connectivity, our first reaction was, this is totally wrong. Because Pearson correlation is designed for independent data. And yet here you have time series over time, they are dependent data, okay? At the least, in order you want to do any meaningful correlation based on time series data or dependent data, you need some kind of stationarity assumption. And luckily that one was actually taken care of, okay? Because there are all kinds of pre-processing steps in the fMRI analysis. So you pretty much can assume that they are stationary, okay? So after we thought, how could that be? I mean, they must be smarter than that, right? They knew that this works. So we realized that we can give an interpretation of Pearson correlation, okay? A different interpretation, which is more reassuring for us to proceed and still adopt Pearson correlation. So our interpretation is the following, okay? If you look at the Pearson correlation based on the data, it's basically the angle between two time series, okay? And an angle is like a cosine of, sorry, it's a cosine of the angle, okay? It's the inner product of two normalized time series. And if we translate that, you know, making it continuous, then the product becomes, inner product becomes the functional inner product in the L2 space. Okay, so this is inner product of two function, of two time series. And with that in mind, now it becomes clear there is a meaningful interpretation of Pearson correlation. Okay, it's just the angle, the cosine angle of two normalized time series. Okay, so that makes it a legitimate connectivity measure now. All right, so that's the correlation. We need a distance, okay? So you need to sort of do the opposite, and we take 1 minus this times 2 for a good reason, okay? Because you can see here, if I look at the L2 norm of those two function, or which actually came from the two time series, since they had been normalized, this is just minus 2 times the correlation, okay? So this has a meaning as a disparity measure. Okay, so now these are the picture you have seen before. So we use that disparity measure, apply MDS to the data, and then this is what you saw a while ago. All right, and to see whether that really worked or not, okay, we did a simulated toy example. Here is the original data that was generated from a smooth process, a bivariate process over time and over space. Okay, this is time, one is space. And then we juggle it as we did before, the order, one direction, okay? So this is what you see here. After we apply the method, the MDS or the UDS approach, we pretty much recovered its structure. It's not perfect, you can see here, okay? But it by and large captured the structure. Okay, so far we just reordered the data, okay? We haven't done any damage to it. From now on, we want to, what do we do with that? It's not only for visualization, okay? We want to do something on brain connectivity. So that comes to the next topic, okay? We want to design a summary of brain efficiency, okay? And the standard way to do that is to use the minimal spanning tree for a network, okay? Because the brain connectivity map is basically like a network, okay? And people have been using the minimal spanning tree. That is just the shortest path to go from to go through all of them. In our case, our network is actually a lot simpler, okay? Because we have stringed the data together now. Okay, so we have actually a network and a path. So we redefine the brain efficiency by doing the following, okay? So go back to the, go back to the interval 0, 1. We try to rearrange the data. Okay, let's say after you rearrange that, the first location is occupied by an object, which is, let's say, x 100, okay? Then psi 1 is the location, so that would be 100, x 100, so we know that. And that's the next one, etc. Okay, so we already have an order over there. And then we just took a very simple and naive approach, okay? Since we believe that we have tried to make similar objects together, we're just going to measure, and we're studying brain connectivity, so we're just going to use the previous distance that we designed, which is 2 times 1 minus the Pearson correlation there of the adjacent object, okay? So these are, for example, you take the Pearson correlation between these two. There's a time series here, there's a time series there, okay? And then you move on to the next pair, etc. Okay? And then we average them or sum them together. That's equivalent. That is our new definition of the path length. Okay, so we don't have a real traditional network which goes all over the place. Okay, we have this simple arrangement over there. And with this path network, the next, we are going to use that to the fMRI data. But before I do that, let me introduce another new concept we developed. We developed a new community detection method. Okay, let me explain this. It's best explained over here. Remember that we have already reordered all those, we have reordered all these objects along here, right? So intuitively, we know that similar objects are already grouped together. So if we want to look for community, we thought we just look at the connectivity and see where it has a sudden break or discontinuity, right? For example, these are similar, okay, until all in a sudden we see a connectivity change. Then we will declare the previous one is a community, and then we search for the next one, etc. So essentially what we will be doing is to detect change point on the connectivity, okay? So that's our new community detection method, and this is the target, which, well, we readjust the standard community formula the standard community formula is this one here, okay? You will compare arbitrary two nodes and try to maximize this object function. We don't have to do arbitrary two nodes because we have already rearranged them, okay? So our goal is to try to group the genes together and just locate the breakpoints. We call it a B, okay? So let's say there are B communities, then there will be B minus 1 breakpoints in between, okay? And our algorithm is supposed to detect the breakpoints. And my student actually designed this. He just used the genetic algorithm to find it because it's multiple time change points. All right, and let's compare the two methods in terms of the computation. If we do the traditional or the conventional modularity measure, the number of operation is B to the power P because you have to place P objects into B community. You have to try all of them, okay? With our method, you don't have to try all of them because they have already been paired. You just need to decide for new data whether it should belong to the previous community or the future one. So it's 2 to the P in operation. Okay, so data analysis. You have seen this slide already. That's the Alzheimer's disease study from UC Davis. Okay, you have also seen this before. And okay, now these are the connectivity, the brain map over here, okay? And you can see here that, well, it may not be that obvious, okay? I don't know what you see here. This is the typical demented subject. In fact, we call it the median demented subject. Okay, what does median means? Well, the median was determined from the path length that we defined earlier. Okay, every subject has a path length. We took the subject with the median path length because we consider that's a typical subject here. All right, and that's the brain map. And this is the typical from a normal subject, okay? You can actually sort of see that for a normal subject, there are less community. Okay, and I will explain later on, perhaps an argument for that. But let's first carry out some confirmatory analysis. So we try to first test the difference between the normal and demented subject using the brain efficiency that we define, which is the path length. Okay, this is our measure. This is the conventional measure. We tried both the t-test and the Wilcoxon test. Okay. Most researchers use t-test or neuroscience. In fact, the Wilcoxon test is perhaps a preferred one to use because it doesn't require distribution assumption and is nearly as efficient as t-test and often much more powerful than the t-test. Okay. All right, so we see here that none of us were successful to distinguish the normal and demented group, okay? Because the p-values are all above 0.01. However, our method seems to be doing slightly better than the traditional minimal spanning tree, okay? All right, now we move to the next one, the community detection, okay? So we speculate that if there are a lot of communities, it means the brain is not efficiently organized. If it's an efficient brain, you don't need that many communities, okay? So we thought maybe the number of communities will tell us something about the disease, okay? So in this study, we focus on the number of communities. And there is an existing tool called Brain Connectivity Toolbox that will do the community assignment for us. So we compare ours to the baseline method, which is from this toolbox. So that's our method on the top, okay? And you can, let's go down straight to look at the p-value here. This time, both are pretty successful in distinguish. Although BCT still didn't pass the 0.05 threshold, but why should it always be 0.05, right? The bottom line is though our method is much more successful in distinguishing the normal and the demented group using the new community that we developed. Okay, so this illustrates the potential to apply or to rearrange the object. Okay, now in this talk, I use only fMRI time series just as a toy example, but since the method only requires a distance measure between any two objects, so you can extend this to any object data, as long as you come up with a meaningful distance measure. Okay, of course, a key is how to select the correct distance measure to study it. Okay. All right, and as I already mentioned before, what's the explanation that the normal subject has less number of communities? I guess our speculation is that less community means a more energy efficient. Okay, so what next? Okay, right now we did a little bit. We actually start to do post-analysis. Okay, post-alignment analysis, which I call. And originally, we actually were more ambitious. After we have realigned the data, originally we want to do classification. We want to see if we were able to distinguish the normal and the demented subject. My student tried a little bit with deep learning. At that point, we were not very good at it, and then he graduated. So, well, we didn't pursue anymore. We were not able to classify them with the reorganized map. But then we have a colleague in CS department who had a visitor from Korea visiting us. So he was in the thesis committee of the student, and he was very impressed with the method. So he thought we could try it. And then we tried it subsequently, in another data of the collaborator, Professor Lee from Korea, Yonsei University. And this time is EEG data, and we are trying to classify emotion. Okay? And we use our method to reorganize the map and then subsequently apply the convolutional neural network. And this time we had more success, but I don't have time to mention that. Okay, so if you're interested, it's in that paper. Okay, so it's time to mention the talk is based on actually 4 papers, but I really didn't talk about the 4th one. The first one is the original string method for high dimensional data in JASA. The second one is the theoretical paper for that functional Cox, but the model was inspired by the stringing. And the third one is to rearrange or alignment of fMRI time series. Here are the collaborators, very clearly split. The top 3 are the ones for the first MDS, the string paper in JASA. These 2 were former PhD students. This is my colleague, Hans-Georg Müller. Okay, the functional Cox model is jointly with Xiao Wang and his former PhD student. And the last one on the brain is with my former PhD student who is now at Lyft. Okay, that's it.
Thanks. Are there any questions?
Thank you, Jenny. Very nice talk. So one question is, you seem to be looking for smoothness in the reordered or stringing method.
Right. Actually, you raise an interesting question because we are from the FDA functional data thinking, right? So our thinking is always we want to make things smooth. But for that last one, which I didn't have time to mention, the EEG data, actually our collaborators suggest that we do the opposite, okay? So we rearrange the data and put the most dissimilar objects together. And it turns out it worked in some case. So it's not clear. I think it really depends on what are the key features if you want to apply deep learning in the end, okay? Sometimes one way is better than the other.
So for the ones you had success, can you make like a biological neuroscience like argument to say that actually smooth?
Not me. I can't really make it. I think maybe a little bit, okay? I think it really depends on the emotion. Maybe in some sense, because initially we thought smoothness is better. Because think about if you have two images, which one is easy to do classification? Originally, we thought the smooth one is easier to do classification, but sometimes not necessarily. So the key is which image is easier for classification. I don't know if that answers your question.
But the first example you gave for the stringing method, you also find kind of suggestive causal for precipitation, right? So
right. Yeah, that one is, but I mean, we didn't claim causal, okay? We just say we found a confounder, basically. That's the precipitation.
Yeah, like a possible.
Yeah, that's right, yeah.
So how do you basically look at the classification error as a way to justify whether this is
right. The final verdict. Okay, there are several ways you can judge whether this method works or not for your data. Okay, first of all, we're not claiming it works for all data. Okay, it may or may not work. But you look at your, for example, sometimes your goal is just to visualize the data, like the first example, the gene expression data. You just look at the heat map. It tells the story already, right? String split the genes into two groups. And for the functional Cox model, it also successfully split the genes to those that are detrimental versus the other group. Okay, so that's where you can claim the method worked. Okay. Otherwise, I don't think, we don't really know the answer until we have tried it. And I also like to mention that we are not the first one to apply MDS to reorganize data. I believe, Bing, maybe you have done it also, and many other people in the graphical or visualization community. We are very ignorant about that community. So I apologize if I have missed any reference over there. But I believe that we are probably the first one to think differently by reorganizing it into a functional data and do subsequent analysis.
Yeah.
Mm-hmm.
Thank you.
Thanks. Mm-hmm.
Okay, I think we will move on in the interest of time.
Thank you.
There can be more questions on chat. Is Hongtu here?
Yes, he's here.
Okay, good. Thanks.
Hongtu, go ahead and share.
All right, so I guess our next speaker is Hongtu Zhu, who's professor of biostatistics at the University of North Carolina at Chapel Hill. He got his PhD in statistics from the Chinese University of Hong Kong in 2000, and he spent some time in Columbia University before he moved to UNC at Chapel Hill. His research interests are in statistical learning, medical image analysis, precision medicine, artificial intelligence, big data analytics. He's an elected fellow of the ASA and IMS, and he was awarded the Inform's Daniel Wagner Prize for Excellence in Operations Research Practice in 2019. So today he'll talk about biobank scale brain imaging genetics, clinical and methodological advances.
Okay. First, I would love to thank Aluch for organizing this wonderful workshop. And actually, we discussed these ideas last year. He really made it. And actually, this is a very important event for, can you hear me?
Yes, we can.
Okay. For the statistics in imaging section, and hope more people, can join our session. And this is basically the joint work. It's my part-time job these days, and this is a joint work with all members of my lab, and also my former student Bingxing Zhou, and also my colleague Yunli, and also my Jason Stein, and also my friend Stephen Smith from Oxford. And actually, in the last 5 years, I've been, moving around, internationally. But one thing is I've been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one thing is I been starting to shift my focus. And one th from, to move to more forward to the data applied problem-driven research. Okay, today's talk is mainly prepared by my students and actually consists of 3 parts. The first one is big data in imaging genetics, and actually the second one is novel clinical findings, and the third part is about methodology challenges. But actually this talk is more about from the data analysis perspective. How much would be for me as a statistician, I want to show how could we do some clinical stuff, okay? And actually, I have been working in the brain image for around 18 years. I learned a lot from my collaborators. Various image modalities have been widely used to capture the brain structures and function changes associated with the major brain-related disorders and normal brain development. And in the last 10 or 15 years, one particular focus is on Alzheimer's disease. And this is just an illustration of the changes of the brain shrinkage for the people with the AD and with as compared with the normal aging people. And why do we care about the genetics of the brain-related disorders? And actually most major brain disorders like Alzheimer's disease are heritable complex trait or disease. And altogether, the genetics actually account for about 50 to 70% of the AD risk, and 75 to 90s of the ADHD risk, and 60 to 85 of the schizophrenia risk, and 80% of the ASK the risk. Okay. And actually the different brain disorders are linked to the brain regions and the function with different patterns. And actually for brain-related disease, instead of using kinds of the disease diagnosis, and actually scientists are moving towards various brain imaging related to the measures. And also the genetic signals on the brain and all the function and the structures are typically long-sparse and weak. And actually this is a typical polygenic genetic architectures. For instance, many genes contributed to the Alzheimer's disease. And to understand the role of the neuroimaging techniques, I have this brain imaging genetics paradigm. And actually it starts from genes to molecular, to the brain cells, to the brain structures and function, and to the brain disorder. And also they reverse the back from the disorders to the genes, okay? And basically we need to understand, try to use and uncover the profile of the brain abnormality in each clinical outcomes to study how does the brain disorders develop across time. And first you see that from the, we studied the gene expression at RNA and protein levels. And also we studied this molecular function and the cell metabolisms. And also we want to see how does the changes in these kinds of neuron structures and the functions, and also these changes, the neural interactions altered the brain structure and the functions. That's basically the whole pipeline. Basically, when you try to link all the information together, that's a very critical pieces. But so far, we have little understanding how does this pathway really goes. The main problem is coming from that we don't have enough data to really understand these kinds of parts diagram. Okay. And another thing, another thing we are interested in is to try to understand and the complex interplay between the brain and other human organs and their underlying genetic overlaps. And we understand that many diseases are multi-system disorders. Okay, like here I show the brain, retina, and the kidney and the heart are kind of related to each other in a certain way. Okay. And the possible causal factors of the brain structures changes resulting in the brain disorders like the stroke, dementia, and the cognitive impairment. Okay, this is one of the key reasons nowadays we also try to understand the relationship between the brain and all the other human organs and their underlying the genetic overlaps. Okay. Actually, there are three non-distance challenges, long-term challenges in brain imaging genetics. The first one is typically the neuroimaging are expensive and have similar, very limited sample size. And actually, when I started to do this research, the topic around 10 years ago, actually the sample size is pretty small, about less than 1,000 most timely. And also the second one is just because the genetic risk factors are typically dense and have very small effects, and thus needs large sample size to detect it. Okay, this is a figure to illustrate how many samples you need. And another thing is, the third thing is it comes from the data itself, because the data is typically heterogeneous. And actually, these are the major problems for us to kinds of integrate the data across the different centers, although even different scanners. And actually, we face these imaging batch effects and the confounding factors, and then we have to deal with these kinds of issues. Okay. And actually, one thing I started, because when I started my career in doing this biostatistics, actually one thing I'm luckily to work with a group of people to basically have all these different imaging data. Actually, 5 years ago, I started to connect my own data set. It's not using money to connect it. Actually, I try to go to all these public resources to get all the data set. I can put them together. And actually, things 5 years ago, I started with one particular very valuable data set is called the UK Biobank. I think compared with all the existing data sets, I think UK Biobank is one of the best in the world, okay, in all the senses. Okay, if you are working on medical sciences, this is the greatest data set you should look at, okay? And maybe 5 years ago, I talking about ADNI. I think the UK Biobank nowadays is much better than UK ADNI in all the senses, okay? And actually, one thing I did in the last 5 years, basically, I connect all the data crossing the ages from the age 0 to 5 years until these aging people and basically quite old people. And then we connect the data from BCP, PIN, ABCD, PNC, HCP, UK Biobank, RADC, and ADNI. And then we put all the data together, and then we process all the data. And actually, this is I'm luckily UNC don't charge me for all these computer hours of processing all the data set. Now I have connected publicly available individual data sets for around 50,000 individuals, and I built this large database in these areas. And actually, I can do a lot of clinical findings by just using my data set. Because you can think about it, the whole neuroimage literature, most of the data set is less than 500. Okay, many clinical findings are quite controversial, and also because there are a lot of the issues inside. That's the reason I tried to connect all the data set. I tried to understand how does some major scientific question can be answered by using much larger data set. That's one of the key motivation when 5 years ago I started to looking at these kinds of problems. And actually another thing is in order to basically to process the data, I harmonized the state of art tools and pipelines to consistently generate the full spectrum of the neuroimaging features from the MRI, diffusion MRI, and the functional data. And actually, I'm lucky because I'm working in this area longer enough to have a group of the collaborators who are leading figures in all these areas. And I can get the best pipeline, we think, and basically to process all the data set. And also we modify some of the data set for our purpose. I did give some examples. Actually, one thing we generated regional brain volumes and the shapes. And also basically we generated regional brain volumes and shapes representation from the 90 different brain regions, and also we generated for like a subcortical and subcortical the substructures and also shapes. And another thing is related to white matter microstructures. Actually, we at the beginning we basically use the Enigma stuff, and actually we characterize the 5 major white matter bundle microstructure measures, and basically include FA, MD, AD, RD, and MO, and the 423, 21 white matter tracks. Okay, and these measures are very sensitive to specific kinds of type of the microstructure changes that have been widely used in clinical research, and also we're try to use, like Jenny said, this is the functional data analysis. We're using functional PCA method to extract some of the key features of the wide matter bundles across the brain. And also another complexity comes from how to really process the resting of task function of mind. There's a lot of different pipeline existing in the literature. So many I get nothing from the. I tried many popular ones, but I finally nailed down this one. I work with my collaborator from Oxford, basically using ICA-based method to form of the 76 functional regions and generate about 1,701 functional connectivity trace to characterize the major functional brain regions and their connectivities. And actually also we try to map 76 of ICA nodes onto these AL populations, and for this well-defined functional networks. And for instance, which is the 7 networks, you use the 2011 papers and the 8 networks for you find the 2015 papers. And actually, this work I started even more than 5 years ago. I'm interested in 4 kinds of questions, and that's the reason I try to push to connect all the data set and process the data. The first one is a related association test. Basically, I try to identify and replicate the global genetic factors associated with brain structures and functions. And actually, in the existing literature, most of the publication is basically done by USC group from the Enigma group. Okay, they publish all the papers in natural science, all these natural genetics, and actually they using the group from the subjects from all across the world. They have a lot of heterogeneous issues and a lot of things. And actually, all the existing, even this year, the science paper they publish still focus on MI images. Actually, we try to push it forward. Besides the MI, we push it to function of MI and DTI. That's the reason there's no existing major finding on this topic. And second thing is I'm really interested to do causal inference and mediation analysis. I want to analyze the genetic links among the brain structure, brain function, cognitive cognition, and major brain disorders, and also we'll try to data integration. And actually, that's to uncover the biological insight. The fourth thing is we want to do predictive model, because all these imaging stuff at the end of the day, you have to basically to help us to improve the prediction accuracy for the brain-related disorders. That's the reason we try to integrate the different information together. And that's basically the first part. The second part is all these parties, this all the global clinical findings, they happen to be reported in the literature any place. And I think that's the reason I'm glad basically what we did on this topic. And actually, first things we shared all these findings with the community. Basically, our group is building the brain imaging genetics knowledge portals at this website, bigkp.org. And then we aim to build the best knowledge database of neuroimaging genetics. And actually, I'm going to add more information inside. And also, we'll try to build a knowledge graph on this. And you will see you can go to visit our website to see the results. And actually, in our QR's locals browser, you can search a database for all the 516 brain imaging traces across 3 imaging modalities, and you can search for all of them. And also, this is one of these the amplitude traits related to the resting function of MI. And actually, in the precuneus, in the major default mode and all central executive kinds of the networks. And this is the GWAS summary statistics. And actually, we have already uploaded the full set of the GWAS, the summary statistics, made free available to researcher communities. Many people download our results and they try to validate and you incorporate in their GWAS analysis. Okay. And this is one of this overview. We try to overview the Enigma DTI pipelines and also the multi-stage designs in our recent the bio-archive papers. And actually, we try to apply the same pipelines to 5 different studies. And actually, you see that when we try to process the data first, we have the first stage, we analyze the UKB phase 1 and phase 2 data set. There's about 18,000 of the British ancestor subjects. The phase 3 data set is also British ancestor, is about 16,000. And actually, we also try to combine this all those 3 phases together to nail down these kinds of 34,000. And actually, we replicate the discovery, the GWAS loci in the independent data set. And actually, then we do these good replications and try to apply the meta-analysis GWAS of all the data sets. Okay, the total number of the subjects is about 43, about 44,000 of subjects. And actually, we observed these kinds of 109 novel genetic regions. And actually, this is 151 in total, and with the p-value small, this very tiny threshold and associated with white matter microstructures. And actually, the heritability is around 45%. And actually, we find that the sample size is essential for gene discoveries of traits with a high polygenic genetic architectures. These are the typical examples. You see that when we published the first paper in medical psychiatry, 2 years ago, last year, and actually with the sample size around 20,000, we identified 40 loci, and actually the sleeper heritability is only about 12%. But now we have 40,000, actually the number of the significant the loci and also the heritability increases dramatically. And those are these ideograms of the genetic regions. And also for all these 25 knowing the genetic risk region of the GBM, the brain cancers, and actually 11 associated with the white matter microstructures. This is completely new in the literature. Nobody report this stuff. And also the genetic co-localizations among the various vascular the risk factors like obesity and the diabetes, the blood pressure, and also those white matter microstructures, and also the stroke. And this is the findings. And also we see the strong genetic correlation between white matter microstructures and the small vessel, the stroke subtype. This is the tables to show you. This is the y-axis is the DTI trace. The x-axis is basically the different disease type, and you'll see that that's basically the key messages here is mainly related to stroke. And also this is the plots related to any stroke, MDD, intelligence, reaction time. And also this is also another very strong clinical findings that we find that basically we see the strong genetic correlations between white matter microstructure and the gray matter volumes of the labyrinth regions. And this is something else also new. Okay. And actually, I work with the Jason Stein, actually, that is our colleague in genetics. And then we try to identify brain cell types where genetic variation leads to the changes in white matter connectivities. And in general, the growth of the cell type is include the neuron and the non-neuron type. Like glia, for non-neuron type, basically you have glia include the oligo and the microglia and the astrocyte. And actually the white matter is largely composed of glial cell types. And actually we do this kinds of the heritability enrichment analysis based on, this is, you see this is all these kinds of the subcortical and the cortical and the subcortical. This is a glial cell type. This is related to neuron cell type. This is also confirmed as kinds of findings. And also glial cell enrichment was widely observed in the white matter tracks and was significant in major region like posterior corolla radiator and PLLIC and general the corpus callosums. Okay, this is also glial cells and this is neuron cells. Okay. And also we do this DTI annotation enrichment. Actually, the heritability of 49 the complex traits are significantly enriched in the genetic region influence white matter microstructures such as stroke, schizophrenia, ADHD, bipolar, Alzheimer's disease, T2D, high blood pressure, and the coronary artery disease. Okay. And this is the related function from resting function. Actually, this is the DTI. I didn't spend it, and actually the function for my took much longer time because the data is very noisy. We spend a lot of time trying different pipelines. And actually, this is we found that our findings is quite related to these well-known the kinds of the triple network model of psychopathologies. And actually, the salience network play a critical role in dynamic switching between the central executive and the default model network. Okay, this is the default model networks, and the salience network is the central executive networks. And actually, these three called function networks that support the effective cognitions and that relate to the major brain disorders such as the AD, PD, and the MDD, and all other disease. How many minutes I have?
I guess a couple of minutes.
Okay, I try to go first. And actually, also we observed the higher heritable than these other function networks like motor and visions. And then you see this is basically within the triple networks and the other side of the triple networks. And also the genetics of the functional, this is the functional brains. With this is the ideograms of the local influence of the resting functional traits of intrinsic to the brain activities at this levels. And also we see these kinds of co-localization with the Alzheimer's disease and the schizophrenia. And this is basically the typical, the well-known genes, the ApoE, and it's associated almost all these kinds of the brain-related disease. And the ApoE has a stronger, and what this is also completely new findings, is basically ApoE genes has a stronger genetic relationship with the brain function than the brain structures. Okay, this is a very surprise to me when I first saw these kinds of results. And also this is, we see the co-localization and these typical regions, because these typical regions are associated with almost all the brain-related things like neurological disorders, psychiatric disorders, education, cognitive ability, psychological traits, and alcohol use disorders. Okay. And also we also see this co-localization with the sleep and the cognitions. And actually, they also the resting functional stuff also have their stronger genetic overlap with the brain structures. This is the shared genetic influence between the functional connected to the default motor worker and the executive network and the insular volumes. Okay, and this is the insular regions, and actually, and you can see that there's a highly genetic spatial co-localization between the brain volumes and the genetic correlated functional connectivity traits. And also with these, the shared and the basic genetic influence between the brain structure and the structure the images. Actually, we see this genetic evidence on how distributed functional networks communicate among across larger distance. And this is the basic related to these regions whose the functional connectivity genetically related to the brain disorders and intelligence like ADHD, MDD, schizophrenia, and intelligence. And also we try to integrate the genetic gene expressions to PIS. And basically we find that basically the truly we try to construct a gene-based PIS and the scores, but leverage gene expressions reference panels in T1s analysis. We see basically the prediction improved in some particular disease type. And actually, this is just the beginning. Actually, at the very beginning, I suffer a lot when basically write papers with just a few thousand of subjects and get rejected almost everywhere. But now I have all these data sets, process all the data, and basically now this is just the beginning of this story. And the genetic discovery in brain by big data integration, that's the training make it possible because of the people are nowadays sharing all the data across the world. And as this is ongoing future directions, we are looking for the causal relationship among disease, brain structures, and brain functionality. We try to build optimal models for complex traits and disease prediction. And using imaging and genetic data, we try to compare and identify the best practical strategies or pipelines for process of different neuroimaging modalities. And you know, I think maybe next year I finish my book, I can share all these things with everyone. And I also try to model the brain's changes and the genetic impacts, effects across the lifespan, align those integrated different imaging modalities. And the last part should be simple because this is one of the papers published by my two collaborators, my friends, basically talking about the brain imaging genetics and learning problems. He basically classify this is three group of the research, learning problems, and the biological application and statistical learning kinds of the considerations. And this is one of the research topics that we are working on related to the multi-biobanker integration, omics data integration, new computational tools, and advanced method for density signals. But for us, all this methodology has to build on the data set we try to build. That's the reason we try to work on. And also this is the etiological layout for our group. Basically, we're working on 4 set of problems, like the convolution, integration, learning, and prediction by using all kinds of statistical methods and of deep learning, reinforcement learning, and causal inference. And thanks for everyone. And the reason I put the Purdue inside just because my student just moved to Purdue as a faculty. That's the reason I have to put it. Thank you. Any questions you can ask?
Yeah, are there any quick questions?
I just want to say this is seriously impressive. Wow.
Thank you.
Yes.
That's my part-time job.
I apologize. You needed more time, and next time you'll get more time. But okay. I look forward to learning all this from you.
Yeah, I just share what we did in the last 5 years.
If you did all this in 5 years, then
no, more than 5 years. It's be fair say that in the last 18 years, I accumulated all the knowledge in the last 18 years.
I mean, a natural question here is that now, of course, you have a tremendous resource. You said data, organized, large data. That's a real gold mine. So, I mean, as it happens in medical imaging, people who possess the data restricted, the data because they could publish it before anybody else could, and that's natural. That's fine. But what's your plan with this data? Is it public at any stage?
No, this all the data public available. It doesn't belong to me. You guys can.
No, but you have organized it. I mean, this is now you have registered, you have extracted structures, you have put timelines, you have done it across the databases, across data banks.
Yeah, that's a ton of work, my friend.
I know.
I don't. All these sites doesn't allow me to share my data sets. Okay. But from I have to either upload my data, process the data to their website so that they can share the data.
Okay.
Because I technically I'm not allowed to do that.
Yeah, no, I'm saying
we can collaborate with each other. That's fine.
Yeah, no, I understand. No, between you and I, we are fine. But I'm just saying this is for a community. I think medical imaging community took off only when the data became available to people who would not see it otherwise. Until then, it's just Hopkins, Harvard, and Washington University. That was it.
All these data doesn't belong to me, except to the first data set we connected. For other data set is basically I got it from the website. I just applied all the protocols. I just started earlier than other people. That's it.
Yeah, but Anuj is right. It became available over the past few years. Previously, it was not possible to get a hold of such data.
Yeah, I think Anthony, but all these data set, when I applied, the data set are available to other people, researchers. It's not about for myself. I have more data set than this like listed here. Just
sure.
That's another side of research. But I think for brain imaging related research, I have all these data set available. And I have other data set related to this, but I didn't list it.
Right. I think we should move on to Marina. Thanks again to Hongtu for the talk.
Oh, I need to log out.
Yeah, if you can please stop sharing your screen. Okay, good.
Okay.
Right. So our next speaker is Marina Vanucci. She's the Noah Harding Professor of Statistics at Rice University, and she's had prior appointments at the University of Kent and Texas A&M. And she received a PhD in statistics from the University of Florence under the guidance of Antonio Moro. Her research interests are in Bayesian statistics, variable selection, graphical models, statistical computing, wavelets, with applications in genomics, chemometrics, neuroimaging, and engineering. She is fellow of the AAAS, the ASA, IMS, and ISPA, International Society for Bayesian Analysis, and elected member of the RSS, the Royal Statistical Society, and the ISA, International Statistical Institute. She's also the past president of the ISBA and former editor-in-chief of ISBA. Not ISBA, I'm sorry, Bayesian Analysis, the journal. And she's currently the co-editor of the Journal of JASA. So, and today she'll speak on Bayesian approaches for inference on brain connectivity networks.
All right, thank you. Thank you for the nice introduction. So yes, I will be talking on this Bayesian methods for the estimation of brain connectivity networks. And I'll just briefly introduce brain connectivity. I think we have seen brain connectivity throughout this workshop and also the different type of data that we can use. So I'll move very quickly to the approach that we have proposed, which essentially uses vector autoregressive models, which is one of the ways that we can estimate what we call effective connectivity, so directed connectivity. And I'll show a model which allows to handle multiple subjects data and data that divide into different groups. So that the model produces inference both at the group and the subject level. And in Bayesian, we will exploit the approach by essentially using special priors that allow the incorporation of external information. Here in particular, we can incorporate multimodal data into the inference. And then I'll conclude with just some just brief comments about dynamic connectivity. So the model that I will be presenting is static, and I'll just mention how we can make it dynamic. Okay, so we have seen in a number of talks, we saw David Danson today, and also we saw this data, David Danson yesterday, but also we saw this data today. We can estimate what we call structural connectivity based on data such as DTI or MRI data. But today, my talk, I will focus more on the type of connectivity that Jane Lin was looking at, the functional or effective connectivity, which we can estimate via fMRI data. What Jane Lin was looking at was more what we call functional connectivity in a sense of undirected association, or to a statistician, just temporal correlation. But in my talk, I will be more looking at what I what I'm referring to as effective connectivity, which is directed connectivity, which is direct influence of a brain region on other brain regions. And I will be looking, there's a lot of literature on connectivity, both functional and effective, lots of different methods to estimate connectivity. I will be just focusing on sort of graph-based approaches to connectivity, to the estimation of connectivity networks. So again, effective connectivity as directed influence. I think in the literature, there's a little bit of misuse of these terms. I see a lot of people referring to functional connectivity as including effective connectivity. So I'm going to make this distinction today that effective is directed. Okay. So we can estimate functional and effective connectivity based on fMRI data. So again, as I just said, I'm just going to briefly mention graphical model-based approaches to the estimation of functional or effective connectivity. For functional connectivity, we're basically looking at an undirected graph. And so obviously in the frequencies world, a lot of the lasso type techniques come to mind, and they have indeed been applied to fMRI data to estimate undirected graphs, both the kind of generic graphical lasso, but also extensions like the group and the fused lasso. There are some Bayesian models that have been proposed to estimate a graph, an undirected graph based on fMRI, so essentially just Gaussian graphical models that use special class of priors that we use to induce sparsity. Today, as I said, I will be focusing more on methods for directed connectivity, and in particular to the class of vector autoregressive models. Again, when we talk about effective connectivity, there are many different ways of estimating effective connectivity. So VAR is only one class of methods that we can use. So I'm kind of just focusing throughout the talk on the pieces that I need for my work. Vector autoregressive models for the estimation of effective connectivity, and I'm going to show you this Bayesian model, which is an extension of some previous work done by Gorostieta and Hernando Ombao, and I think Mark Fiecas also. But the method is extended to handle multiple subjects, multiple groups, group and subject level connectivities, as well as the incorporation of external information, which we achieve through the prior structure. Okay, so starting from the model, so if xt of S is the vector of fMRI bold signal at time t for subject S, we assume to have a parcellation of the brain. This is also something that Jane Lin spent some time talking about. When we talk about connectivity, it doesn't make sense to think about voxel level analysis. We're not interested in seeing how voxel connects to another voxel, but people tend to parcellate the brain into regions of interest as like groups of voxels, and the region makes sense. It has a certain interpretation to the practitioner. And so the interest is in inferring a network, in our case, among these R regions of interest. Here we assume to have multiple subjects and to have groups of subjects. So you would typically have a healthy group versus a diseased group, for example. And so here in my notation, eta is the label for, eta S is the label for subject S. And this is, here on the slide is the formulation of the multivariate VAR process of generic order L, although with fMRI data, because the time resolution is not that great, usually people looks at leg 1 or leg 2 at most. But so with the generic lag L, this is the model formulation where conditioning for subject S, conditioning upon the class membership of that subject. This is the formulation of the vector autoregressive model. And parameters of interest here are those coefficients here, the VAR coefficients here. In this formulation, I have a matrix phi R by R of VAR coefficients that capture the leg-specific effective connectivity, so the direct connection between the two regions that the coefficient points at for subject S. So those will be the parameters of interest in our Bayesian modeling. Typically with it is typical with VAR models to work with vectorized coefficients. So here I'm kind of changing notation now to use beta GS, which is the vectorized subject level vector of effective connectivities for subject S in group G. So essentially I took the phi matrix and I vectorized that matrix. And then I'm going to assume that, again, for subject S in group G, the subject level parameters are modeled as random deviations from a baseline process. So I'm assuming a Gaussian distribution centered in omega G, which is now the group level vectorized subject level sets of connectivities at group G. So now I have two sets of parameters. I have my set of connectivities at group level G, and I have my subject level set of connectivities at subject level as simple deviations from this from the overall from the group level mean. The next step, so I have the two sets of parameters that I need to estimate essentially connectivity networks both at group level and at subject level. So the next thing is to utilize priors, and here in particular I'm going to use priors that impose sparsity so that I will effectively estimate a network at the end of the day. So I'm going to assume, I'm going to use the so-called spike and Zilla priors, which are a class of priors that we use in Bayesian statistics to essentially impose sparsity. So I'm going to impose sparsity at the group level while allowing the subject-specific connectivity to deviate from this group mean. So focusing on the group level and the parameters omega, for the individual connectivity omega k in group G, I'm going to assume a spike and Zilla prior, like the one that you see in the fig in the slide. The idea here is to introduce binary indicators. I have here gamma k G, which indicate whether connectivity K is active in group G. And then the prior is actually a mixture distribution, and the mixture is indexed by this binary indicator. And the mixture has two components. One component is a spike and zero. So this is the Dirac density at zero, which essentially will set that connectivity to be zero for group JG. And the slab portion of the spike and slab is actually a Gaussian distribution where we actually used an ICAR type of prior because we try to encourage some smoothness across regions and for same regions across different legs. So again, when gamma k is equal to zero, the prior and the posterior on the corresponding connectivity is zero. And then when gamma k is equal to 1, then there is a prior on the corresponding connectivity that tries to enforce some smoothness across region. Then with this construction, we have introduced an extra set of parameters. And so as Bayesians, we'll continue to put priors on the unknown parameters. And in particular, we can impose a prior on the binary indicators as well. Here is where we can kind of exploit the construction by essentially making the model multimodal. We can consider prior for gamma that essentially allow us to incorporate additional information. You see here, for example, a probit type of prior. You can also use a logistic prior, works similarly. And the prior depends on a set of on a set of additional covariates, right? And K, that can be extracted from, for example, structural data. So if you have DTI data, you can think about using your FA type of measures here, or if you have just MRI data, you can just use Pearson correlation coefficients among, for example, volume measures. I'll say a little bit more in the applications. But so again, the idea of the prior here is that I'm allowing, I'm actually encouraging, okay? I'm encouraging a connectivity, okay, where there is evidence of structural information, okay? So this prior, we say that the prior probability of gamma being equal to 1, so a prior probability of a non-zero connectivity is a function of whether there is evidence of structural information as well. The construction depends on some additional parameters, and in particular, I think it's worth pointing out the sparsity parameter, alpha 0, which is the way that through this spike and Stella prior, that's the way that you can impose sparsity in your network, or you can sort of control the level of sparsity in the inferred network through the specification of the sparsity parameter. You can have an hyperprior on it, or you can just set it and then do some sensitivity analysis to this parameter. So that's a nice way of imposing sparsity through the process. Initially, when we implemented this model, we just, as a first try, we just went ahead and do an MCMC implementation for posterior inference. The MCMC is pretty straightforward if you are acquainted with the spike and slab prior and the sort of sampling algorithms that we use for this type of priors. So it's easy to implement an MCMC sampler here. The output from the MC sampler, the output of interest of the MC sampler will be, again, the group level connectivity network, as well as the subject level connectivity networks. And then the estimate on the binary indicators of the spike and slab essentially allow us to recover the sparsity of the networks. So this implementation was pretty simple and to do. The cons of the MCMC is, of course, the speed, right? And we kind of realized it right away when we try to analyze data. We had at that time, I'm not going to show you results on that data, just I have this slide just because it allows me to make a couple of points. But at that time, we did an application to data on temporal lobe epilepsy. We had a group of healthy controls and a group of temporal lobe epilepsy patients, and it was immediately clear that we could not handle the full parcellation of the data just because of the MCMC being too slow. So at that time we resorted, and we have seen some today as well, we resorted to use to the use of ICA components, where essentially you take you take ICA and then you try to infer a network in the ICA domain. And here in particular, we look at a small number of ICA components, 6 of them. They were kind of those pointing at the resting state networks, because those are notoriously implicated in epilepsy. So we sort of had to provide some rationale for doing a data reduction essentially before being able to run the MCMC. We also did not have available DTI data, and so we used structural information from the MRI data, which you have always available when you have fMRI. And so we used as structural covariates Pearson correlation coefficients between gray matter volumes of each pair of components. But later on, I'm going to show you a different application where we did have DTI data. And also, we imposed very little smoothness, because working with ICA components, they are independent, and so the smoothness of the prior didn't make much sense. So we just imposed sparsity across connectivities that were sharing a same node and same connectivities across different legs. Okay. But so as I said, this kind of application kind of made us realize the shortcomings of the approach. So the next step for us was to try to build upon the scalability, and one way that Bayesians can scale up their models is by sacrificing essentially the MCMC, by forego the MCMC for approximation methods like variational Bayes that would not provide a sample from the posterior. So in that sense, they have limitations, but they allow you to speed up the inference. So we worked quite a bit to make this happen. And so I had a second student working on this. And so we looked into, as I said, variational Bayes, which turns the inference into an optimization problem. So again, we lose something. I believe, as a Bayesian, we lose something when we do variational Bayes, because we no longer have a sample from the posterior distribution, but only in approximation. But it's very powerful set of techniques if you want to scale up your Bayesian models. Also here, we are not looking at estimating variance parameters, which is one of the drawbacks of the variational Bayes, right? So it seemed kind of a nice, ideal approach for this type of methods. And we looked in particular into mean field variational Bayes. I think we have seen this sort of methods a little bit yesterday, so I'm not going to say much. So we use kind of standard mean field variational Bayes. The idea here is to look at an approximation of your posterior, which actually fully factorizes over the parameters of interest. And in Bayesian statistics, these construction work very nicely with the idea of conjugate prior, conditional conjugate priors. So in a model like the one that we have, where we have a set of conditionally conjugate priors, we can easily implement a mean field variational Bayes by keeping that structure, which is very nice. Once we had the variational Bayes implementation, we went back and made sure that it was giving the same results as the MCMC, right? Because the MCMC is kind of like, the gold standard for us. And so we did things like, for example, small simulations, because we want to run the MCMC. So with only 10 nodes, we looked at simulated data, and by averaging the results over a certain number of replicates, we actually could see that the variational inference works pretty well in this setting. As I was saying, we're not looking at estimating variances. So if you can look at the measures on the slide, you can see that actually MCMC and variational Bayes kind of provide very similar answers. So we were kind of like, we felt good about having this tool. This scalability was really impressive. For 10 regions, the MCMC will take 40 hours. The variational inference will run into 1 minute. So at that point, we could really look at applying these methods to the full parcellation of the brain with 90, 100 regions. And the next step in the process was that now that we had a method which we thought was valuable, was to try to make it available to the practitioners. And so my student also worked on a MATLAB GUI, which we believe is user-friendly. So it's called Bivar Connect. It's available through my GitHub. As I was saying, it is user-friendly, has a couple of interfaces, one for model fitting and one for visualization of the results. Through model fitting, you just ask to input the data. You can input the parcellated fMRI data, any type of structural information that you want to incorporate into the prior. And then there are some prior settings. The GUI does provide suggested prior settings for all the priors and all the parameters. So the user can just use the default setting, or you can specify the prior yourself. And then you can use the visualization interface to draw kind of very simple connectograms. My student did work quite a bit to try to make nice connectograms. Eventually, something that we decided to do was to allow for the GUI the option of exporting the output from the variation, so exporting the connectivities essentially, both at group level and at subject level. So then essentially the user could just take the connectivities and then use any type of commercial software to make nice connectograms. Okay. And there's a paper coming up in neuroinformatics that describes the GUI. And so, okay. So with this GUI, you know, we have been looking at all sorts of data, but again, the hope is also that, you know, that other people may be able to use the GUI in their own research. But here in Houston, so like I have several collaborations with people in the medical center. One of the latest one was with the investigators working on pediatric TBI, traumatic brain injury. So we analyzed data for that group. They had 70 pediatric TBI patients and 50 healthy controls. They had fMRI, and here they also had DTI data. So we were able to use structural covariates that were summarizing the DTI information. And here you have, you know, just the output showing part of the TBI network, the part of the network that we inferred for the TBI patients. This is only a portion of the full network, is the default mode network, because it is of interest in traumatic brain injury. The investigators also had a set of, I should say, traits, a set of covariates, like post-concussion symptoms and measures of anxiety. They measure lots of things on these kids. And so we also try to see how predictive of these traits the inferred connectivities were. This was done in kind of a two-step approach, right? So it was first applying BVAR Connect to estimate the subject level connectivities, and then regress essentially the subject level, the traits on the subject level connectivities to see if we had found sensitive neuromarkers. In terms of future extensions, this application kind of provides perhaps us with, like, you know, a good idea of where we want to go. It would be nice to have a model now that incorporates the covariates directly into the estimation of the connectivity networks. And so this is certainly something that we will be looking at as a future direction. And also talking about future direction, one obvious limitation of the model so far is that it's only static, right? So we can only estimate static connectivity, both at the group and at the subject level. But if you look at the literature out there, there is a lot on dynamic connectivity. I mean, I think it has now been established that indeed connectivity is dynamic, right? It changes along the time, both for subject at rest and also subject doing tasks. There are different ways of making models dynamic, or different ways of estimating dynamic connectivity. The naive approach would be to use sliding window, where you certainly you choose a window and then you slide the window along the data temporally, and you kind of you use your method of choice to estimate a connectivity network within the window. Like, for example, you can use GLASO, and then you can use something like a clustering method at the end to sort of find the hidden states, the repeated connectivity states that you have estimated. A more sophisticated version of this is to think in terms of, as I was saying, hidden states, and therefore to think in terms of a hidden Markov model rather than doing a naive sliding window. You can incorporate essentially a hidden Markov model in whatever modeling you are doing. And here the idea would be to essentially be able to simultaneously estimate the hidden states, so the change points of the hidden states, and the connectivity networks that correspond to these hidden states. And the approach has, in my view, many advantages over the sliding window. Like, for example, you can estimate same connectivity networks over non-contiguous time points, because you could have two states, a state that repeats later on. So you have two chunks of data that would contribute to the estimation of the same network, which doesn't happen when you slide the window. This idea of incorporated hidden Markov models is out there. We have been using it in my group to estimate functional connectivity, where we were looking at undirected connectivity. So a simple GGM, a Gaussian graphical model, which we augmented with this idea of hidden Markov model. And essentially, you can sort of build that framework as well as a hidden framework to the VAR construction, something which we know is called switching VAR. There is something in the literature that has been mainly looking at single subjects. So doing it in our modeling framework would allow to have essentially dynamic networks, both at group and subject level. So we think there could be an interesting extension for the next generation of BVAR Connect. Okay, so I think I'm good with time. So I can just read my conclusions. So again, I've focused on brain connectivity, directed brain connectivity or effective, and also on a specific class of models to estimate effective connectivity, the vector autoregressive. And I've proposed a Bayesian construction that allows to infer connectivities both at group and at subject level. The construction uses sparsity priors that we use as Bayesian statisticians to impose sparsity, and also it incorporates external information. I was using structural data, but I think the prior construction is flexible enough that one could think about different information. And we have resorted to variational inference to scale up the models. I did not show you anything on comparisons or simulated data, but in the original paper, which was back in 2017, we actually did a simulation study and we compared our model to kind of the naive approach of what practitioner would do to estimate connectivities over multiple subjects or groups of subjects. It's a two-stage approach where they do an estimation at subject level, then they take the estimates of subject levels and they aggregate the estimates into a group level estimation with via t-test and so forth. And so in that original paper, we actually did a comparison between our fancy way of estimating simultaneously group and subject level connectivities and these simple two-stage approaches to show that indeed there is something to gain there. The accuracies, as you can expect, is much better when you try to do a simultaneous estimation. I think I'm done. The last slide is just the acknowledgements. The work was initiated with my student Sharon Chang. She was an MD PhD student, which was incredibly beneficial for me to be able to get into neuroimaging and in particular studies on epilepsy, which was her interest at that time. And she's now a neurology resident at UCSF. And then the student who works on the variational based implementation and the MATLAB GUI was Eric Cook, who finished last year and is now a senior scientist at Merckx & Co. And I've also briefly mentioned that the work that uses HMM with undirected graph, which was done by my student Ryan Warnick, and all work is in collaboration with Michele Guindani, who is a professor at UC Irvine. And these three people down here are the collaborators here at the Texas Children's Hospital here in Houston that provided the TBI data for us. And that's all I have. Thank you.
Thanks. So I guess there are a few questions on the chat, but it's not completely clear. Is the sensitivity analysis question? So there are, so there's a question on, did you do any sensitivity analysis on the priors?
Yes. So in the in both papers, both both the 2017 and the 2021 paper, we do sensitivity. We always do sensitivity. It's very important when you use the sparsity priors, right? Because you have these parameters that essentially impose sparsity into the model. So we always do sensitivity to that choice. Yeah.
Sure. So I had a couple of questions to myself. One is a practical question. So these TBI children that you had, so they had similar injuries?
Similar what? Sorry, injuries.
Injuries, traumatic injuries in the brain.
Yes. No, they had. We divide into mild. They have traumatic and mild, or severe and mild. Yes. So they have different types of injuries. Yes, and we have some covariates also on the type of injury and so forth. It's an interesting data set, particularly because of the availability of the covariates, which we have not exploited well yet. But yes, they had different severities of injuries. Yeah.
I see. So another question I had was, I mean, so you have these done only on regions, right? And I understand this is what I'm going to suggest is probably impossible. But can we actually do it at essentially a voxel level? I mean, it's a horrendous problem, but I mean, that's the way we will find connectivity in new places.
So, okay, yes, definitely. Okay, let me say this. We can handle more than the 90 brain regions that you get from typical atlas, right? 91. Sure, yeah. Essentially, we can certainly handle more. I don't think we can handle, like, the very fine box or
yeah.
We could, like, any other way of parcellating, even taking larger cubes, right? Just artificially, manually, we can certainly handle that. We can handle a much bigger parcellation.
Oh, sure. Yeah. So right now you're taking regional, so you're taking, I mean, so each region you're compressing it into one number, right? Essentially.
Yes.
Okay, I see. Yes. And how do you do that?
It's also because at least the collaborators that I work with, they wouldn't know how. I mean, for them, like, they look at their atlas, they know what that region is, they know how to search the literature for their particular region, right, of interest, and so they wouldn't know how to interpret the network otherwise. So I think it's just probably just because of the collaborators that I work with, that they prefer to have upfront a parcellation. So they parcellate according to an atlas that they like, and then they average. I think Jane Lin mentioned this, right? You just average the time series across.
Yeah.
So
the 90, yeah.
We actually didn't average over the entire region. We select the seed voxel first with a method, and then we average around the seed voxel.
Okay.
But I suppose one could also do the overall averaging. Yeah.
I think in my case, they average overall. Yeah.
I see. So Ting Ting has a question, and her question is, in this study, what are the advantages of effective connectivity over functional connectivity studies?
Yeah, I mean, they give you the directionality, and actually in the paper, the one that it is submitted to human brain mapping, there is some interpretation of the directionality as well. Again, the collaborators were able to kind of search the literature and kind of find a nice way of interpret, because it was one of the questions from the referees, right? I mean, edges are directed. Can you say something? And they were actually able to look at that and find an explanation for why you think that the connectivity should have that direction. So I think from a statistical point of view, it's just something else that you give to the investigator, right? I mean, it's part of your output, and then it's up to them to interpret, right, what that arrow is. It's just something, that makes your inference richer from a point of view.
Right.
I think we should stop now.
Okay.
There are plenty of good questions still unanswered, but hopefully Marina can handle it.
Yeah, we can answer. Yeah.
Thank you.
Thanks Thanks, Ranjan, very much for chairing this session, and thanks to all the speakers in this session.
Yeah.
Very impressive work, and there's a lot to think about. Let's take about 10 minutes break. We will start again 3:30. Last session, I promise you, the most exciting session we have saved for the last. Please come back, and we'll have a good end to the workshop. Thank you very much. Let's take a 10 minutes break.
So this is a question for Marina and Jianling. Have people done comparative studies of these different ways of establishing connectivity with the same data, just to see how the connectivity might differ or consistent? I think that would be quite interesting. Has anybody done that?
The different type of data, you mean structural and functional?
Yeah, either just like have the same data, different methodologies applied. I think would be very interesting to see. I mean, I'm kind of getting into this area.
Yeah, I think
like which one?
Yeah, Bing, you raise a very good point. I actually was, I have a lot of frustration because every day I see this new paper, right? They find this and that brain region significant based on this and that method. And, you know, for the Alzheimer data, we beat it to death. It was very hard to find any signal or any meaningful message from there. So I think you're right. The ultimate test, whether it can sustain a different methodology and still reveal some shared commonality in the findings.
Yeah, I get one suggestion for unusual, the people organizers or the people who have been here longer. Would be nice to have like new data set and do a like a challenge for different groups, and then maybe can really write it up for statistical science. I mean, I can talk to, I'm actually on the editorial board. I can take the initiative to ask the editor, Sonia, to see whether will be something kind of as outcome of this workshop, just to help the new people to really orient themselves and also do some comparative studies of the different methods. That's one thing, you know, you can see I push for stability because I generally have this problem of all the people I like and they do different things for the same type of problems. And if I come in new, it's like, which one do I follow?
Yes, yeah, no, that I think that would be interesting, definitely, yes. I want to mention that for the way that I did the integration of the two data is only through the prior, right? So, and the prior just gives an indication or a preference, right? You say there could be a higher probability, prior probability of a functional connectivity if there is a structural connection. But then the posterior, you can or cannot find that connection has been present. So I think it's a nice way because you have a prior and then you have a posterior distribution. You can kind of see if there is if there is agreement in the posterior distribution, right? So then you have
sensitivity analysis. There's also cross, somebody who doesn't take the Bayesian approach. So for me, I would intend like if you have a network and Jianling has a network on the same data, I would just look at where you guys agree, right? Two opinions I trust, and I'm going to only trust when you guys agree, right? That's what I would do, right? That's what you talk to two doctors and you try to find some commonality. And that would be a more reliable link, I would think, I hope, than each of the different methodologies.
Right. You probably saw this, right? They have done this crowdsourcing with analysis, 100 different analyses. How many different outcomes?
100?
Right. Yeah, I think that would be really interesting and see, or at least which methods agrees with each other's.
Yeah, I think it's really helpful. I think statistical community, we can really help to orient people to at least have some serious comparisons, and other people can say, oh, this is more reliable. It just look like reliable from what I could tell, and I'm going to go use it.
Right.
Yeah. So I think for Alzheimer, that's what I'm starting to work with UW on that. And my neuroscience collaborator telling me that here in Berkeley, like, oh, this red state things are not very reproducible. And I was doing some private chatting with Moo too earlier. and he kind of agreed that it's a problem.
Yeah, we haven't tried.
But
sorry, go ahead.
No, go ahead. Yeah.
Oh, no, I just was talking about the Alzheimer's disease data. I mentioned that we couldn't pull it off by just classifying the brain image per se. And I think that was probably too ambitious because I don't think you really can extract information directly from the fMRI time series. I don't recall anymore whether we try just the connectivity map. That might be more promising to do. But also at that point, we were not very good at deep learning. No, well, the most recent paper, we succeeded mainly because we have the help from collaborator. And this also supports the concept of people working together, right? Those who are better at one technique can do it, and we can provide the basic statistical approach to it.
Yeah. Yeah, I also like all the data Hutong has collected. And even if it's possible to share and the platform will all apply.
Right. If Hontu can put one data set up, then we can all work on that and see what happens.
Actually, there is open neuro nowadays, which is quite
all the
good.
data sets on the public.
Yeah, that's right.
It's true.
That is right.
That
is right. Sorry.
No, but I think the curation would be good to also have some standardized curation. Otherwise, everybody does different cleaning, and then you still end up.
Yeah. No, but Open Neuro has public data sets, and they are curated.
Right, but for example, you know, we have our own method of finding the seed voxel, right? And somebody else may have a different method to find the seed voxel, etc. So, of course, maybe the method does depend on which method you use to parcellate the brain, etc. But still, a common platform that we don't do anything. Just give us the data, and we will run it and see what comes out of that.
I think that eventually we try to move to that directions. But I think at the current stage, you know, I think that it's very important to get more data set. Like actually the UPenn, they have a new consortium about Alzheimer's disease. Actually, what in that studies the canal imaging genetic data, and actually there's also large number of subjects. I think that's also valuable kinds of resources. People are interested in Alzheimer's. That would be great data set to play with. But I think I eventually will upload all my processing pipeline to public, and but I need to clean that up.
But maybe the ASA section can have some website where all this can be shared, and we can all go there, look for the updates of either the processing, or maybe ASA, this section can have a GitHub repository, and we can all share codes, and then also information on new sources of data.
I think that's durable. Actually, we discussed these issues last year, and because I think I really want to push this topic forward for the statistical community. Well, I think one thing is the data set itself. The second thing is the best processing pipelines, and they can play with it. And I think then the third thing is we need to contribute a different method and standardize the things, so that I think the people can really work with collaborators to produce the best results. And so that we can attract more fundings for the statistical community. I think that's the best practice for us.
Yeah. I mean, it's both best, but also most robust results. When you have data change a bit, the collection change a bit, things are still robust, than just tailored to particular data. So we're working with the NeuroHub. There's a new consultant between UCSF, Berkeley, and UW. It's called NeuroHub. So my group is trying to do something on the standardization or quality control process. But if ASA, this section has something we can build on, that'll be very helpful, or just the knowledge in this community. Somehow we can take advantage. We have our own like PCS pipeline, but that's usually for IAD type of data we have experience with. And we have
I think this can be done, and they just need people to, we need to organize together to do something on that. Yeah.
So does the ASA section leadership have any interest in that?
Aluch? Are you still chair president or chair? Something he disappeared.
For another few weeks, actually.
For a few weeks, right?
For another 2 weeks. Anuj, are you still the
3
kind of
weeks.
chair for statistical imaging?
Anuj, we have a task for you while you were away.
What's that?
So you are
I
asked
need
to set
vacation after this.
Well, before that, you do the task. Anyway, so set up a repository where people can put in their codes and processing things. So that's why we discussed it while you were away.
It's a great idea, and I'm sure somebody will do it.
Who's the next chair?
Oh, I'm the next chair. Hi, Bing. How are you?
Oh, hi. Oh, Ying is next chair. Great.
Yeah. So let's start.
So we should talk.
Oh yeah. So now is the time to start.
I think we can start, but as you told me, let me just tell everybody your internet connection is not reliable. So if for some reason you zoom out, I will take over.
Okay.
Just as a backup, but I
Yeah,
would
that
rather
is very safe. It started yesterday, so I don't know what's still trying to. I probably will call the internet provider. Anyways, we start now, right?
Yes, please go ahead.
Okay. So welcome back. Session applications and statistics. So I know during this talk, they are all very amazing applications, and they use from like adding public cyclone to biometric data and also brain network. So our first speaker is Lee, Professor Lee. Actually, she's an old friend of mine from Management University, and she's going to understanding the evolution of tropical cyclone convective. Very interesting phenomenon. Okay, so Anli, can you your screen the talk? For those who have questions, you can type in the chat box, and then I will ask questions.
Okay. First, thanks so much, Jingnang, and to Anuj.
Anne, have you
Yeah?
shared your screen?
Oh, it's not being shared?
We can see the.
That's fine. We can see it.
Do you see my first slide?
All good. Go ahead.
Oh, okay, good. All right. So thanks so much to Anuj and the organizers for inviting me. So it must have been at least 10 years since I gave a talk on image analysis to an image analysis vision audience. So it's wonderful to see some familiar faces again. So this talk will be on satellite imagery and tropical cyclones. And I chose this topic. Let's see if I have the cursor here. There. I chose this topic because it's a great area of research if you're interested in statistical image analysis and interdisciplinary research. So Trey McNeely is an amazing student of mine, and Kim Wood is our tropical cyclone expert and collaborator. Oops, so I'm not able to paste. Let's see if I can. Sorry. Oh, that worked. Okay, so this work is part of STAMPS, which stands for Statistical Methods for the Physical Sciences. And this is a research group we started at Carnegie Mellon a couple of years ago. You're very welcome to join our public webinar series, which is listed on our webpage. So STAMPS develops statistical methods for analyzing large and complex data arising in the physical sciences, such as astronomy, particle physics, climate, and environmental sciences. So today I'm going to talk about meteorology and satellite imagery. So tropical cyclones are rapidly rotating systems, and they form over the warm tropical waters. And because they develop far from land-based observing networks, geostationary satellite imagery are really critical to monitor these storms. And a few brief words about the anatomy of hurricanes. So hurricanes basically draw the energy from rising moist air, and deep convection intensifies the storm. So you get faster rotating winds. And infrared imagery, like the ones here, they serve as a proxy for convective strength. So they're basically measuring the temperature at the top of the clouds, because the infrared radiation does not penetrate the clouds. So the deeper the convection you have, the higher up the clouds are, so the colder the temperatures, which are sort of shown here as dark here. And so to the left here, you see Hurricane Edward as a Category 2 hurricane. And you can see that it's sort of like highly axisymmetric and very organized. It's like tightly organized. And to the right here, you see Hurricane Nicole after they had weakened to tropical storm. So here you have like less organized patterns, and you see a so-called dense overcast here. So the bottom line is that there's a lot of information in the satellite images about convective structure. And there's also a direct relation between the patterns that you see in the infrared images and tropical cyclone intensity. But spatial temporal information in infrared imagery is underutilized. And so you might have seen pictures like the one to the left of these trajectory forecasts. And trajectory forecasts have improved a lot over the past decade, while tropical cyclone intensity forecasts, like the ones to the right, have very large errors. So what you see here is the predicted wind speed versus forecast error for some common intensity guidance tools. And the line I put in here of forecast 24 hours forward in time. And if you look at it, you can see that the predictions are sort of like all over the place. So some intensity guidance are predicting that the storm will intensify, and some predict that they will sort of weaken. So you have very large forecasting errors here. And that's sort of bad news if you live on the coast of Florida, and if you want to know whether you need to evacuate or not. So I think I have to click on this. Okay, so spatial temporal information in infrared imagery is underutilized. So how can you as a sort of data scientist or computer vision researcher help? So what is it that scientists and forecasters need? Well, the thing to realize is that science and forecasting is ultimately done by humans in the loop. I like the forecaster here that looks at all the screens. So it's really like a human that issues the forecast. And whatever you create is really a guidance tool rather than kind of like just a number. That's not very useful. So what's needed is interpretive quantification of the spatial temporal evolution that you see in the imagery. So that can bring insight on how physical relevant predictors relate to one another and to intensity change, as opposed to like a black box forecast, because that's not going to be used we put in operational use. However, these GOES imagery that you see here, they're updated every like 15 to 30 minutes, and they're at very high resolution. So the information that you produce has to be easily digested in real time. So what we need are sort of concise representations. But current guidance tools are really based on spatially average quantities. So it doesn't really take into account all this information that you have in these images. So we need like representations that are more descriptive and more, you know, a richer representation of the kind of structures you see here. So my student Trey, he just published a paper in Journal Applied Meteorology and Climatology on how you can unlock sort of the rich information contained in these GOES imagery about the evolution of these convective structures in tropical cyclones. So our main objective here is really understanding and providing scientific insight rather than prediction alone. So we want to help scientists, forecasters relate sort of the TC internal structure to the environment and behavior, such as like intensity change in this a short-term 24-hour window. So, so current intensity guidance are based on pretty much like spatially average features. So what Trey has been developing here is like a rich scientific interpreted dictionary of continuous functions for tropical cyclone structure. So we'll call it ORB, and the acronym stands for Organization, Radial Structure, and Bulk Morphology. So let's look at some examples here. So the ORB functions for organization, they leverage the axisymmetry of the mature intense storm, like the one to the left. So these are basically temperatures. And if it's like very organized, then if you think about the gradient, then it's more or less pointing like radially out or in. So in an idealized storm, you'll basically have the gradients pointing in the radial direction. So if you look at the angle between the temperature gradient and the radial direction, in a sort of organized storm, that deviations of that angle or the variance of that angle is very small. So, and this is called the deviation angle variance. So in intensity guidance tools, the DAV is only computed for like a fixed radius, such as like within a disk of radius of say 250 kilometers from the center. So there's a lot of information that's getting lost there. So to retain more information, we're basically working with continuous functions. So this figure here shows you the variability of the deviation angle as a function of the radius. So for Hurricane Edward, that's very highly organized. You can see that you have a low variability, especially here around the eye wall, where you have very intense, very fast winds, rotating winds. And Hurricane Nicole, which here is like weakened, has a much lower variance. So we're basically looking at this entire function as a predictor of organizational structure. And ORB functions similar for radial structure, they probe the core structure on tropical cyclones. So instead of using sort of handcrafted features that guidance tools are using now, like looking at the thickness of the eye wall and so on, we're using predictors that are entire radial profiles. So it's basically the temperature as a function of the radius averaged over the azimuthal angle. And see if I can get the figure here. So this figure to the right shows you the hourly radial profiles for Hurricane Nicole. And these lighter colors indicate higher intensities. And they sort of have, you can see the warm eye and the eye wall. So a high intensity basically corresponds to like this clearest eye wall structure. And you can look at how the intensity of Hurricane Nicole is changing, like it's weakening and intensifying. So you have this sort of information if you look at the entire sequence of radial profiles rather than like typically image features, which is like the common practice. And you can also look at all functions for bulk morphology. So here we're computing level sets for different temperature thresholds. And again, rather than looking at sort of threshold-based statistics, such as, let's say, the size of the storm below, let's say, -20 degrees, you can compute these level sets. And then for each level set, you can compute statistics such as the size and skew of each level set. And you can regard these statistics as sort of a continuous function of the level set threshold. So here we have the size as a function of the level set threshold. So that's another kind of orb function. So basically, in summary, is that orb is basically a diction of physically interpretable functions for TC structure. And then you can use these as predictors. Okay, so how well does orb explain or nowcast rapid intensity change? So the operational definition of rapid intensity change is more than a 30 knot increase or decrease in sort of the short 24-hour window. And rapid intensification and rapid weakening events, they're associated with the largest forecast errors. And they can also, these errors can also be very devastating, like if you get it wrong. And when nowcasting, we're referring to estimating probability that a storm is currently part of a rapid intensity change event. So given predictors, observed predictors now and the past. So you can think of this as a probabilistic classification problem. And we're using a logistic lasso model here because of interpretability. So we're basically writing the log odds of a rapid intensity change as a linear function of different predictors. So here we're just using the main effects. And we're also including a last L1 penalty term for feature selection. And we're looking at 3 predictor sets here. So orb only are basically the principal components of the orb functions and lagged values. So ships only are environmental predictors and lagged values, which are used for operational intensity guidance. And the ships and orb is sort of combining the satellite information and the environmental information. So how well can we classify rapid intensity change event? So the figure is showing the AUC, which is the area on the ROC curve metric, which considers both sensitivity and specificity. So a larger AUC is better. You can read about the details in our paper, but the bottom line is that orb only, like if you just use the satellite information, you can capture a lot of the information that's in the environmental predictors, which are shown here in green as ships only. And if you combine the two, then you can do better. So this is basically just a sanity check that we're doing, something right here. And there's sort of information in the images about the environment. So I think, so what's next? I think this is sort of the interesting part here. So far we've only used the principal components of the orb functions. So what we want to do is to look at the entire orb functions and then look at the joint evolution of these. And that will inform us about how the spatial temporal evolution of these images evolve in time. And they will be interpretable because the scientists or forecaster can relate them to something that's scientifically meaningful. So this is actually a very new idea instead of looking at features, which is kind of the approach that's being taken now. And we're going to look at 2 aspects. One is structural trajectory analysis, which is describing the spatial temporal evolution of these image patterns and how they relate to current intensity change. And then structural forecasting, which is predicting this whole evolution of the image patterns, the convective structure and TC intensity change like forward in time with 6 or 12 or 24-hour lead times. So, so you can follow the spatial temporal evolution of a tropical cyclone in this orb space by looking at the sequence of these functions. So to the left here, we have the path of Hurricane Katrina through the Gulf of Mexico. And to the right, I'm showing the evolution, well, it's the corresponding trajectory in orb space. But in this case, I'm just showing the principal components of a single orb function. And it's probably best shown like as a video. I didn't put that in here. But like if you look here in phase space, you can see this clockwise oscillation. And it actually matches sort of the day-night cycle of the Hurricane Katrina. So what you're seeing when you go here is sort of the night. You see like the hurricane breathing. It's night and then day, which we show in light colors here. And there's actually two deviations from the cycle. And there's the point D. You can see that it's kind of getting a little bit messed up here. And if you look at the map, it's this point here. So that's where Hurricane Katrina turns north and then accelerates and becomes like a major 100-knot hurricane. And the other point is around here somewhere, where you get a deviation around point E. And on the map, it's over here. That's when the tropical cyclone begins to interact with the land. So basically what we have here is that orb allows us to monitor the tropical cyclone, and we can quantify these changes in the tropical cyclone convective structure by looking at these sequence of functions, and we can relate them to behavior and also intensity change. And this is exactly sort of what we want to do. So what we're working on now is to looking at the trajectory over the whole set of orb functions. So we want to analyze the structural evolution of tropical cyclones by comparing high-dimensional distributions. So with that, I mean distributions of 24-hour trajectories over the whole set of orb functions. So basically a 24-hour sequence of these one-dimensional functions. So how are they, for example, different in distribution for, let's say, rapid weakening events and non-rapid weakening events? So that's a very challenging statistical problem. It's like how to compare high-dimensional distributions. So basically distributions over trajectories. And so a new local two-sample test by Il-Mun Kim, who graduated this spring, may actually answer that question. So this is our sort of preliminary results. It's a visualization. So what you see here, like each point in this figure represents an entire 24-hour trajectory in orb space, like a whole sequence of orb functions. And the blue, let's see what I should say. The red points here correspond to modes of evolution that are identified to be more representative of rapid weakening events. And you can look at, here's an example of a sequence. You have a storm that's weakening. And the blue points correspond to modes of evolution like this one that are more common among non-rapid weakening events. So this is done by like a statistical significance test. So basically what this two-sample test does, it leverages probabilistic classification to compare high-dimensional distributions. And this preliminary work, we're using logistic lasso principal components, but I will propose is instead to use like entire sequences of entire orb functions and do the same sort of analysis. So the second project my group is working on now is structural forecasting So this is a proposal track paper for a NeurIPS climate change AR workshop. And Trey is presenting this work next Friday at the NeurIPS workshop. I think it's called Tackling Climate Change for AI. And the next, this figure here is a schematic diagram that kind of summarizes the main ideas. So here you see a time axis from the past to present to future. And the first row here represent the present and recent past. And the second row is the future time. So that's a forecast. So the first row is basically what we've done so far in the JMC paper. So that's nowcasting. So we take the observed infrared imagery to the left. We're representing these structures with these orb functions, this dictionary, very large dictionary of one-dimensional functions of convective structure. And then we use these to predict observed intensity. So that's nowcasting. So what we want to do is forecast. So we want to forecast intensity 6 or 12 hours forward in time. And in principle, you can do it with traditional end-to-end deep learning approach because the sequence of images that looks like a video. So you could potentially take the observed imagery and directly forecast intensities. And that's not what we're doing. That's not what we're going to do. Because such forecasts, they're non-interpretable. I think it would be hard to convince a forecaster to put this in operational guidance because it does not provide information about what's actually happening to the tropical cyclones. So our proposal is to instead compute these structural orb functions that we worked on it for a couple of years with our domain scientists, and then use autoregressive models, like generative models, to project these forward in time. So basically, pull out the structural summaries, the orb functions, and then we can build a generative model for forecasted structure. And then use these to predict intensity. So you basically can, if you can do nowcasting and you can generate these structures, then you can forecast. So this intermediate sort of structural forecast would basically provide something that end-to-end prediction models and traditional intensity guidance can't do, which is basically a tool for monitoring high-dimensional time series of like physically relevant predictors. You can relate these functions to one another and also to intensity change. And it will also give you like a means to understand basically how these predictors relate to the environment and other kind of observations and how they relate to short-term intensity change. So I'll see I'm right on time. So to summarize, we're using geostationary imagery to better understand the evolution of tropical cyclones. But instead of using spatially average quantities or threshold image features, we have developed this dictionary of continuous functions that are scientifically interpretable to quantify like the TC structure that you see in infrared imagery. And then you can use these as inputs to statistical machine learning models. So both for structural trajectory analysis, where you can compare sort of time sequences of orb functions, and also for structural forecasting, which is what we're sort of proposing or working on, which is to project these forward in time and then relate these to sort of TC intensity change. So I think that's I don't have a reference slide, so this is my last slide. And yeah, welcome to ask questions.
Thank you. Thank you, Anne. I'm not sure if Yingnian is sort of coming in and out, so I will step in. Wonderful talk. Thank you very much. It's very interesting. It's much more relevant to me because half of the pictures you showed of hurricanes my home is somewhere in that in those pictures. Let me ask you this. Let's see if anybody else has any question. But in the meantime, let me ask you this. Structural trajectory analysis. I mean, you are a student of one of the greatest geometer of last century. So let's ask this question. Isn't there some geometric representation of these trajectories? Somehow the way the shapes are formed of how the hurricanes move. Of course, there are tons of covariates which affect this geometry. But isn't there a geometric point of view to look at these trajectories rather than trying to extract features or make them in some sort of functions or this or that?
Actually, there was a great talk yesterday in Stamps. I'm advertising that by Jenny Evans, and they do look at it for guidance, but they're fitting like things like polynomial and things. I don't think people are using. First, this is a great field to work on. There are not many statisticians working on this. You'd be surprised. So the models they're using operational guidance are things like linear models, linear regression. To answer your question, yes, but I'm not doing that here. It's kind of about I'm just treating it as a 2-sample test, and we're basically saying you can do this test if you can just turn it in probabilistic classification. So I'm not looking at geometry, but I'm thinking of it as whatever predictors you have, if you can do probabilistic classification, then you can do a 2-sample test. I don't know if it made any sense.
I think that makes sense, but ultimately, I mean, I've sat many nights sort of looking at these trajectories, trying to predict, is my home on the way or not? I've done this a few times, and somehow the shapes of these trajectories, and I feel like looking at historically the geometries of these trajectories, so somehow there must be in some morphological space, these things must cluster into very few patterns that emerge.
I think you can look at it, but what I'm using here is like, I'm actually not really looking at the trajectories at all. So maybe I was confusing. So I'm looking at the trajectories in like the phase space of how the images are changing. So I'm only like predicting intensities. So I do want to use all these information about the environment and information about what's in the image. So this is like, I'm really just studying for this example, just a pattern in the image. So the trajectory here are just like the trajectory in this high dimensional space. But for trajectory analysis is sort of like a different thing. And yeah, I think there's a lot of stuff you can do by looking at the shape of it. The talk I heard yesterday by Jenny Evans, they're basically fitting polynomials and have a mixture model for, polynomials. So I don't know if it answers your question.
Yeah, no, I think it does. I think, I mean, in the real physical space, surely there are trajectories and shapes, but even in the phase space, I think there are patterns and they're geometric patterns. And I think there's something to be done there.
Right.
Okay.
Yeah.
If there are no other questions, thank you very much, Anne. Fantastic talk. Good to see you again after a while.
Thanks so much. I'll stop sharing my screen.
Our next speaker is Arun. There you are. So while Arun pulls up, Arun is a professor, John and Eva Silag, endowed professor at Michigan State University. So one of the reasons for having Arun here is that for people who work in statistical approaches to image analysis, this topic area of human biometrics is probably the biggest, source of data for our approaches. And Arun may say more about it, but I don't think there are that many card-carrying statisticians involved in this area. So, I mean, I look forward to this talk, but it will be a good inspiration to look at some of these applications and learn about problems in this area. Go ahead, Arun.
Yeah, thank you very much, Anuj. Thanks also for the invitation. Was very pleased to listen to the presentations prior to this. Very inspiring. And just looking at the various techniques that have been developed is remarkable. And the application arena is also very rich. And so what I'd like to speak about for the next few minutes is on the topic of biometrics, and more specifically on the topic of altered biometric data and its implications in many of our current events about deep fakes and such. So I just want to kind of give a brief overview of what we have been doing specifically with altered biometric data. So just to get us started, biometrics is the automated recognition of individuals based on their biological and behavioral characteristics. And these traits are expected to be distinguishing. That means they are reasonably unique to an individual. And at the same time, they're repeatable, which means that there is some degree of permanency to these features when associated with an individual. So biometrics is effectively using attributes such as fingerprints, palm prints, iris, etc., in order to recognize an individual, which could mean verifying an identity or even identifying an individual from a database of labeled identities. So there are a large number of biometric traits that are being studied, although the more popular ones are fingerprints, which you see on the upper left, face in the middle row to the left, and then of course iris is another modality that is being studied, as well as palm prints. But at the same time, many of the other traits have also been studied and have been evaluated, traits such as gait recognition or ear biometrics, and you have vasculature pattern, and so on and so forth. So the list goes on, but the two fundamental questions revolve around the uniqueness of a trait and also the permanence of a trait. And the issue of persistence is very important, because we would like to know if we can compare and successfully match two images of an individual that are obtained after a significant time lapse. And so the issue of persistence or permanence is also equally important. Just to kind of get us started here, when we talk about biometric matching or biometric comparison, we assume that we are given two biometric samples, and often we want to estimate two numbers. Here we have two fingerprints, and we estimate the likelihood under the hypothesis that they are of the same person, and then the likelihood under the assumption that they are under the hypothesis that they are of different people, and then you can take a ratio between the two, compare it with the threshold in its very simplistic form, and then there are also other complex ways of formulating the problem. And so be it two fingerprints or two iris images. The iris is the annular structure that we see over here, and it excludes the sclera, the eyelids, and the eyelashes. So when we talk about iris recognition, we often talk about this annular-like structure, sometimes referred to as the colored portion of the eye. And then, or it be two face images or two hand images. Based on the geometry, one could answer these questions. But in today's talk, I'd like to focus on the altered data. What happens if there is an adversarial attack against a biometric system, either in the digital domain or in the physical domain itself, as we will see in the next slide? What kind of countermeasures can be deployed in order to ensure that we can detect these altered data points, especially if it is intended to be adversarial? So this is a paper from a different research group from 2019, CVPR, where they had this black box attack, a decision-based black box attack. And on the upper row, this illustration shows a dodging attack, which means you have two images, and normally these two images would have been successfully matched. But can you create an image that looks very similar to this image? And I hope you can see my pointer. but will not match with this image on the extreme left. And so by executing a certain sequence of queries or a certain number of queries, the authors were able to generate images that look very similar, at least visually speaking, to this image that you see over here. But nevertheless, when you were to match this image now, for example, with this image, it would be a non-match under some certain threshold. And then you have the impersonation attack, where you see the original pair of images here, and this should be a non-match, as we call it in biometric recognition. But then can you do this black box type of attack where you generate an image based on a sequence of queries, a set of queries, such that it looks very similar to this image that you see, but when you match this image with this image, you actually get a match. And so hence the term impersonation attack. So one could clearly see the vulnerability of face recognition systems to some of these subtle changes, at least visually imperceptible to some extent. These changes that can cause the biometric system to kind of be challenged, and it starts mismatching identities. So this is one reason why the whole topic of altered biometric data or adversarial attacks on face recognition or any biometric recognition system for that matter has taken on prominence in the field. So there are also some attacks that can be launched in the physical domain. And if you look at this particular video, again from a different research group, you will notice that the person detector system, it has to detect a person or a chair in the scene, actually gets confused because of the presence of a physical adversarial patch associated with this individual. So if I start playing this video, you will notice that the detector is able to detect the person on the left, but the person on the right is not detected as far as the detector goes. And it is because of this adversarial patch. And so if I were to move this forward here, you notice here now when the person changes the position or even the side of that particular object that he is holding, in this case, it's an adversarial object, you notice that the person detector system is confused. And it's not just related to that person. If I were to fast forward this a bit more, now you can notice if that adversarial object is presented to the second person, the person on the left, that is, you notice that there is a problem in the detector. The point is fairly simple. Many of the deep learning based systems are often vulnerable to these type of adversarial attacks, be it in the digital domain, like I showed in the previous slide, or in the physical domain. And you must have read several articles about how even autonomous vehicles can behave in a chaotic manner when the traffic sign is slightly altered. When a physical traffic sign is slightly altered, changing a stop sign to say, a yield sign, although visually it would look like a stop sign, but it has been changed so in a concerted manner that the autonomous vehicle thinks that it is a yield sign. So it can cause a lot of disruption when you talk about automated systems that are running atop deep learning based systems. But the focus here, of course, is on biometrics, and one could imagine some of the concerns that can come about when these type of attacks are launched. Now, this is a real world challenge, as I alluded to, because of the widespread use of Photoshop and Snapchat filters on face images. And deep learning based manipulations are being increasingly used in order to modify attributes of an individual, say adding beard or changing the color of the hair, or changing the disposition of the mouth, or even age progression and age regression can be accomplished using these type of filters and these type of software that is predominantly these days based on deep learning. And sometimes the changes are so subtle that, again, like I said earlier, not visually perceptible, but it can cause some kind of damage in the digital domain, because the system that is employing these detectors or comparators can be confused by the image that is being presented. So image forensics has taken on importance now, especially digital image forensics. Questions like which sensor produced this image? So you're given, say, in this case, an iris image, which also has the periocular region. Which sensor produced this image? Or is this an altered image? Has it been altered in any way? Or if you have a set of images, questions like how are these images related? In other words, which is the original image, what is called as the root node, and how are these images, how have these images been modified in order to generate these sequence of images. So this has taken on prominence in the field, especially due to the availability of these filters that can very easily be used to modify images subtly, but in some cases adversely. So well, one of the questions is, given an image, how do you connect it to the sensor that produced this image? And this is done using many different techniques. And one of the techniques that is very popular, which is still in play, although it's over 14, 15 years old, is using the principle of photoresponse non-uniformity. And what this does is look at the sensor noise that is manifested in an image. When we think about a sensor and the image that is produced by it, we can have at least two types of noise. One is a short noise, as it's called, a random component, perhaps due to thermal fluctuations in the environment. But there's also a fixed pattern noise, which is more of a deterministic component. And this fixed pattern noise can be divided into two, roughly speaking. Again, one is what is called as the dark signal non-uniformity. That is when the pixels are still responding, even though it is completely dark. And so there is still some electric discharge happening, and it's non-uniform. Not all the detectors are behaving in the same way. Or you could have what is called as photoresponse non-uniformity, PRNU, which is when the same amount of light is incident on these detectors, the optical power that is generated may be different. And so you notice that there is a non-uniformity, and often this is referred to as a sensor defect, in the sense that different detectors within the same pixel array or sensor array may behave differently, and that is in some sense manifested in the image that is acquired. So there are some well-known techniques by which one could extract what is called as a sensor reference pattern related to a sensor by collecting some training images. And then when a test image is supplied, one would use a simple correlation process in order to decide if this test image belongs to this sensor or not. And this has been traditionally done through a denoising operation, where you take the original image and then you apply some kind of a filter. Wavelet filters have been extensively used. And what this does is act as a denoising unit. And so when you take the difference between the two, what is left is something like a constant noise that is embedded in the training images, and that is referred to as the sensor reference pattern. And there is also some interest now in sensor de-identification, especially for photojournalists, in order to ensure that the image that is collected cannot be linked to a specific sensor. And the reason is for privacy purposes, and also for journalists who are concerned that if they were to publish some images in the digital domain, that it can be traced back to them. And in some cases, that may not be the best thing to do. So we've been looking at ways in which you try to maintain the integrity of the image. So the source sensors are called out here. These are just various types of smartphone sensors. And then on the right, you see the target sensor. So the image is subtly modified so that its biometric utility is maintained. So you can still use this image for biometric recognition, but it has been spoofed in the sense that if you were to extract that PRNU noise pattern that I talked about in the previous slide, it would be associated with a different sensor. And this is to both advocate for privacy, but also spoofing in order to confound a PRNU-based sensor identification system. And so all these things, the overarching point is, on one hand, there is a need for detecting altered data because it can potentially cause great havoc. But at the same time, in many other applications, there is a need to cause perturbations of the image for privacy preserving reasons, because biometrics is very closely and intricately linked with an individual's privacy. And so how do you balance these two things? So when we talk about altered data, although there is an adversarial overtone to it, there is also a privacy overtone that can't be denied as far as biometric recognition is concerned. And so deep fakes have also caused a lot of issues. And many of you might know this website, thispersondoesnotexist.com. It is a website which generates synthetic images based on GANs, various type of generative adversarial networks. And all three images that you see here are synthetically generated. These are deep fakes. These individuals that the system generated was not based on actual images or actual people. It may correspond accidentally to someone in the real world, but it was not intended to do that. And of course, you can see some artifacts that are perhaps indicative of the fact that these are synthetically generated, but it's not very easy. One could easily imagine this coming from a regular DSLR camera with some motion blur or so that is more prominent over here, or some other type of pixel defect that is present over here. The point being that detecting deep fakes is a non-trivial problem. You can detect those deep fakes which have been generated based on a certain principle, as long as you have a large number of images pertaining to that principle. But once newer methods emerge, then the previous techniques used for detecting deep fakes can fall apart. And clearly, deep fakes are not just confined to face images. One could imagine this being used, and is already being used, to generate other types of natural scenery also, in order to, in some cases, deliberately confuse people. Another aspect of altered data which is causing some issues is this notion of morphed faces, where you combine two face images. For example, here, my pointer is now pointing to ID1 and then ID2, and then you mix these two face images, morph it really, and you create this morphed image that I'm pointing to that is in the center. And this image now matches with both these images. And so this is referred to as the magic passport, where the same passport can be associated with two individuals because the face image in that passport, when subjected to an automated face recognition system, will actually end up matching with these two face images. And so you see other examples here. This is ID1 and this is ID2, and you've created this face image, which visually you might assign it to just one of these two face images, but the system will associate it with both identities. And you see a similar example here, ID1 and ID2. This is a morphed image, and this morphed image can now match with either. And this can be problematic. And so now certain countries have come up with laws that would prevent passport photos from being acquired in homes, for example, or in specific places. It has to come from an authorized location where the picture of that person is taken, and cannot be taken in one's personal space. So clearly, these are problems that are being encountered even in border control systems, wherein a morphed identity can match successfully, as far as the automated face recognition system is concerned, with two distinct identities. One of the problems that I'd like to to discuss in the remainder of the time that we have is this notion of near duplicates. These are subtly modified images. So you see a set of near duplicates here, a set of near duplicates here, and a set of near duplicates here. In this case, we are using very simple transformations. But as we will see later on, you can also use some of the filters that are available now to create these near duplicate images. And the definition of near duplicates in our case is that these images are not perturbed unduly, so which means the SSIM, the structural measure of similarity, is within a certain threshold. So what we are trying to do is, given a set of images like this, you have 5 images here, we would like to create an image phylogeny tree where it says that image 5 is the original image, and it has been modified to create images 2, 3, and 4, and then image 4 has been modified to create image 1. And here we assume that we don't have access to any metadata or EXIF data pertaining to the camera. All we have is just the raw images, and often we notice this even in the internet, where someone posts one image and then that image is taken and modified subtly and then reposted. And so now you have a plethora of the same face image floating around, and often it is required to know which is the original image that was posted and what are its derivatives. So there is a lot of practical application, especially in the context of media forensics. So the importance of the problem is, we want to deduce whether a set of photometrically transformed images originated from a single source or multiple sources. It can also be used to detect image tampering. That can be done as well. And you can also determine the transformation parameters that are connecting two images. So to construct an image phylogeny tree, it's a 2-step process. Let's assume you have 5 images here, and you compute an asymmetric matrix. It has to be asymmetric because transforming 2 to 1 should be different from transforming 1 to 2. And so we make some strong assumptions, including the assumption that you can't have cycles in this graph. And so from this matrix, then we use a tree spanning algorithm to generate something like this, where it says, well, this is the root node, and here are the relationships between the component nodes as well. But the challenges are plenty. While this kind of an application has tremendous impact in terms of forensics, it's not an easy problem to solve. There are a large number of photometric transformations, indefinite number, and each transformation is characterized by multiple parameters. For example, a simple Gaussian filter, you need to define what the window size and variance are. And then each parameter can have a range of values. For example, a simple parameter such as window size can be 3 by 3, 5 by 5, and so on. And we still need to distinguish between A and A to B transform from B to A transform. So it's not simple in the sense that a single metric will not give us that information. We need to have this direction-specific information, a vector. So our approach, as we wrestle with this problem, has been as follows. We try to use a generic parametric function to model the relationship between any 2 images, notwithstanding what kind of transformation was actually used, because like I pointed out, the space of parameters and the space of transformation is not easy to model. And so we use a generic transformation function. And so given 2 images A and B, we estimate the parameters of this function in both directions, because we don't know whether A was transformed to B or B was transformed to A, or they are not a function of each other. And then at the same time, we then use the likelihood of these parameters to determine which of the 2 cases is more likely. That is, whether A was transformed to B or B was transformed to A. And so the idea is fairly straightforward. You have a source image. Now we have this generic transformation function. What we do is have a sequence of basis functions, and then which are conditioned on the parameters of the transformation function. And now what we would like to do is to estimate the parameters. And so by modeling the transformation from A to B, similarly, we have to do it from B to A. we apply some straightforward, well-known algorithms in order to estimate the parameters. But the important thing here is because we don't know in advance what the transformations are, we approximate the transformations using a set of basis functions. So we have many different kinds of functions that we tested in order to do this. But ultimately what this does is these functions are used to model transformations from A to B, and then also from B to A. And here you see a set of functions that we tested. Some of them are holistic or global functions, and some of them are local. And so you can see some of the artifacts that are introduced because these are locally applied. Now, when we model the transformation in both directions, we get two sets of parameters, which we denote as alpha and beta. And so then what we do is we compute the likelihood ratio of the estimated parameters to obtain an asymmetric measure. And to compute the likelihood ratio, we need the density function for the parameters. And these density functions are obtained during the training stage, where we use a small set of transformation functions, but we give a large number of values. So it generates many sets of near duplicate images, a massive number of near duplicate images. And then we estimate this forward transform as a function of alpha, and also the reverse transform as a function of alpha. So that's why you have PF and PR. And now that we have estimated alpha and beta, we plug it into these estimated likelihoods and then obtain these values, lambda alpha and lambda beta. And then once we have the asymmetric matrix, we use depth first search to construct the IPT. So just some experiments, and then I'll bring this to a close. So we have generated many different IPTs, in this case, about 2,000 odd image phylogeny trees by subjecting face images to a random sequence of 4 transformations. And then what we do here is see how we can estimate the root node. That means what is the original image, and how we can reconstruct the entire tree itself. And the previous baseline is seen over here. For root identification, the best performance was 47.27. And for IPT reconstruction, the best performance was 18.75. And what we did was we improved the state of the art to now 80% for root identification, and then for IPT reconstruction to about 66%. These numbers don't look very attractive up front, but we must understand that this is a very hard problem, and the previous state of the art found it challenging as well. So the generalizability, can this technique be used for other types of images? So we have tested the generalizability and also on unseen transformations, including deep learning based techniques, which means during training, when we estimate those density functions, we have no understanding of what kind of transformations will be used, but still can we do the the prediction using transformations that were not seen during the training stage. And so we did some experiments in that front as well. The root identification accuracy, as you can see, ranges from 83 to 95%, but the IPT reconstruction accuracy, in the case of Photoshop, we were able to do perfect reconstruction, but not so in some other cases. So it's a very challenging problem, but a very interesting problem. So let me summarize what we talked about today. Biometric data is being used in many different applications, not just for recognizing individuals, but also in many cases to extract some information like demographic attributes, environmental characteristics, sensor properties, etc. And then digital image forensics has taken on prominence because there are questions like which sensor did this image come from, especially when there are so many images floating around in the web. Has this image been digitally tampered? And in many cases that could indicate some intent. And what is the relationship between a set of near duplicate images? So that's a very important question as well to construct the image phylogeny tree. And then issues related to privacy, which I didn't talk about today, but we have used this altered data to impart privacy to face image using a concept called a semi-adversarial networks. But that is a discussion for a different day. So I'll stop there. These are some of the publications that we have on this topic. And I will stop there. I went a little over time, but Anuj will forgive me. Thanks again for inviting me.
You are, thanks very much, Arun. You are very much forgiven. This is excellent problem area for us to think about. There's a lot. I mean, your life must have been made really complicated by all these deep fakes and, I mean, pictures and videos. Let me ask you this question that, some time ago, I think it was a different field where people used to look at actual image pixel statistics.
Right.
And I think you were referring to it a little bit somewhere, this sort of the non-Gaussianity of this distribution. It's something actually Anne Lee studied in as part of her PhD too, long time ago. So is it still, is there still a role to play to describe these deepfakes and or to detect these deepfakes?
Yeah, great question, Anuj. In fact, those are the techniques that are now taking on prominence because many of the deep learning based techniques to detect deep learning based attacks require massive amount of training data. And often they are confined to a specific problem. And so looking at natural image statistics and understanding that certain transformations can lead to certain types of image statistics is an important piece of analysis. And so most of the current approaches, they try to bring both these things together. A data-driven approach based on deep learning, but also a statistics-based approach based on our understanding of natural image statistics and then understanding how these statistics are perturbed, if you will, when an image is generated using GANs. And there is also some recent work on trying to understand if the GANs leave a footprint in the synthetically generated images so that you can actually determine which GAN generated that image. So the short answer to your question is those techniques are still very applicable. Of course, they have to be modified to accommodate the type of deepfakes we're encountering, but those techniques are very much relevant.
Yeah, I feel like it should be, it should be a topic area on its own, like what you just said, at the technique that is used to generate or fake or perturb an image would leave some kind of footprint in some image statistic domain. Some higher order statistics, somewhere it will, visually we can't tell any difference. We are very happy with pictures of Obama we get,
right.
But somewhere in some of, some projection of this in some domain, we'll get some change in distribution of the pixels.
And those are the types of techniques that may not require massive amounts of training data as well.
Yeah, exactly.
We're able to understand those types of patterns. And so, here there are 3 deep fakes, and visually one can be fooled. But as you rightly pointed out, in some transformed domain, they can leave some footprints about how these images were generated. Anuj, I see 2 questions. Can I go ahead and answer them? Do I have a couple?
Yes, please.
So we have a question from Vic. 3D surfers are now at our fingertips. Are they used in biometrics? Yes, 3D face as well as 3D fingerprints. 3D fingerprints are making a comeback because of this need for contactless fingerprints. And so there is some work in the past that was done in this front, but now again, there is much work now being done on taking pictures of fingerprints that are contactless. And so you take it from a slightly, at a slight distance, and then you create a 3D surface of that. There's a question from Ranjan. Do you have any thoughts on identifying altered images as done in image steganography here? Yes. So in fact, in AAAI 2018, I believe, they actually changed the MSB. And then what they noticed was it created some type of, let's say, artifacts in the image, which led to the breakdown of face recognition systems. And so one could potentially identify altered images using, what has been used previously in steganalysis and steganography as well. I don't recall of any paper recently that has explicitly leveraged that, but I'm certain people are thinking along those lines. The greatest difficulty is that the pace of changes that are possible is remarkable now, because GANs have opened up many kinds of attacks. And so it is difficult to put some kind of a structure to what kind of changes are possible. But if we get a better grasp of that, I think some of the techniques that were previously used and are still being used, for image steganography can be appropriated. But you're right. If we don't have the true image, then all bets are off, because we now don't have a bivariate problem. You have a univariate problem, and that often is very difficult to resolve. Is this a real image or not? Anuj, there's one more question. Do you want me to take that? It's from Bin Yu.
Yes, please.
Okay. Thank you. I heard from David Wagner's group that the same adverse latex work for a variety of DNNs. Do you have any insight into why? Oh, that's a great question, Bin Yu. One of the challenges is also people have noticed that it depends on how many epochs of training the DNNs have been exposed to. So that is another variable also. While it is true that an adversarial image presented to one kind of DNN is also adversarial to another type of DNN, it is also equally true that that adversarial aspect is in some sense impacted by how the training was accomplished and what kind of data was used for training. So I would tend to think that if we have more insight into that aspect, as far as how much training was accomplished and what kind of data was used, I believe we might be able to understand better why the same adversarial attacks seem to work for a variety of DNNs. I'm sorry, I don't have a solid answer, but there are these other variables in the picture that have to be taken into account.
So am I right interpreting what you said as actually the input data might be driving this, not just particular architecture? And people usually use very similar training data. That's why they have similar weak spots.
That could be the case. I know they've done some GradCam analysis by back propagating and finding out the salient regions in the image. And in some research work, I believe, I think it was either in NeurIPS or CVPR, where they've shown that many different DNNs still focus on the same salient region. And so at the end of the day, even though the architecture is different, and even though the number of parameters are different, if by using a GradCam kind of analysis, if one were to determine that the same salient regions are critical in making the final decision, then that problem would persist. But if the salient regions are different, then perhaps that problem can be alleviated to a certain extent.
So salient region in the image training, like regions.
I'm sorry, Binyu, I missed that. Sorry.
What do you mean by salient regions in the original image?
That's correct. So one thing that we can do using these neural networks is when a neural network is operating in the inference mode and making a classification decision, that decision can be back propagated to the intermediate layers to find out which portions of the image contributed most to the final decision.
Yeah, we actually have something tried to do that, but yeah, I'll follow up with you if you don't mind offline. Yeah, thank you.
Thank you for your question, and look forward to that.
Thanks very much, Arun. It feels like a lot of these talks should have just 1 hour, 2 hours per speaker, and we could go on forever. But thank you very much, Arun, for coming, and hope to include you more and more in this statistics image analysis community in the future.
I appreciate that.
All right. Yeah. All right. So our last speaker for the session and for the workshop is Ting Ting. Ting Ting is a freshly minted associate professor of statistics at Pittsburgh. And not only that, she is actually the incoming chair for this section on imaging in statistics in imaging. So in some ways, or in many ways, I'm handing it over to her for the next year to take it up another level and make this section grow in all directions. So go ahead, Ting Ting.
Thank you, Aluji. So first, I want to thank everyone for staying until last minute in this workshop, and especially on Saturday, 5 p.m. And I also want to express my appreciation to Luigi and his colleagues in devoting a lot of time and efforts into organizing this wonderful workshop, taking advantage of this workshop. And it's great to see so many people during the pandemic. I hope next year we can see each other in person. For today's talk, I'm going to present high-dimensional directional network analysis for focal figures. Okay, next page. So right now, most of my research is about understanding the mechanism of the human brain. Typically, the brain is regarded as a high-dimensional directional network system consisting of many brain regions as network nodes that exert influences onto each other. The directional influence from one region to another is called directional connectivity. It is also called effective connectivity. Right now, most of the studies of the human brain networks focus on functional connectivities or on low-dimensional directional network. In just recently, we started to see some methods for analyzing high-dimensional directional networks in the brain, such as Professor Vellucci's work. But still, the efficient methods for identifying high-dimensional directional networks in the human brains are still lacking. So to address this gap, we developed a statistical modeling approach to characterize high-dimensional directional networks in human brains. And we use this method to understand normal and abnormal directional brain networks for patients with epilepsy. And the reason we chose to study epileptic brains is because we find directional network method is more efficient for understanding this patient's brain mechanisms. First, let me briefly explain what is epilepsy. It is the fourth most common neurological disorder, which affects approximately 3 million people in the US. In a typical focal epilepsy settings, when a seizure occurs, the abnormal excessive neuronal activity starts from a very special brain area called sedia ancellum and spreads quickly to many other brain regions. So here, let me show you a short YouTube clip of a epileptic patient. This can give you some basic understanding of what a focal epilepsy look like. So this is an epileptic patient. In the beginning, he behaved normally. He was smoking and listening to music, even though epileptic patients shouldn't smoke. Despite his normal behavior, if you look carefully at his brain activities, you can see that some of his brain regions started to show abnormal neuronal activity as indicated by those high frequency oscillations. And those abnormal neuronal activities became more pronounced and also spread to many other brain regions. Then more and more brain regions for this patient in the entire brain, his entire brain showed this overly synchronized excessive neuronal activity. Then this patient also have this kind of clinical symptoms of seizures. His body shook, his muscle jerked. And in the end, this patient also lost consciousness. So this is what an epileptic, let me come back to my slides. Okay, this is what focal epilepsy look like. So you can clearly see that focal epilepsy is a directional network disorder. The seizure propagation, which starts from sedia ancellum and spreads to many other regions, is a clinical pathological directional network phenomenon. And so we want to use a directional network method to understand how this patient directional brain networks changes from normal state to abnormal state. And we also hope to use this upturned network methods to improve epilepsy treatment for neurologists. In our analysis, we use a very special human brain data called intracranial EEG data. Intracranial EEG has a similar electrical physiology as EEG. The key difference is that it uses electrode placed inside the human skull to record many brain regions neuronal activity. So this figure gives a better illustration how intracranial EEG data are collected. So for this patient, a large part of the skull was removed by neurosurgeon. Then around dozens of electrodes are placed on the exposed surface of this patient brain, and each white dot here corresponds to one intracranial EEG electrode. Due to this special data collection technique, IEG data have very nice properties. Each IEG electrode directly records local brain areas neuronal activity with high spatial resolution and high temporal resolution, and also a strong signal to noise ratio. So we want to use this data to identify directional brain networks between these recorded regions and reveal their brain network changes from normal to abnormal state. Okay, so I want to mention that this intracranial EEG data are actually not collected for this research purpose. It's used in daily epilepsy treatments, and this is because there are around 30% of patients have drug-resistant epilepsy. So for these patients, medicine has no effect on them. The best chance for them to achieve seizure control is to surgically resect the seizure onset zone. The success of the brain surgery highly depends on the accuracy in localizing the seizure onset zone. So for this purpose, neurosurgeons place intracranial EEG electrode inside those patients' skull to record many brain regions neuronal activity. Then trained EEG experts manually examine those IEG data to identify the seizure onset zone. The procedure was pretty much like what I showed you just now, and they look at the IEG data around the seizure onset, and then they're trying to identify the region that first have the abnormal activity as the seizure onset zone. Unfortunately, this manual examination is not always successful. We think this is because the brain is a high-dimensional, complex directional network system. The complex interactions among those brain regions are difficult to visualize. And also these complex interactions make the manual identification of seizure onset zone very difficult. So to address this problem in the clinical treatment for epilepsy, so we want to use our network method to improve the accuracy in localizing the seizure onset zone. Okay, so first we recognize three challenges in the development of efficient methods for identifying high-dimensional directional network brain networks. The first one is due to our limited understanding of the brain, it is very difficult to build a perfect model that can accurately characterize activities of many brain regions or their complex interaction relationship. In other words, our model for high-dimensional directional network has some model inadequacy. And the second, even if we have an accurate model, this model must contain many free parameters to characterize directional connections among many brain regions. Meaning the estimation of these many model parameters can have large estimation errors. The third one is the analysis of high-dimensional brain data can be computationally intensive. It turns out that all the existing methods, directional network method, address part of those challenges. So for example, biomedical engineers develop many information theoretical methods to quantify directional connectivities. This include directed transinformation and partial directed coherence. And these measures usually focus on quantify a pairwise relationship between brain regions, and they cannot separate direct connections from indirect ones. So those indirect connections that are mediated through other brain regions. So we think it's more appropriate to build a model that can characterize simultaneous directional connections among many different brain regions. So in the literature, the most popular models for the brain's directional connectivity were built by biophysicists. So they use very complex ordinary differential equations to describe the complex biophysical mechanism of the brain. And usually those models are very difficult to be scaled up to high dimensional system. In addition, we also find that all ordinary differential equations models are highly sensitive to model inadequacy and data noise, and usually they are computationally intensive. So we built our own high dimensional directional network models. So due to the limited time, I hear many talk about the intuition of our model. So our approach is an integration between a multivariate autoregressive state space model with a clustering structure. With this model, we can simultaneously characterize directional connections and clusters among many different brain regions. So here, let me briefly introduce some notations here. We let YIT denote the observed IEG measurement of region I and time t, and XIT denotes the neuronal state of region I and time t. Because our IEG data have very nice properties, we can assume a simple observational model to link the observed IEG measurement to the underlying neuronal state of the regions. So CI is an unknown constant used to standardize different scales of neuronal activity in different brain regions. And the epsilon IT is a data measurement error. Then we assume a first order multivariate autoregressive model at the neuronal states to describe the directional connections among the deep brain regions. So under this model, each region I's neuronal state and time t depends on all the other brain regions' neuronal state at the previous time point. The gamma ij is an indicator for the directional connections, and aij is a coefficient. So by introducing gamma ij, we can distinguish non-zero directional connections from zero ones. So identify directional connections is equivalent to selecting non-zero gamma ij's. And so this multivariate autoregressive state space model has been used in many other time series analysis. But the key differences between our model from the existing one is that we need to apply this model to the activity measurement of many brain regions. In other words, D is large. In practice, D can be easily larger than 50. In many cases, D can be larger than 100. Then direct application of this multivariate autoregressive state space model to IEG data can give estimates with large estimation errors. So to improve the estimation efficiency, we incorporate the clustering structure and also called modularity in our model estimation. This clustering structure has been widely reported in the literature of human brain networks. It turned out that it is associated with the human brain's functional organizations. So we decided to use this prior knowledge to improve our model estimation. So here I want to point out that we just know that the underlying brain network have clusters, but we don't know where are the clusters, which brain regions form a cluster. So here, to identify both directional connections and clusters, we modify the stochastic block model as a prior for our model parameters. So let me briefly explain the stochastic block model. It is a generative model for network patterns in a cluster structure, but it is mostly used for observed network data. So for example, stochastic block model is mostly used for social network data. In those cases, subjects are network nodes, and the observed interaction between subjects are the given observed network edges. For our cases, we're actually addressing a more difficult problem. We don't know the network edges, so our goal is to infer those directional network edges. To address this, we modify stochastic block model to be applied for our model parameters. Then we develop a Bayesian framework that can integrate the clustering structure and data information to make inferences of regions, directional connections, and cluster assignments. So in the end, our identified directional brain networks include both identified clusters and identified directional connections. So this is different from many existing brain network methods. Usually they just focus on either identified directional connections or identified clusters only. So our Bayesian method provides a unified tool for identifying clusters and directional connections simultaneously. So it turned out that this is more efficient. Okay, so let me I won't go into the technical details. Let me talk about the real data analysis results. This is the most interesting part. So we apply our method to the analysis of 6 patients' intracranial EEG data. And these patients have different epilepsy types and different seizure onset zone locations. But we identified consistent network results. So let me show first show the first patient network results. And this figure shows the placement of intracranial EEG electrodes on the left hemisphere of this patient. It turns out that region 37 is the seizure onset zone. So in our analysis, we didn't use the location information of seizure onset zone. So we want to see that whether we can identify unique connectivity property of seizure onset zone. So here, let me show you our identified directional network for this patient from 300 seconds before to 300 seconds after seizure onset. So we want to see how this patient brain network changes. And in our network plot, all the diamonds correspond to seizure onset zone. So the nodes or regions in the color red are the regions fall into the cluster of the seizure onset zone. For epileptic patients, it is of great interest to identify the seizure onset zone cluster because it is a group of regions that are most affected by the activity from the seizure onset zone. So the regions or nodes in light blue did not belong to any cluster. And the region in the same other color, such as dark blue, green, yellow, are the region identified to be in the same cluster. Okay, so for this patient, we find that before seizure onset, his brain network, directional brain network, was pretty stable. The directional connections were sparse, and the size of the seizure onset zone cluster is small. It included usually just seizure onset zone, and it's a few immediate adjacent regions. So this indicates that very few brain regions are affected by activity in seizure onset zone before seizure onset. However, right after seizure onset, we find that the number of directional connections and the size of seizure onset zone clusters increase significantly. So for this patient, all the brain area fall into the seizure onset zone cluster after seizure onset. Then to the end of the seizures, then the number of directional connections and also the size of seizure onset zone clusters reduce to the level before the seizure onset. Okay, so this is a network result for one patient. We also evaluate the network for another patient. So this is for another patient. And so the right panel shows the networks, and the left panel shows the IEG data. And so we also show the brain network from 300 seconds before to 300 seconds after seizure onset. So similarly for this patient, before seizure onset, his brain network was pretty stable. The seizure onset zone cluster was small, and also seizure onset zone connected to just a few brain regions. However, right after seizure onset, the seizure onset zone cluster increased, and also the number of directional connections of the seizure onset zone also increased significantly. And then to the end of the seizure onset, but for this patient, actually just 50 seconds after seizure onset, then the cluster size of the seizure onset zone and the directional connections of the seizure onset zone reduced to the level before the seizure onset. So you can see that this patient have a different directional brain network after seizure onset compared to this previous patient, it turns out that these two patients have different epilepsy types that give them actually different clinical symptoms. Another interesting thing we identify using our method is that, okay, so we find that for several patients, okay, for example, for this patient, several regions outside the seizure onset zone cluster, such as TMP and TMA, had no changes in directional connections, even though based on this region's IEG data, these regions had epileptic activities. So using our methods, we are able to separate the regions that are truly involved in the seizure propagation from the regions that just show ictal or epileptic activities, but are not affected by epileptic seizure propagation. So this result cannot be achieved just by visual examination of IEG data or just using low-dimensional directional network method. So far we show you the directional network structure changes for the epileptic patients. We also want to identify the unique directional connectivity properties of the seizure onset zone. So we evaluate directional connectivity changes for all the recorded regions. So the right panel shows the time series of connectivity changes for all the recorded region for this patient. And each time series is a time series connectivity changes for one region. The red line corresponds to the connectivity changes for the seizure onset zone. So this is what we find. Before the seizure onset, or just like 10 seconds after seizure onset, we find that directional connectivity of the seizure onset zone is not distinguishable from other brain regions. However, right at the seizure onset time, the seizure onset zone and also its a few immediately adjacent regions have largest increase in directional connectivities. So based on these unique connectivity properties of the seizure onset zone, we develop a seizure onset zone localization method. So across all the 6 patients with different epilepsy types and different seizure onset zone locations, using our method, we are able to achieve 100% true positive rate and less than 3% false positive rate in localizing the seizure onset zone. So here I want to spend more time for discussing the result for localizing the seizure onset zone of 6 patients. So for this patient, this figure shows the electrode placement of this patient. So this patient is a very difficult case, both in the clinical practice and the research analysis, because this patient actually have more than one seizure onset zone locations. So this indicates this in the ROD, in the RTA, and also recorded by RTM. And this, typically, existing quantitative method can only identify at most one seizure onset zone locations for such a patient. But our method can successfully localize all the seizure onset zone locations for this patient. So we also tried another network method. You can see that the user can only identify one locations, seizure onset zone locations, or they are computationally infeasible. Okay, so in summary, in this approach, we develop a new high-dimensional directional network modeling method. And this method has properties of robustness and improved estimation efficiency and also computational feasibility. We use this method to consistently reveal the evolution of the directional brain network changes from normal state to abnormal epileptic states for epileptic patients. And we also develop a new seizure onset zone localization method, which has a much higher accuracy than existing method. We think our method outperforms existing method mainly for 2 reasons. The first one is that our method uses high-dimensional directional network results. And the second, so our method focuses on We also think when our method identify the right and unique connectivity properties of CC on their own. Usually the existing method just compare different brain regions and connectivity strengths, but our method trying to evaluate the changes of directional connectivities for different brain regions. So our method is more sensitive to the network changes that due to the seizure propagation. We think that our method can improve the current efficiency in epilepsy diagnosis and treatment, because usually the neurologists need to manually examine this enormous IEG data. So here I want to thank my collaborators. Mark Crick is a neurologist and also a director of EEG lab at the UV hospital. He provided us with all the patient's data. C.G. Talbot is a neuroscientist and also a clinical engineer. He pre-processed the data and also identify the data for us. Guofeng Yan is a biostatistician at the UV hospital. She's a close collaborator of mine for many years. I also want to thank my student, Yao Tian, who did all the work for us. And thank you all for your patience.
Thank you very much, Ting Ting. Very nice work. Let me see if there are any questions. I mean, you mentioned at the start that, you know, it relates to the presentation Marina had about directed graphs. So, I mean, how, going the other way around, how about you applying your techniques to fMRI data?
Oh, that's a good question. Thank you for asking this. We are indeed using that to fMRI. But I want to mention that fMRI is actually more complicated than intracranial EEG. One biggest issue is that they record the brain activity for a very long time. Even though it's just a second, but actually it's a very long time. The brain is changing a lot. So we indeed apply our method to fMRI data, and we are able to identify some very consistent clusters of regions that specialize in the brain, different brain functions, such as auditory brain, and also visual cortex. So those are very consistently identified, because they are highly specialized brain functions. So that's what we find. But for other brain areas, I think such as the frontal lobe, I think those frontal lobe areas are, I believe they are actually involved in multiple clusters of functional specialized brain areas. So it needs a more advanced method.
Yeah, I mean, epilepsy, at least from the data you were showing, the change point was so clear and it's so dramatic, then it's easier probably to detect the changes in the network as opposed to functional tasks in the functional MRI, which are more subtle.
I think task-based is okay. We tried resting state fMRI. The issue is for resting fMRI, the different subjects are actually in different states, and they are always thinking different things. So the clusters you identify are always those very consistent ones. For example, visual cortex, even though we didn't use any special information, we're always are able to identify visual cortex. And also sensory motor areas. Those are highly specialized brain areas. And it's very shared in common across different subjects. But for other areas, needs more time to analyze.
Okay, well, thank you very much. This is a good time to thank all the speakers in this session. Fantastic job. Maybe this is also a good time to thank everybody who spoke at the workshop. I don't know whether they are all here. Some are here, some are not, but thank you very much. Thanks for people who asked questions, participated in one way or another. Thanks to the organizing committee for putting up with all the emails I sent out. And thank you to all my students who, the biggest task was just to let people into this session. We need to sort out that issue somehow. Just people in and out of the meeting. So I think this is time to say thank you and close the meeting. And hopefully this sets up a good enough motivation to do such a meeting next year as part of the section in some ways. Keep the eyes open, keep it broad, keep it inclusive. try to bring in more people who would have not known and seen about this particular section of ASA before.
Thank you.
Thank you, Anuj.
Thank you, Anuj.
Thank you. Bye-bye.
Thank you.
Thank you. Bye.
Thanks so much.
Thanks,
Yeah.
Anne.
Thank you.
Thanks, Ben.
Bye.
So I don't know if we keep any of the chats. There was some good information exchanged during the chats, but I suspect the moment we close this session, it's all gone.
So
Or
what
maybe
happens? No. What happens is that the chat gets saved in everybody's local drives when you switch it off.
Really? In
At
fact,
least that happens for me.
I did click an option which says chat save, and it says saved.
Okay, yeah,
Not
that would
sure
also
where,
do it.
but not sure where.
It saves in your local drive somewhere under some. Well, I mean, for me, it is under documents/Zoom. But
Okay. So I can Google it. I mean, I can search over
search
my.
it.
Okay.
Yeah.
Just in case somebody asked for some question that was already answered.
Sure.
So we will get, including from the speakers here, I will ask you, please send your talks. I have already gotten from a lot of these speakers already. And so we will work on putting all the videos, the Zoom recordings online, and the talks next to them. So
I think YouTube you can access, right? YouTube already store it, right?
Yeah.
So YouTube usually also include the chat.
Okay, I haven't actually gone to YouTube and looked at what is visible in YouTube.
Also Bilibili, right? I had never heard of it. Okay. I had never heard of it before this.
You need to create an account and put in your credit card, and we will all share your credit card. So, okay, everybody, take care. Have a good weekend.
Bye.
Thank you. Thanks,
Thank you.
Anuj.
Thank you, Anuj. Yeah.
You're welcome.
Bye.
Bye.
Hey, Chow, maybe it's time to close the session.
Okay.
I think I don't know if there is a way to save the chat, but hopefully it is saved somewhere on its own.
Yeah, maybe just like the video, maybe I can check. There are some emails after I closing the meeting. And yesterday I got the email. It says all these videos we recording yesterday has been saved, and we can use the link to track all these videos. Yeah.
Okay, let's meet next week sometime to organize all these videos.
Okay. Yeah,
let's
sure.
take a break. Thank you very much, Chow. Thank you.
Thank you. Yeah, thank you. It's a really wonderful workshop.
Yeah, I thought so. I
Yeah.
really enjoyed Hong Tu's talk. He's in another planet.
Yeah.
He's doing some remarkable work.
Okay.
All right. Taking off. Bye-bye.
Okay. Bye-bye.